data by using, so okay, when we reduce the amount of data by using convolutional neural networks, not neural, but using convolutional technique, we also add another calculation inside our neural networks. So you can imagine the problem that we have. So we want to reduce the amount of data, but to reduce the amount of data, we also need to calculate still the data itself to reduce the amount of data. So it's not just okay, we reduce the amount of data. No, we actually need to forward propagate the reducing result, and then we also need to back propagate the reducing amount, the reducing result, and that is the convolutional neural networks. So if we are using this convolutional neural networks in just a regular NumPy calculations, it is going to be so slow, and we also going to need a heavy computational calculations. So the problem, okay, so now the question is, so again, I'm using the MNIST dataset to show you, if we are using the MNIST dataset and we are getting such a slow progress, let alone we are using this kind of an image, right? So we need to so it's not about the technique right now. It's not about the technique or the formula right now. It is about how can we improve the speed. So now the problem is, how can we improve the speed of the training using the same technique, which is using the same techniques such as convolutional neural networks, okay, the technique of convolutional neural networks, but we want to improve the speed. So again, it is not about the technique. Now if you are probably wondering, what if we are using the new technique? But if we are using the new technique, or adding the new technique, if we are adding a new technique, if it's a calculations, we still oh my god, we still, not that we still, we basically not reducing the speed, because the more calculation is equal to more time. Okay, so it's not about the new technique, it's not about the new formula, it's not about new equations. How can we improve the time itself? And I guess this is the perfect moment for me to introduce you to a framework. So I'm going to use something called Pytorch, and I'm going to explain about Pytorch in the next segment of this video. So in the previous segment I mentioned something called Pytorch, and if you're not familiar with Pytorch or a framework in a neural network, so there's a few of neural networks framework that you can use. Like you can use something called TensorFlow, and you can use something called Pytorch. So Pytorch is one of the most used library. You can say it's a library, you can say it's a framework, so that we can work in our neural network. So what is Pytorch? Pytorch by definition is an optimized tensor library for deep learning using GPU and CPU. So if you want to learn more about Pytorch, you can go to their documentations. So you can go to the Pytorch documentations. But now let's go into the basic of Pytorch. So first of all, let's go to Google Colabs as usual, and we can rename this to Pytorch. Let's call this Pytorch basic. So we are going to go through the basic of Pytorch, like what Pytorch can do, and etc, etc. So first of all, of course, we are going to import Torch, to import the Pytorch library, and we can click enter, and let's wait. So first of all, I want to so first let's create something called tensor. So we can create tensor using Pytorch. How can we do that? So let's create a variable called my tensor, and it's equal to torch.tensor, and let's create a tensor. So it's going to be 1, 2, and 3, and then we could have 4, 5, 6, and let's print my tensor. So now we create a tensor, okay, and we can also doing this my tensor dot shape, and it's going to be 2 by 3 because there's 2 array, and inside of these 2 array there's 3 value. So that's how you create a tensor using Pytorch. You can also create a tensor with the data type that you want. Like for example, again, let's create my tensor, and it's going to be torch.tensor, and it's going to be just the same 1, 2, and 3, and then 4, 5, and 6, and then we can choose the data type that we want. So let's, for example, we have we can have float 33. So in order to create the data type of float 33, we can just type torch dot float 33, and it will create, oh my god, what am I doing, float 33 float, oh, okay. And let's print. So this is going to be a float. So in the previous one we have an integer, okay, and then we have float, which is we have dot like right here, and this is why, and like this is how that we know that we have a float data type basically. So that is we can create the data type. And what else? Okay, we can choose the device that we want. Like Okay, what do I mean by that? So let's create another example. So it's going to be torch.tensors, and it's going to be the same 1, 2, 3, and then it's going to be 4, 5, and 6. And let's choose the data type of torch dot float 33, 32, and then we can choose the device that we want. So if we have a CPU, we can use CPU. If we have a GPU, we can use a GPU. So but for now let's use the CPU. So we can create, so like this, my tensor, and it's going to be a data of a float 32 that has connected to the CPU that we have. So basically that's what device. Now okay, we can also create a tensor that basically how can I say it? It basically have a gradient record. So okay, I'm just gonna create the tensor flow first. It's going to be tensor, and it's going to be it's going to be 2 by 3 of a tensor. It's going to be 1, and then 2, and then 3, and then we have 4, 5, and 6, and the D type is going to be torch dot float 32, and then the device is going to be CPU, and then we can have required grad. Oh my god, what is this? Okay, required grad, and we can put a true in it. Okay, wait, this is not right. Okay, and we can print, and now we have the required is equal to true. So if you don't know what required grad is, torch required grad requires grad. Okay, so you can go to the Pytorch documentation if you still, and this is a big framework. So as you can see, like this, there's a lot of things that you can learn from it. So, and I'm going to recommend you that do not try to remember all of this, but I always see framework or a library, especially in a machine learning or deep learning case, as a big calculator. So this is because we are working with the numerical data, and of course something like Pytorch, they just optimize your data, your numerical data. So this is just a big kind of a calculator. You can see that way. You can see. Now let's go to the. So what is this? So it could record the operations on the tensor. Like for example, if you have this kind of tensor, you have this tensor, and then you using additions in order with other tensors, it would record the that additions action, if that makes sense. It would record that operations. Like for example, if I have addition or subtractions or multiplication with this tensor, it would record that multiplications or that additions, and we can use this grad, which is the gradients, to create our backward applications, because in backward applications we need to, going back based on the forward applications. So this is why they have this requires grad, because by setting this into true, they will like memorize what's going on with this tensor. If that makes sense. I hope that makes sense. Okay, so and then I want to let's start with the GPU thing. So you can check by using Pytorch. You can check if you have a GPU or not. Checking if we have a CUDA GPU. Okay, we can check if we have a GPU by doing this. So it could be device is equal to CUDA if torch.CUDA is is available else CPU. So what this code is doing, if we have a GPU, we are going to use that GPU. But if we don't have a GPU, have a GPU, we are going to use CPU. Now in Google Colab, they actually provide a GPU, a free GPU for us. So you can using GPU by going into runtime and then change the runtime type. Now you can choose either you can use a CPU or GPU. Okay, and of course if you want much more powerful a GPU, you can purchase the additional computer units from the Google. Now let's use a GPU. So if we are changing the runtime or changing between the CPU into the GPU or GPU into the CPU, we are going to lose all of the works that we have already done. So basically all of this executions is going to be gone basically. So but let's do that anyway. So now I'm going to use the GPU, and we can see here it's connecting into the GPU. Okay, now we get, you can read it. It is connected to Python, to the Google Compute Engine backend using the GPU instead of CPU. And as you can see, we lost all of our executions in every cell. But we can run all to run every cell that we have. So let's run all, and let's wait. And now we are using a GPU, and if we are running, now we are running the cell, and since we are having the GPU here, now we are using the GPU instead of a CPU, if that makes sense. And also you're probably wondering why we are using a GPU, because why using GPU instead of instead of CPU. Okay, so why we're doing that? The answer is, okay, let's make it bigger. The simple answer is basically we can do a parallel computations by using the GPU. Is we can perform a parallel computation by using GPU. So this is the answer. If we are using a CPU, like for example, the calculation that's happening in the CPU is they are going to calculate everything one by one. So for example, if I okay, I'm going to give you an example. If we are using a CPU, it's going to be like this. So everything is going on one by one, right? If we are using a GPU, the computation becomes parallel and everything becomes getting compute all at once. So if we are using a GPU, it's going to be like this. Okay, it's going to be like this instead of like this. And okay, I have I love this video by the Mythbuster explaining the GPU versus the CPU. So basically, what has happening is that okay, I don't know if we can hear that, but we don't need. So basically, if we are using the GPU, this painting is going to, it is performing one by one. So this is the CPU part basically. So everything is going to be one by one, right? And then start the eye, and then previously we have the head. But if we are using a GPU, which is doing everything in parallel, so everything is going to be all at once. Here's what happened. Everything is going to getting executed all at once. So this is what the difference between a GPU and a CPU. They are doing so. CPU doing it one by one, and the GPU is doing it all at once. In the neural network case, you can imagine something like okay, let me pull out. Go ahead, pull this out. So this is our example in the previous segment. If we are using a CPU, you can imagine like we are calculating x1 and w1, and then x2 with w2, x3 with w3. So it's going on one by one. Okay, and then xn multiplied by the xn. Okay, everything going on one by one. But if we are using a GPU, you can imagine like this is for the sake of intuitions. You can imagine like x1 multiplied by the w1, x2 multiplied by the w2, x3 multiplied by the w3 is happening all at once. So that's why we are using a GPU, because it is allowing us doing a parallel computations. And okay, you're probably saying, okay, I do have a GPU in my computer, but in order to use a Pytorch, but you need to use Pytorch or TensorFlow, and both of these frameworks is going to need not just a GPU, but you are going to need CUDA GPU. So what is CUDA GPU? I hate Yahoo. So Google. So CUDA GPU. Okay, in computing, CUDA is proprietary parallel computing platform application program interface that allows software to use a certain type of graphic processing units for accelerated general purpose processing. So you cannot just use a GPU. You need to use CUDA GPU to perform training your AI or training your neural networks. And this is why in device we are using CUDA, because you cannot just use any kind of GPU. You need to use a CUDA GPU to perform the parallel computations. And both Pytorch and TensorFlow, they are going to need, the CUDA one, not just the regular GPU. So if you don't have a CPU, not CPU, but if you don't have a GPU, you can go to Google Colab to get a free access into your GPU. And if you don't have a CUDA GPU, still you can go to the Pytorch, because they have the CUDA GPU that allowing you to perform a parallel computations by using these frameworks. Okay, so that is why we are using GPU instead of a CPU. I hope you understand. Okay, now let's playing around with the Pytorch. So first of all, we can create let's call this 1A. 1A is going to be, so let's do a common initialization. Okay, let's do a common initialization. It's going to be like, for example, x is equal to torch.empty, and the size is going to be 2 by 3, and let's print torch.empty, and we get, wait, what is it? Okay, so we get this kind of a initialization, and we can use this initialization in our neural networks. Like, as you remember, in the first iteration of a neural network, we need to create a random initializations, and we can using torch.empty to create our random initializations. And another one is we can create torch.zeros, and torch.zeros is going to be the size of, again the same, let's do the same, it's going to be a 2 by 3, and let's print, and we get the tensor that have 2 by 3 dimension that has a 0 value. Now let's what else? Okay, we can also use the random initialization, like for example torch.ran, and the size is the same. We get 2 by 3, and the x is going to be a random initializations, just like what we have in a NumPy, and it's going to be 0 from 0 to 1 of a random initializations. Okay, now what else? We can also use torch.ran n, and the size is going to be just the same, and we can execute this one, and it's going to be a random value between from negative 0.5 to 0.5 basically. So that is the difference between ran and ran n. And then what else? We can have x is equal to, oh my god, we can have x is equal to torch dot not ice but 1, and it's going to be size, again the same, and then let's run this one. Not once, it once, I believe. Okay, so instead of 0, we can also calling the ones value to create an array that, you know, it has one value of a data. And then we can have something called torch.i. Torch.i. Oh my god. And what is the torch.i? So it would create just this kind of a I shape. So the first index is going to be 1, second index in the second array is going to be 1, the third index in the third array is going to be 1, and so on and so on. So that is the torch.i. You can use this for creating I believe a bigram model. You can use this for the NLP problem. Like for example, if you want to create a transformers by using bigram or a trigram model, you can use this, I believe. And then we can have x equal to torch dot arrange, like for example. And let's start from 0 and end at 5, and the step of 1. So it will create an arrange value from 0 to 5 as an index. So this is working as an index, not as a, you know, the last value. So we have from index 0 to index 5 that has step of 1. And then what else? We can have torch. Oh my god. We can have torch dot linspace, something called linspace, I believe, linspace, and it's going to be start from, let's say 0.1, and then it ends in 1, and the step is 10. So it would create, okay, I'm just gonna print it. So it would create torch linspace torch.linspace start at 0 steps. Okay, it would create just like the arrange part, but we okay, so we have 10 steps, which means it would create a value between the start value and then the end value with the amount of steps that we have. So we have 10 steps, which means we have, you know, 10 amount of number here. So if we for example, if I have 5 steps, it will create 5 number between the start and the end. If I can create 7, and I can create you know, maybe a random number 13, so it will create a number that has the value from the start to end, and the amount of those number is going to be 13 basically. So that is what linspace is. Again, what else do we need? Okay, so we've already learned about batch normalizations. We can use something called torch dot empty, for example. And instead of this empty, we can have the size of like for example like maybe 1 and 5, and we can doing this. So the normal is going to be min of 0, and the std is going to be 1. And let's create this. So it will create a random value that has the mean of 0 and the standard deviations of 1, which is just a Gaussian distributions. So we can create a Gaussian distributions by doing this this command by using Pytorch. And what else? And of course we can create the opposite of Gaussian distributions. You can say something like that, which is the uniform distributions. And it's going to be like again 5, and it's going to be dot uniform like this, and it's going to be from 0 to 1. Okay, let's, and again it is going to create a uniform distributions that has the value from 0 to 1. Okay, what else? Okay, now let's going through the B part, and it's going to be converting tensor type. So it's going to be okay. I need this to be big. Okay, now like for example, if I have I don't know, tensor is equal to torch, just an example, a range, and it's going to be 5, not 5, 4. Okay, so let's print the tensor, and let's also print the data type. So it's going to be tensor dot d type. So if we are not, what is the default data type that Pytorch have? So it's going to be the integer of 64. That is the default data type that if we are creating a tensor using Pytorch. So now let's change the tensor types. So okay, we can do this, we can do that, and then the tensor, let's change the tensor into Boolean, like for example. And let's see the data type, and it's become Boolean. So this is how you change the data type in a tensor of a Pytorch by using Pytorch, I mean. And then we can change into something called so tensor is equal to tensor dot we can say tensor dot short to get a shorter data type. So previously we have integer of 64, now we have integer of 16. We can also using the opposite of short, which is tensor is equal to tensor dot long, and it's going to give us the long data type. And then we can use tensor is equal to tensor dot half, and it would give us a float 16 of a data type. And then what else? Well, we are going to float territory here. So now let's change this integer 64 tensor is equal to torch dot float into a float data type. And torch d type torch dot tensor. Oh my god, it's going to be tensor dot float and we get the float of 32. So if we are calling the float of the float just a float, we are going to get the float of 32. Now what else? So you can have a tensor is equal to tensor dot double, and it would give us the float of 64. So previously we have float 16 by using the half function, and then we have float, and then we have float 32 by using the float function, and then finally we have float 64 by using double function. Okay, what else do we need? Okay, we can also, so it could be C1 converting array to tensor and vice versa, Okay, so what do I mean by that? Let's say I have, okay, so I'm going to import numpy as np, and let's say I have an np of array, which is the numpy array, and it's going to be np.zeros, and let's say I have 5 by 5. So we can change this array into a tensor by doing tensor. Okay, let's create a variable called tensor from array, basically, and it's going to be torch. So this is going to be in a array, and let's change this array into a tensor. So torch from numpy of np dot array, and now this zeros has become, this zero array has become a tensor basically, and then we can go back tensor back basically. Let's say tensor back. So we can going from, oh my god, no, okay, from that into numpy again by doing this. So we're going back to this. Okay, we can do that basically, and then, oh yeah, let's print it. Why not? So let's print tensor from array dot d type, and let's print the tensor back. Not tensor back. Oh my god. Dot d type, and it's going to be, yeah, it's going to be in the torch, and then it's going to be in the numpy array in the torch tensor. So this one is the torch tensor, and then this one is going to be the numpy array 1. Okay, so we have that, and then I don't think mathematical expression is important, but it's worth to mention. So let's do a tensor math, just an example, but I don't think it's important because we can use NumPy. Like for example, let's say we have torch.tensor of 1, 2, and 3. So we have another one, and it's going to be torch.tensor of 4, 5, and 6. Oh my god. And let's do addition. So in order to apply the addition, we are going to need the output first. Let's say the output is the z1, and it's going to be torch.empty. It's going to be 3. Okay, and let's do the torch.add to do the additions. It's going to be adding between the x and the y, and the output is going to be the z1, and let's print the z1. So you can do additions by using Pytorch. So it's going to be add 1 plus 4, and then 2 plus 5, and then 3 plus 6, and then you need to have the output dimensions, and then use that output dimensions as your output result, basically, for your addition, for your operations, mathematical operations. I'm not gonna lie, I don't think it's important because we have NumPy to do, which is I would say NumPy is more friendly. If that makes sense, or I just get more used to NumPy when it comes to mathematical operations. What else? Okay, so also we can do something called broadcasting by using NumPy. So let's say broadcasting. So what is broadcasting? Okay, well, let me give you an example. So I'm going to have x1 is equal to torch.random, just random, and it's going to be 5 and 1, and the x of 2 is going to be torch.ran of 1 and 5. How about that? Now we can create the output. Is going to be z, and it's going to be x1 minus x2. Let's run this, and then let's see what z1 is. Okay, so how can I explain the broadcasting? So basically, let me print the x1, and let me print the x2. Okay, so what broadcasting does is, well, it broadcasts. Okay, how can I explain this one? It will perform basically. Okay, so you have completely different dimensions, right? So basically what happening is you can do this this part value, and then you can broadcast this value into all of this value. Basically that's what happened. So for example, you have this value, and then you get it is going to be, so this value minus this value, and this value minus this value, and then this value minus this value, this value minus this value, and then this value minus this value, and all of those answer is going to be recorded in the first of your array, which is this array, which is the first index of your array, or the 0 index. And then, so that's what broadcasting means. It is not what do you call, it is not element wise operation. So you can have one value, and then you can, doing mathematical operations on this one value throughout the entire this value, throughout all of the other value. So that's what a broadcasting is. Okay, and then the same thing happening with this one is going to be minus all of this, and the result is going to be all of this. So you don't need to have the exact the exact rule of matrix additions or matrix subtraction, because so this is what broadcasting means. Okay, I hope you get it. Okay, right now let's do the neural networks. Okay, I'm going to do this. So it's going to be neural networks implementation using Pytorch. Okay, so let's do this. So how can we implement the neural networks using Pytorch? So first of all, we need to import some dependencies, and it's going to be import torch, and then it's going to be import torch.nnsnn, and then we need to import, import torch.optim as optim, and then we need to import torch.nn.functional as f, capital F, and then from torch.utils.data we need to import data loader. Okay, and then wait, is data loader, I believe that's data loader, and then we need to import torch vision dataset as datasets, and then we need to import torch vision transforms as transforms. Okay, so let's try to run this, and now we need to, so let's create the fully connected layer, or neural networks, not layer. Okay, so we need to create a class, and let's call this NN, that stands for neural networks, why not? And in this class we need to module, so we need to pass module, and then we need to create init function. So it's going to be define init, and then it's going to be self, and then we need to get the input size, and we also need to get the number of classes that we need. that we would have. Okay, and then we're going to need the super function, and inside the super function we need to pass our this class name, and then we need to write self like that, and then init like this, like that. After that, we need to create self dot fully connected one, so this is going to be the first hidden layer that we have, and n dot linear, so it's going to be linear function, and it's going to be the input size and how many neurons that we want to have. Let's say we want to have 50 neurons. Okay, so that is the first hidden layer. So okay, so this part is basically the input and the output. Okay, and then in the fully connected 2, which is the second hidden layer, we need to create an n dot linear. And of course, what is the input? Well, the input is 50, because that is the output from the first hidden layer. And then the output is the number of classes, because it's going to be categorical neural networks. Okay, and then we're going out from this function, init function, and then we create the forward function for the forward propagations. And inside the forward functions, we need to have self and the input. So x is going to be the value of the self dot fully connected one and the input. Okay, so this is going to be the input, right? Basically it's going to be our input data. So our input data is going to get into this function, which is the self fully connected function, and it's going to be going to execute here. Okay, and then after we get, so because this is like the the linear function, we need to apply the non-linearity to it. So I'm going to do this. So f dot value is going to be giving a non-linearity into this linear function. So non-linearity implementation here. Okay, and then we save the output of the non-linearity inside of this x. And then we need to have self dot fully connected to, and inside this fully connected to, we are going to input the output from the nonlinearity implementations, which is the first hidden layer. So this is like going inside the second hidden layer. Okay, now we can going out from this function, and we can create checking some. So let's go check the model. So it's going to be the model, and it's going to be an n. Okay, we create the n model. So we're going out from this class like this. Okay, and then so we are going to use the MNIST dataset. So it's going to be MNIST implementation dataset, and we are going to have 784 amount of data, of course, and then we are going to have 10 number of classes. So again, we need to know the input size, and the input size of the MNIST dataset is 28 by 28, which is 784, and the amount of classes is going to be 10 because it is a handwritten data from 0 to 9. Okay, and then we're going to create a variable called edge, and it's going to be torch.random.n, and it's going to be 64 and 784. And we can print the model dot shape. Okay. And now let's print this model. Does not have the attribute of shape. Oh, I forgot to return bx. So, okay, now we have our model. Okay, so what I'm doing here? So what I'm doing here is that I create just a random initialization basically to see if this model is working. So if you so if you using this as an input, and then you get this kind of output, which is basically, so basically we know that this neural networks that we have is a correct implementation. Okay, so there's no error inside of this neural network. So this part is just for, again, this is for the checking part. Okay. Now we need to set the device. Set device, and it's going to be device equal to torch dot device, and it's going to be CUDA if torch dot CUDA dot is available, else we are going to use CPU. So we are going to use the CUDA. So we are going to use a GPU if we have a GPU, and we are going to use a CPU if we don't have a GPU. And let's run this, and then we need to create the hyperparameter. Okay, now the hyperparameter is going to be the input size. Again, hyperparameter is a parameter that you can change basically. So it's going to be the input size, which is 784, because we are using the MNIST Dataset. MNIST Dataset, and then we are going to have number of classes, which is 10, and then we are going to have a learning rate of, I don't know, maybe 0.001, and then we are going to use the batch size of 64. Let's use 64 amount of data, and then the number of epoch is going to be, let's say, 10 epochs. Okay, let's run this part. Now we need to load the data. So load data, and we are going to get the MNIST dataset from the Pytorch, and this is how. Okay, so Pytorch MNIST, so they provide the MNIST dataset for us. where is it? Wait a minute. Pytorch MNIST. Where is it? Is it here? Datasets. Okay, so Pytorch actually have their their dataset. So they have a bunch of dataset that we can use. So we don't have to download from other places because they provide the dataset for us. So they have a lot of datasets. Like for example, in the case of image classifications, like they have the Caltech dataset, they have the Cipher 10 dataset, they have the Fashion MNIST dataset. They have the a lot of dataset basically, and you can use all of this dataset for your implementation of your neural networks, just for the to study the neural networks in general. So you can use all of this dataset that being provided by the Pytorch, and this is how you load the data from the Pytorch. So we are going to create train dataset, and it's going to be dataset dot MNIST datasets dot MNIST, and the root is going to be dataset slash, and then train is equal to true, and then transforms is equal to transforms dot to tensor. So we are going to import the dataset into tensor, and download is equal to true. So this is how we download the dataset from this repository. And then we're going to need train loader. So train loader is going to be data loader, and the data loader is going to be dataset is equal to the train dataset, which is this part, train dataset. Okay, and then the batch size is going to be the batch size, which is here. Okay, batch size, and then we are going to shuffle the data, and it's going to be true. And okay, so the datasets dot MNIST is going to be connected from this. So if you're not so if you're facing an error, you probably don't import the Torch Vision dataset. So this part is going into this part, and this part is going into basically this part. Okay, Torch Vision dataset, which is this is what they have, Torch Vision dataset. Okay, now other than train, we need to have test dataset. So in the test dataset, we do the same, and it's going to be datasets dot MNIST, and the root is going to be the datasets, and the train is going to be false because we don't want to train this data. We want to test this data, and transforms is going to be transforms dot to tensor, and we need to also download the data. Okay, it should be as transforms. and we need to create the test loader, and the test loader is going to be data loader, and inside this data loader is going to be dataset. Is going to be this dataset is going to be the test dataset, and then the batch size is going to be the batch size, and the shuffle, we are going to shuffle the data, and we can run this part. Transform should be S. Transforms, oh, it should be without S. Transform. Okay, so we are downloading the data, and we can, wait for the download to complete. But while we waiting, we can create the initialization part. So initialization network. Okay, so in the initialization network, okay, so we finished downloading the data, so we need to initialize the model. So the model is going to be the NN model that we have, and the NN model is going to be the input size, and we are going to have the input size, and then what we need the number of classes, and the number of classes is going to be number of classes, and then we need to use the device. So this is how we can either using the CPU or a GPU, and then we can run this part. After that, let's create the loss and the optimizer. So to create the loss and the optimizer is, so we need to have, let's say criterion as a variable, and we are going to use the cross entropy loss, which is the negative log likelihood loss. Okay, and then the optimizer is going to be optim, and we are going to use Adam optimizations. Adam, and we need to pass the model dot parameters, and the learning rate is going to be so learning rate like this. So the learning rate is going to be the learning rate, which is the value that we have here. Okay, now we can run this part. So let's start to train the network, train networks. And to train the networks, we need to have the for loop for epoch in range of the number of epoch that we have, and for batch underscore idx, and then the data, and then we need to get the target in enumerate train loader. Okay, so we are going to create a data, and it's going to be enumerating all of those data, and then put all of those enumerate into data and the targets. Okay, and then we're going to create the data variable, and it's going to be data dot to, so to device. So we are going to use the device. So the data is going to use the device, whether it's GPU or CPU, and the targets is going to be targets dot to. It is also going to be device is equal to device targets. Okay, now we need to change the data. So data dot reshape of data dot shape in the 0th index is going to be 1. So what happened is, so we are going to have a batch, and then we are going to flatten off the channel, the row and the column. Basically that's what happened, and column. So this part is the batch part, and this part is the flattened part. Okay, so which is the input for the fully connected layer. Okay, now we need to forward, which is the forward propagations, and it's going to be we can just create model and the data, and it's going to be data. So we are going to, you know, have our data inside of this model function that we have here, and this model is going to, you know, passing those data into the NN class that we have here, and we need to record everything because the class of the NN is going to return this x. So we need to catch that x and store it into a variable. So let's call that variable score, and then we need to create the loss, and the criterion is going to be scores, and also the targets. So basically this is the predictions, and then this is the true label basically. So that's what happened here. Okay, and then after we going forward, we need to going backwards. So to go backwards, we need to use the optimizer dot 0 grad. Okay, and then we going backward using the loss backward function. Okay, so that's it for the backward propagations, and then we need to apply the gradient descent. Gradient descent like this, and it's going to be optimizer dot step basically. So this is what happened, which is basically you can say this as the updates. Now we can run this cell, and so this basically they are training our data. Now let's create a function to check the accuracy. Checking, so let's check the accuracy. So we are going to wait until it finished training. Okay, and while we waiting, let's create a function that telling us the accuracy of the networks that we get. Basically that's what happened. So let's create a function called check accuracy. Accuracy, and we are going to input something called loader and model. So let's create a variable called number of correct. So how many correct number of or correct prediction, and let's start with 0, and then the number of samples that we have, so how many data that we have, and it's going to be 0, and then we need to evaluate the model, so we can call the eval function like that to evaluate the model. Okay, now with torch dot no grad is going to be for x and y. In loader we are going to have x is equal to x dot to device is equal to device, okay, and then y is equal to y dot to device is equal to device, and then we are going to have x equal to dot x dot reshape, and then it's going to be x dot shape of 0, and it's going to be 1. So again, this is just the same thing as previous one, which is we are going to have a patch and then the flatten of the input data basically, and then we are going to have the scores. For scores, we are going to create this model and then input the x. I'm going to do this. Now we can get this data, and the prediction is equal to scores dot max of 1, and it's going to be the number of correct prediction. Basically is going to be add if we have a correct prediction based on the predictions is equal to y, okay, dot sum. So what is going on here in this part? So the predictions is coming from value is coming from the neural net, the neural nets that we have already trained here, okay, and if the predictions is equal to the label, which is that's what we want to the predictions from the neural nets the same prediction as the the true label. So you can see this y as y hat in the previous example, but basically this is the predictions. If the prediction is equal to the true label, we are going to adding the number of correct. So if we have the correct number of predictions like 10 times, which is then we have 10 predictions correct, and then we just sums up all of those number. Basically that's what happened. It's coming from NN, and then the number of samples. So we are going to basically of 0, not 0, dot size of 0. So we are going to see how much the predictions that we are doing, how much, not the prediction, how much the NN predicting something, predicting our data, okay, which is it's just how much the data that we are going to pass into the neural networks to predict. And then let's go out from this for loops and let's print and using the f string we got. So how many the number of correct divided by the number of samples with accuracy of, so we are going to create a float data type, and then it's going to be the number of the correct prediction divided by the float value of the samples, number of samples, and then multiply that by 100, and then let's use just the value behind the comma, and then let's add the percentage symbol. And so let's create model.train. Okay, now we can going out from this function and finally check the accuracy, and we are going to pass in the train loader, not the train one, the train loader, and we are going to have the model. Then we can create the check of accuracy from test loader, and going to pass the model. Now let's run this cell and let's see. Okay. Oh, that's a pretty good model. So we get 98% accuracy, and we have, by using the train loader and by using the test loader, we get 97% accuracy basically. So this is how you implement the neural networks using the Pytorch. Okay, now the next part is going to be, so we've been using the MNIST dataset just for the introductions for the introduction for Pytorch. But in the next segment, I'm going to use the RGB image. And so yeah, let's go into the next segment. I would like to introduce you to something called patch normalizations. So patch normalization is basically a normalizations, but it's not in the input part. So it is inside of your hidden layer, and we are using the patch normalizations to fix the internal covariate shift problem. So okay, what is the internal covariate shift problem? So you can imagine you have the input, and this is the first layer, which is the input layer, and this is the first and the second layer, and then this K is basically the hidden layer. So it's going to be inside of your neural networks, right? And the problem is we doesn't know what kind of distributions that's going on inside of those hidden layers. So we can normalize the input layer. So we can normalize the input by in our case, we basically divide our number by 255 in a MNIST dataset. But we cannot do that inside of this what's it called, hidden layer, because we doesn't even know what kind of distributions that's going on here, that's going on inside of this neural networks. We doesn't know what kind of number even, because this is just a random number in the first part of the initializations, right? And so all of this is a learnable value of the W and the bias value. So we doesn't know what kind of distributions that's going on, and the problem becomes if we have, for example, batch normalization like this. Where is it? Where's my I guess, wait, okay, I want to do this. Alright, now if we are using batch gradient descent, not batch but mini batch gradient descent, so we are going to split our input data into a mini batch. So the problem becomes, what if the first batch as an input create this random, for example, just for an example, so it create this kind of random kind of distributions. But when we input a new batch, which is the second batch inside of our neural networks, the distributions is going to change because it's just a new input, it's a new information, so the distribution is going to change. Okay, and then we input the third mini batch, and then the fourth mini batch, so the distribution inside of the hidden layer is always changing. So that is what the eternal covariance shift mean. So there's going to be a shift or a changing distributions, and to fix the internal covariance shift, okay, so I have another example here. So we have this trained data, right? So in the training process, we get this kind of classifications, which is such a good classifications in this training case. But when we are using the input, so you can see this as a training. So the training, we get the perfect kind of distributions, and the result is we get the perfect kind of classifications. But once we change the input, we are going to get a completely different distributions. Hence, we are going to get a completely different classification. So now you can imagine, if we are using this classification in the training process, and then we are using this classification in the test process, we are going to get, yes, you can see like this is the correct kind of classification, but this is not the optimum classification. In fact, for this particular case, in this particular case, the classification should be look like this, right? It should be look like this. It should be look like this, right? Instead of looking like this. Okay, because there's going to be a gap that we don't need. So this is the gap that we are going to remove, right? So there's this gap that we are going to remove that we don't need. So that is why we need to fixing this problem. So we need to fix the internal covariance shift problem, which is, again, it's just the difference of a distributions inside our neural networks, inside our hidden layer in the neural networks. So how can we fix those? Well, we can use something called batch normalizations. And in batch normalizations, you will have this formula. So okay, so the main idea behind the batch normalization is that, okay, if I have a random distributions, why don't I just, you know, make the same kind of distributions, which is I'm just gonna make the distributions become kind of a Gaussian distributions. So okay, if you doesn't know what Gaussian distribution is, it's basically a distributions where you are going to have the mean of 0 and the standard deviations of 1. So that is the idea behind the batch normalizations. And so you can also see the batch normalization paper. So this is the batch normalization paper. It's called Batch Normalization: Accelerating Deep Network Training by Reducing Internal Covariance Shift. So again, we want to reduce the internal covariance shift, which is the changing of a distribution inside of the hidden layer in our neural networks. So this is the formula that they have, that they are okay, I don't know if you can see that. I hope you can see that. Okay, so this is the formula of the batch normalizations. So first of all, we need to find the mean, and then we find the variance, and then we normalize based on the mean and the variance, and then finally we get the Gaussian distributions by doing that. So here I have an example for that. So this is the mean, and this is basically the same formula with this, right? So this is basically the same. So to find the mean, here I have mu as the mean is equal to 1 divided by the amount of images for every patches, and then you just sums up all of those number and divide by the amount of the images that you are going to have, the amount of value, not the value, but just the amount of number that you are to have, and that's how you get the mean, right? And then we need to find the variance, and here the variance is getting the notation of alpha squared, and the alpha squared, or the variance, is going to be 1 divided by the n amount of data, and we are going to sums up a value of the value of the number of the data that we have minus the mean, and then we square those number. So here I have my example. For example, if I have 3, 5, 8, 9, 11, and 24. So this is just a random example, just a random value. So first of all, I want to find the mean of this number. So to find the mean, I'm just gonna sums up all of this number, 3 plus 5 plus 8 plus 9 plus 11 and plus 24. Sums up all of those number and then divide those number by 6, and I will have the 10 as my mean value. Okay, so this is the mean value, and after I get the mean value, I need to find the variance value, and so the variance value is going to be the alpha squared, and it's going to be, so each value instead of this our example, we're going to reduce it by the mean value. So we have 3 minus the mean, which is the 10, and then square those number, which is basically we are going to have in this case we are going to have 49, right? Because we're going to have minus 7 and then square that number, it's going to be 49, plus we have 5. minus the mean, square those number, and then we are going to have 25, right? And then you do the 8 minus 10, square those number, the 9 minus 10, square those number, and then 11 minus 10, square that number, and then finally you have 24 minus the mean, the 10, and then square those number. And then after you get all of those numbers, you sums up all of those numbers and you divide by the amount of number that you have, and it's going to be 6. And the variance that we get from these distributions, from this number, is 46. Okay, so now to make this number becoming a Gaussian distributions, which is a distribution that has the mean of 0 and the standard deviation of 1, we need to apply this normalize. So we currently have the mean of 10, so, and we want the mean to be 0, and we also have the variance. Okay, so the variance and the standard deviation is basically the same thing. So right now we have the variance or the standard deviations of 46, and we want the standard deviation becoming 1, so that we have the Gaussian distributions. So to get the Gaussian distributions, we are going to normalize this value. So the normalize is going to be x hat, okay, and it's going to be every value minus the mean divided by the root of the alpha squared plus the epsilon. And so the epsilon is going to be a really small number, just to prevent we get the root of 0. Okay, so let's do that calculations here. So in the first value, in the first x, we are going to have 3, which is the x of index of 0. So the index of 0 is going to be 3, right? So the index of 0 is going to be 3 minus the mean divided by the standard deviations square plus the epsilon value to prevent the 0 root, and we are going to get minus 1.03. And then we are going to the next index, which is the 5, and so 5 minus the mean divided by the 46 squared plus plus the epsilon value, and then we'll get minus 0.75. Okay, and then next we are going to have the last index. So basically you do this kind of calculations for every value inside of this distributions. And we have, so for the final distribution, which is 5, we are going to have 24 minus the mean divided by, again, the same standard deviation square plus the epsilon value, and then we are going to have 2.06. And then we are going to use all of those numbers. So so we are going to change this number, these distributions with okay, I'm going to do this. So okay, all right, now so we are going to replace, so this minus 1.03 is going to be replacing the 3 number here, and then the minus 0.75 is going to be replacing the 5 number here. going to be here. So we are going to replace all this number into this number. Okay, and this of course the 24 is getting replaced by 2.06. So we replace all this number to be this number, okay, based on these calculations. And if you trying to find the mean of these distributions, it's going to be 0, and the standard deviations, which is this variance, and apply the calculations for these distributions, you are going to get one value, which is something that we want. We want the Gaussian distributions, something that has the mean of 0 and the standard deviation of 1, which is the exact thing that we want here. Okay, now let's say we are successfully normalize the distributions inside of a hidden layer, inside of our hidden layer, with these Gaussian distributions. Okay, but there's one big of a problem with this kind of a technique, or with this formula, and that is, okay, so let me just show you. So of course, when we are applying neural networks, we need to apply the nonlinearity activation functions, right? So for example, here I have the sigmoid function. So the sigmoid nonlinearity function is going to look like this. But here's the problem. If we have the Gaussian kind of distributions and we apply the nonlinearity of a sigmoid, for example, we are going to get just kind of a linear function, because the distributions makes the nonlinearity in the sigmoid function become useless. So basically the distributions make the nonlinear function become useless. So okay, I'm going to draw it for you if you're not understand what do I mean by that. So this is what I mean, right? Okay, so this is the sigmoid nonlinearity, right? And this is the Gaussian distributions. Now if we apply the Gaussian distributions in and find the nonlinearity, it's going to be look like this. It's going to be look like this, right? So now the problem become the nonlinearity is going to be a linear. So the nonlinearity inside of this Gaussian distribution is going to be linear. Hence the nonlinearity function becomes useless, because we need the nonlinearity. But when we cannot find the nonlinearity inside our distributions, it just becomes useless, because okay, in this case of the sigmoid, the nonlinearity is coming from here, right? So okay, this will become nonlinear, and this is where we become nonlinear. But since we are not inputting our distribution number into this part, we are just getting kind of a linear value, a linear function. Okay, so there is a problem. So basically the distributions, the Gaussian distributions, makes the nonlinear function become useless, because it's just going to be a linear function anyway. So how can we solve this problem? Well, we are going to perform something called scale and shift, and scale and shift is actually in the Batch-Normalization paper. It is also here. So this is so this is the scale and shift, and basically what the scale and shift doing is that, let's say I have a Gaussian distributions, but I want to apply a nonlinearity inside of my Gaussian distributions. So we need to make it bigger or smaller. So you can imagine like this. We don't want the Gaussian distributions become too small, because it would make the nonlinearity becomes linear. But we also doesn't want the Gaussian distributions become too big, because it will saturate the value of the sigmoid function, right? So we doesn't want these distributions become too small or too big. So that's why we need the scale and shift. And by performing scale and shifting, we basically, again, just like its name, we scale, which is we make it bigger or smaller, and we're shifting, so which is we are either making it going to the left or going to the right. So here I have my Gaussian distributions. Okay, so this is the Gaussian distributions, and if I performing the scale and shifting, it would look like it's going to be look like this, or it's going to be look like this, or maybe it's going to be look like something like this. It doesn't matter, because if you see the scale and shifting, it is going to be a learnable parameters. Okay, it's going to be learnable parameters. So the distributions that we get from scale and shifting is going to be based on the performing of the neural networks. So it's going to be match our data, and that's what we want. That's what we want here. So it's not going to be a Gaussian distributions, but it's going to be our own distributions, and this distribution is going to be based on the input and the output, because the scale and shift is going to be a learnable parameters. So it's going to learn just like the W and the bias value inside of a regular neural networks, right? So we are going to it's going to be, so in the first iteration, of course, it's going to be kind of a random, but the more we train, the more these distributions becomes like its own distributions, and and this kind of distribution is going to become the main distribution in that hidden layer. And so so you can also imagine something like, so in each hidden layer is going to have its own distributions, which is based on the input and the backdrop, which is based from the gradient descent process. Okay, and you can imagine like this is so this part has its own distribution, this part has its own distribution, and maybe this part has its own distributions, but it's going to be the distributions that match with our data. So that is what batch normalization is. So I hope you understand. Now if you're not understand, I feel like it's pretty fine. If you not understand the theory, we are going to get the programming part, and I hope you understand about batch normalization in the programming part. So remember when I said in the batch normalizations, there's going to be the learnable parameters that are going to learn throughout the process of a gradient descent in the neural networks. So of course, those learnable parameters needs to be going through the process of backpropagations, right? So, and as we know, in order to get the, in order to to do the backpropagations, we need to know the derivative of the loss for each variable that are learnable variable. So, for example, here in the paper of the batch normalizations, this is the formula for the derivative of each learnable parameters. So let's go through each one of these. Now, in the case of the derivative of the loss with respect of the x hat, which is how much the x hat affecting the value of the loss, is equal to the derivative of the loss with respect to the yi, which is the label, multiplied by the gamma. So, and then we have the derivative of the loss with respect of the alpha squared is equal to the sum of the derivative of the loss with respect of x hat multiplied by the x of I minus the mu which is the standard deviations multiplied by the -1 divided by 2 multiplied by alpha squared plus epsilon to the power of -3 divided by 2. And then we have the derivative of the loss with respect of the mu p. So this is basically the mean, like how much the mean affecting the loss, is equal to the sum of the derivative of the loss with respect of the x hat multiplied by the -1 divided by the root of the alpha squared plus epsilon. And then you add those numbers with the derivative of the loss with respect of the alpha squared times the sum of the -2 multiplied by the x of I minus mu divided by the m, which is m in this case is the amount of data. And then we have the derivative of the loss with respect of the x of I, which is just the input, right, is equal to the derivative of the loss with respect of the x of hat multiplied by 1 divided by the root of alpha squared plus epsilon plus the derivative of the loss with respect of the alpha squared times 2 multiplied by the x of I minus the mu divided by the m amount of data plus the derivative of the L with respect of the mean multiplied by 1 divided by the amount of data m. And then we also have the derivative of the loss with respect of the gamma, and it's going to be the sum of the derivative of the loss divided by the y multiplied by the x of hat of I. And then finally we have the derivative of the loss with respect of the beta value is equal to the sum of the derivative of the loss with respect of the yi. Now, if you are wondering how can they get this derivative formula based on where is it? Based on this formula, here I have the breakdown of the batch normalizations backpropagations basically. So now here I have the batch normalization computation graph. So here I have the x2 and x1 as an input, and this x2 and x1 is going to the mu, and it is also going to the x of 2 hat and then the x of hat of 1. Now we know that the mu value is the mean value, and then this mean value will going through the x of hat, and also is going through the x of hat of 1, and this is also going through the standard deviations. So if you remember, so where is it? If you remember in our formula, okay, so we have the input, and so we have the input, right? And the input is going, so this is the x of I, which is stands for the x of, is either the index, x of index, right? So the x of I is going to be the x of 1, x of 2, x of 3, etc., etc., so on. And so the x of I is going through the mean, so you need to find the mean of the x of I, and that's why in the x of 2 and the x of 1 you are going to get the mean. First you get the mean, right? And then after you get the mean, you need to find the variance. So the variance is going to be the alpha squared. So after you get the mean here, you're going through the alpha squared here, which is the variance. After you get the variance, you can get the normalized version, which is the Gaussian distributions. And the Gaussian distribution is going to be the x of hat. So we have the x of hat here and the x of hat here. Now after we get the x of hat, we actually get a new value. So before we have this kind of input value, right? This so this is the previous example. So this is the input value, but after we normalize and create the Gaussian distribution out of it, we get this kind of value, this input kind of value, replacing this value, and this is basically becomes the new input, and this is why the x of hat is connected to the input value. Okay, and then of course after that you get the output, right? And then the output is basically the Gaussian distributions. But since we are having the trouble with the nonlinear activations, we need to apply something called scale and shifting, and the scale and shifting is controlled by the value of the beta and the gamma. So this is basically what happened. So that's basically what happened in the batch normalization's computation graph. Now if we look at this computation graph, we need to find, so this is everything that we need to find. So you can imagine like this y2 and the y of 1 is basically the output, right? So we need to find everything that is going to affect the output value. So you can call this part, you can imagine like this part is basically the loss value. Okay, so the derivative, so we need to find how much the output, which is the derivative of the loss, got affected by the x of hat, which is here. So how much this got affected by this too, which is the x of hat. Okay, And in order to find how much, not in order to, and then we're going back again. So this x of hat, we're going back here, and then we found the alpha squared. So we need to find how much the loss got affected by the alpha squared. So we basically going from the output and going back to the input, right? And then after we found how much the loss got affected by the alpha hat, we need to find how much the loss got affected by the mu, which is the mean. How much? So this is going to be how much the derivative of the loss with respect of the mu. And then we need to finally, after we going here, we need to find how much the loss got affected by the input itself. So how much the derivative of the loss with respect of the input, or the input of I. So it's going to be every input, right? And then after we going back from here and then here and then here and then here, or we can go here and then here and then here and then here, and then finally go here, we need to find how much this output also got affected by the gamma value. So it's going to be how much the derivative of the loss with respect of the gamma. And then finally we need to find how much this output got affected by the beta value. And this is how you wrote it. We need to find how much the derivative of the loss with respect of the gamma. Okay, so we're going to go through this formula one by one. We are going to, basically going back in a computation graph for the batch in order for us to write the batch normalization, the batch normalizations. So first of all, we need to find this. So basically we need to find all of these equations or formula, right? The formula for the derivative. So first of all, let's go to how much this beta affecting the value of the loss, which is this part, right? So first, this is what we are going to do. The derivative of the loss with respect of the beta is going to be the derivative of the loss with respect of the y1 times multiplied by the derivative of the y1 divided by with respect of the beta itself, plus the derivative of the loss of the y2 multiplied by the derivative of the y2 with respect of the beta. So if you remember the chain rule, in order to find how much this loss with respect of the beta, we need to go to the how much the loss got affected by the output. Okay, how much the loss got affected by the output, and then finally how much the output got affected by the loss. So this is basically what we are doing. How much the output got affected by how much the loss got affected by the output, and then how much the output got affected by the beta. So this is for the first output, which is the y of I, not y of I, but the y of 1, plus how much the loss got affected by the second output, which is y2, multiplied by the how much the output of the y2 got affected by the beta value. Okay, so remember your chain rule. Now we know how much this value is. We know how much the loss with respect of the output of 1, and then how much the loss with respect of the y2. Okay, so we knew this value, which is 1. Now we need to find not 1, but it's just whatever value is, right? Whatever value this y2 and y1 get, right? Okay, now we know these two value. Okay, we know these two value. Now we need to find how much this value and how much this value. So in order to find the derivative of the y of 1 with respect of the beta, we need to find, okay, what is y1? y1 is the gamma multiplied by the x of hat plus the beta. So we are applying what's it called? Shit, I forgot. So we need to apply the partial derivative of this value with respect of the gamma. Okay, so the partial derivative of this is basically the derivative of the y with respect of the beta is going to be 1, and the derivative of the y2 with respect of the beta is going to be 1. Okay, and oh yeah, since the y1 and the y2 is basically the same, so it's just basically the same value, right? So you apply partial derivative and then you get this value for each of the output, right? Now, okay, basically since the y1 is basically the same with the y2, so that the answer for this partial derivative is 1. Hence, the answer for the partial derivative of in the case of the y2 is basically the same answer with the y1. And then we get the derivative of the loss with respect of the beta is equal to the derivative of the loss with respect to the y1. So we know this value, multiply by this value, which is this partial derivative value, which is 1, plus the derivative of the loss with respect of the y2 multiply by the partial derivative of the y2 with respect of the beta, and it's going to be 1. And so it just basically the answer is the derivative of the loss with respect of the y1 plus the derivative of the loss with respect of the y2. So if you write the formula is going to be the derivative of the loss with respect of beta is going to be the sum of the I is going to be the derivative of the loss with respect of the y of I. So for example, if you have the output of, like, for example 5, so it's going to be y1, y2, y3, y4 and y5, the answer is going to be the sum of the value of the derivative with respect of each index of those 5 values, which is going to be, if you have 5, y is going or the 5 input output is going to be the derivative of the loss with respect of the y1 plus the derivative of the loss with respect of y2, and then the derivative of the loss with respect to y3, etc., until you get to 5, until you get this n value. Okay, so in this case the n value is going to be 2 because we have 2 output. Okay, so this is the formula for the derivative of the loss with respect of the beta. So we found this one, so we found this formula for this, the formula for this, right? And then let's go to find the other value. Now the next one we need to find is the derivative of the loss with respect of the gamma. Okay, so the derivative of the loss with respect of the gamma is going to be the chain rule effect again. So it's going to be the derivative of the loss with respect of the y1, which is the output, and the derivative, and then so you need to go do the output first, and then you get you need to find how much the loss got affected by the output, and then you get how much the output got affected by the gamma, and this is the chain rule. So the derivative of the loss with respect of the y1, which is the output of 1, multiplied by the derivative of the loss of the y1, which is the output 1, divided with respect of the gamma, plus the derivative of the loss with respect of the y2 multiplied by the derivative of the y2 divided by the gamma. Now again, we know this value, so we know how much this value is going to be. We need to find how much this value, how much the derivative of the y1, so how much y1 got affected by the gamma. Okay, and we also need to find how much the y2 got affected by the gamma value. So first we need to find how much the y1 got affected by the gamma value. And what is y1? Well, y1, which is the output, is basically the beta times the x of hat plus not the beta, but the gamma times the x of hat plus the beta value, and then you find the partial derivative with respect of the gamma. Okay, and then you get, and then you get the partial derivative, and it's going to be the x of hat. Okay, so the partial derivative of this formula is going to be the x of hat. Now this is for the y1, and similarly with the y2, because this is like the similar path and the similar formula, the y2 is going to be also the x of hat. Now okay, so we found the value of this, which is the x of hat 1, and this value is the x of hat 2. So we need to change the formula to become like this. So the derivative of the loss with respect of the gamma will going to be, so we know this value, just move it here, and then it's going to be the derivative of the loss with respect of the y1 multiplied by this value, the partial derivative answer, which is the x of the hat 1 plus the derivative of the loss with respect of the y hat multiply the x of hat of 2. So based on this formula, we can define the entire formula is going to be the derivative of the loss with respect of the gamma is the sum of the how much your output going to be, and that is n, of how much the derivative of the loss with respect of the output that you have multiplied by the x of hat that you have. Okay, so if you see, like, this is the y1 is going to be the x hat of 1, and this is the y2 is going to be x hat of 2. So you can so this is why in this formula is the y hat is going to be I and the x of hat is going to be I, because it's follow the same value. Okay, now we found how much gamma affecting the value of the loss. Next, we need to find how much the derivative of the loss, how much the loss got affected by the x of hat, and how x of hat and of 1, and how much the derivative of the loss got affected by the x hat of 2. Okay, so if you forgot, the x of hat is basically the value of the Gaussian distributions after we pass on the input. Okay, so in order to find this value, let's derive the value. So we need to write the derivative of the loss with respect of the x hat of 1 is going to be the derivative of the loss with respect of the y1, apply the chain rule, multiply by the derivative of the y1 with respect of the x of 1. So this is the chain rule, and then it's going to be the derivative of the loss with respect to the y of 1 multiplied by the partial derivative of the y1. So what is y1? y1 is the gamma multiplied by the x of 1 hat plus the beta, and then you find the partial derivative of this value with the x of 1 hat, and then get the partial derivative value, and it's going to be gamma. So the partial derivative value of this formula is gamma. So the formula become the derivative of the loss with respect of the x of hat 1 is going to be the derivative of the loss with respect of the y1 multiplied by the partial derivative of this, which is the gamma. And similarly with the x of hat 2, we also have the same step of the for the formula. So you can write the derivative of the loss with respect of the x hat of I is going to be equal to the derivative of the loss with respect of the y1 multiplied by the gamma value. Okay, so this is how much the x of hat affecting the value of the loss. Okay, next we need to find how much the derivative of the loss, how much the loss got affected by the alpha squared. Okay, now apply the chain rule. Okay, I'm probably going to show you this because this is quite a lot. Okay. Okay, so apply the chain rule. So we need to go from the y. Okay, so what do we need to find? We need to find the derivative of the loss with respect of the alpha squared. So how can we do that? First, we need to go. So this is the loss, right? You're going back, and then you get the x hat. You get the x hat, and then you finally get to the alpha squared. So we need to find how much the loss got affected by the x of hat, and we know the value. We know how much this value because we already found it, which is so we've already found the value of that, and that is this one, the one that we've already calculated, which is the number 3, right? So this is, so we have found the value of the loss got, how much the loss got affected by the x of hat. Okay, we've already know the answer. Now we need to find how much the x of hat got affected by the alpha squared. Okay, how much the x of hat got affected by the alpha squared. Now I'm going to do this. Okay, now let's derive. So first of all, we need to find the derivative of the x hat with respect of the alpha squared, and it's going to be, okay, what is the x of hat? Well, the x of hat is basically, oh my god, what is the x of hat? X of hat is this one, so we need to apply this one in this one. So What is f hat? Oh my god. So we need to find the partial derivative between this formula, which is the x of I minus the mu divided by the root of the alpha squared plus the epsilon value, which is this one. Okay, so this is the x hat, and this is the x hat. You just to find, just to change the formula. So the partial derivative value is going to be the x of I minus of the mu multiplied by the 1 by the negative 1 divided by the square root of the alpha squared plus epsilon times the partial derivative of the alpha squared plus the epsilon with respect of the alpha squared, and then you are going to get negative multiplied by the x of I minus mu divided by the alpha squared plus the epsilon multiplied by the 1 divided by 2 multiplied by the root of the alpha squared plus the epsilon, and then you multiply with the partial derivative between alpha squared plus epsilon with respect of the alpha squared. Okay, and then you working out on these calculations, you get negative 1 and a half, not 1 and a half, negative 1 divided by the 2 multiplied by the x of 1 negative minus the mu divided by the alpha squared plus the epsilon, and then you multiply the value with this value and this value, and you are going to get 1 divided by the alpha squared plus epsilon with the power of 1 divided by 2. Okay, and then you are going to get the negative value of the 1 divided by 2 multiplied by the x of I, but x of 1 minus the mu times the x, but the 1 divided by the alpha squared plus the epsilon to the power of 3 divided by 2 to the power of, yeah. Okay. Okay, now continue with the, okay, I don't know if is it better? I hope it's better. Okay, now continue. We get the negative 1 divided by the 2 multiplied by the x of y minus mu times, so you move up and then it makes the power becomes negative, and then you continue the calculations and you will get the derivative. Oh no, you stop the calculation there actually. So okay, you stop here. So this is the derivative of the x of 1 hat with respect of the alpha squared. And now of course you do the same thing with the x2 hat, and then you get the same kind of result. Now oh my god. Okay, now the formula is going to be, okay, you basically just change this one with this one, right? So you will get the derivative of the loss with respect of the alpha squared is going to be the derivative of the loss with respect of the x hat of 1 multiplied by the negative value of 1 divided by 2 multiplied by the x of 1 minus mu multiplied by the alpha squared plus the epsilon to the power of negative 3 divided by 2, and then plus, so this part, okay, this part is this part, right? And then and this part is this part, which is the derivative of the loss with respect of the x hat 2 multiplied by the negative value of 1 divided by 2 multiplied by the x of 2 minus mu, and then multiply with the alpha squared plus the epsilon to the power of negative 3 divided by 2. And then so how much the loss value got affected by the alpha squared is going to be the sum of the n amount of your x hat is the sum of the amount of x hat with the derivative of the loss with respect of each of your x hat multiplied by the negative 1 divided by 2 multiplied by the x of I minus the mu multiplied by the alpha squared plus the epsilon to the power of negative 3 divided by 2. Okay, so this is the formula basically. So this is the formula. I forgot to make a rectangle. So this is the formula for the derivative of the loss with respect of the alpha squared, or how much the alpha squared where is it? Oh my god. How much the alpha squared affecting the value of the loss. Okay. Now we are again need to go back. So after we found how much the alpha squared affecting the value of the loss, going back again, we need to know how much the loss got affected by the value of mu, which is the mean value. Okay. Oh my god. And to find that, we need to apply the chain rule. Okay, we need to apply the chain rule. And okay, so we need to know how much the derivative of the loss with respect of the x hat multiplied by the derivative of the x of hat with respect of the mu plus the derivative of the loss with respect of the x hat 2 multiplied by the derivative of the x hat 2 with respect of the mu plus the derivative of the loss with respect of the alpha squared multiplied by how much the alpha squared got affected by the mu. So again, we know this value. So this 1, 2, 3 value, we know how much. That's it. Not that we know how much, but we know the value. And the value is going to be, so this is the value for the loss with respect of the x of hat, so which is this one and this one, right? And then the value of this is this one, which is we already found the formula. So we need to find how much the x of hat got affected by the mu. Now let's find it. So okay, so let's find how much the x of hat got affected by the mu. So the derivative of the x of hat with respect of the mu is going to be the partial derivative of the x of hat with respect of the mu. And what is the x of hat? well, this is the x of hat, right? The x of I minus the mu right here, so divided by the root of gamma squared plus the epsilon, and then you apply the partial derivative and you get 1 divided by the root of the alpha squared plus epsilon plus negative 1. So this is the partial derivative value. Now so this is the partial derivative of the x of 1. And then you just multiply this with this, and then you get negative 1 divided by the root of alpha squared plus the epsilon value. And similarly with the x hat of 2, which is going the same kind of calculations, you are going to get negative 1 divided by the root of the alpha squared plus the epsilon. Okay. Now we need to find how much the derivative of the loss with respect of the x hat, which is, we know the answer already, we already done the formula, times, so this formula is going to this here, and this formula is going to this here, which is basically this formula, and this is the formula, and but this formula is this formula, okay, and this formula is this formula, and this formula is this formula. So basically this that's what happened here. So that's what happened here. We basically just move the formula. It's going to be the derivative of the loss with respect of the x of hat of 1 multiplied by the negative 1 value divided by the root value of the alpha squared plus the epsilon plus the derivative of the loss with respect of the x hat of 2 multiplied by the negative value of the root alpha squared plus the epsilon. Okay, so the formula is become the sum between the n, and n is the amount of the data, the amount of index that you are going to have, of the derivative of the loss with respect of x of I multiplied by the negative 1 divided by the root of the alpha squared plus the epsilon. So you just remove the 1 and 2 and then change it with I basically. Okay, so we found this part. This part. We found this part. Okay, we found this part. Now we need to find this part. So in this two part, we already found this part. Now we need to find this part. Okay, we need to find this value of how much alpha squared got affected by the mu. So here is the calculation. So how much the alpha squared got affected by the mu, and it's going to be the partial derivative between, so what is the alpha squared? So this is the alpha squared. So it's basically x of I, not x of I, but x of 1 minus the mu squared plus the x of 2 minus the mu squared divided by the n amount. So this is just the find the variance. So we already done the calculation here, which is basically just so here it just so this value minus this value, square those value, and then plus this value minus this value, square those value, and then sums up all of this number, and then you divide by the amount of the value that you have. So this is what happened here. But in this case, in our case, the input only have 2, so we divided by the 2 amount, right? So that's what happened here. Now you need to find the partial derivative of this value. Okay, Oh yeah, so this value is basically just this value, right? So this value is 1 of n multiplied by the sum of the x of I minus the mu squared. So this is the variance, which is the alpha squared. Now find the partial derivative, and the partial derivative of this value is the 1 divided by the amount of data multiplied by the sum of the derivative of the partial derivative of the x of I minus the mu squared with respect of the mu. Okay, so what is the partial derivative of this? So the partial derivative of this is going to be this. So the formula become 1 divided by the n multiplied by the sum of the 2 multiplied by the x of I minus the mu multiplied by the partial derivative of the x of I minus the mu with respect of the mu. Now let's continue with the calculations. So now the calculation is going to be 1 divided by the n multiplied by the sum of 2 multiplied by the x of I minus the mu multiplied by the negative 1. Okay, so the equations becomes, so you just multiply this 2 with this negative 1, and then you get this, which is 1 divided by the n multiplied by the sum of the negative 2 multiplied by the x of I negative minus the mu value. Okay, and the mu value is basically the mean value. Okay, so this we finally found this for where is it? For for this part, right? So you just combine all of them together and you get the derivative of the loss with respect of the mu is going to be the sum of the derivative of the loss with respect of the x of hat of I multiplied by the negative value divided by the root of the alpha squared plus the epsilon plus the derivative of the loss with respect of the alpha squared multiplied by the 1 divided by the n multiplied by the sum of the negative 2 multiplied by the x of I minus the mu. So this is how much mu affecting the value of loss, which is this one. So we finish finding this one, finding this one. Now let's go and finally, oh my god, okay, I made a mistake. Okay. Okay, now we find this one. So how much this one got affected by the loss value, right? Now we need to go back one more time, and that is how much the input affecting the value of the loss, which is how much, oh my god, which is how much the loss, oh my god, which is how much the loss got affected by the value of the input, of each input, which is the derivative of the loss with respect of the x of I and 2 and the x of y of 1 and x of I, not x of I but x of 2. Now you need to apply the chain rule to get so first of all, let's find how much the derivative of the loss with respect of the x of 1, which is how much the x of 1 affecting the value of the loss. Apply the chain rule, which is going back, like, right? So to going back, you need to know how much the loss got affected by the x of hat here, which is here, x of hat, and then you are going to get how much the x of hat got affected by the x, oh my god, how much the x of hat got affected by the x. And then you will need to find how much the loss got affected by the alpha squared here. And then finally you need to know how much the alpha squared the x or the input got affected by the alpha squared, plus you need to know how much the loss of the mu multiplied by the how much the mu got affected by the input, so which is this one and then this one. Okay, so you just need to go back. Now we know this value, so we need to sub this value from where is it, x of hat. So we know this value from here, so this value is this, okay, which is we found the answer already, and we know this value, and this value is this value. Okay, we know the value of this, and then we also know the value of this, which is this, right, the derivative of the loss with respect of the mu. We know and basically this is the answer. Okay, so we know 1, 2, and 3. Okay, so the value that we doesn't know right now is this 3 value, which is the value of how much the input affecting the value of the x of hat, how much the input affecting the value of the alpha squared, and how much the input affecting the value of the mu. Okay, so we need to find those value, those formula. So first of all, we need to find this one. Okay, so this one is going to be the derivative of the x of hat of 1 divided by the with respect of the x of 1, and it's going to be, so you apply the partial derivative. So what is the x of hat? The x of hat is, again, the x of hat is this. So we need to find the partial derivative between x of 1 minus the mu divided by the root value of the alpha squared plus the epsilon with respect of the x of 1. Okay, so do the partial derivative, and then you get 1 divided by the root of alpha squared plus the epsilon multiplied by the partial derivative of the x of x of 1 minus the mu with respect of the x of 1. So you apply the partial derivative, and then you for this, and then you get 1 divided by the root of alpha squared plus the epsilon plus the partial derivative value of this is going to be 1. Okay, now so you just multiply this with 1, which is basically just you can remove the 1, and the formula is just going to be the derivative of the x of hat with respect of the x is going to be 1 divided by the root of the alpha squared plus the epsilon. So okay, so we found oh my god, so we found this one, which is this one. Okay, so this one. Now let's find how much the alpha squared got affected by the x. Now, how much the alpha squared got affected by the x? So we need to perform the partial derivative. So what is the alpha squared? This is the alpha squared. This is the alpha squared, which is the x of I minus the mu squared plus the x of 2 minus the mu squared divided by the n amount, and in this case we have 2 amounts. Okay, and then perform the partial derivative, and then you get 1 divided by 2 multiplied by the partial derivative of the x of 1 minus the mu squared, and then you square the value with respect of the x of 1, and then you get 1 divided by 2, and then apply the partial derivative, and then you will get 2 multiplied by the x of 1 minus mu multiplied by the partial derivative of the x of 1 minus the mu with respect of the x of 1, and then you apply the partial derivative of this, and the partial derivative of this is become 1. Okay, so this is the 1 value. So the formula become 1 divided by 2 multiplied by 2 times x of 1 minus the mu multiplied by 1, because the value of the partial derivative of this is 1. Okay, now let's go. Okay, so the derivative of the alpha squared with respect of the x of 1 is becoming 1 divided by 2. Okay, so again 2 is the n amount of the data that you have. Okay, n amount multiplied by 2 times the x of I minus the mu, and then you are going to have the derivative of the alpha squared divided by the x of 1 is going to be 2 multiplied by the x of I minus the mu divided by the n amount. Okay, so I'm just this should be 2 because, but since this is the, technically the n amount, so I'm just replace the 2 with the n. So we basically just divide this, just doing division between this and this, right? And this is why, and technically this is the n amount, and that's why I'm using this n right here. Now we are going to get, okay, so this is the formula that we found. So we found, where is it? Okay, now we found this one, right? So this one is this one. Okay, now finally we need to find this one, which is the derivative of the mu with respect of the x of 1. Okay, so what is so how much the mu got affected by the x of 1? So it's going to be the partial derivative of the mu. So what is the mu? The mu is just the mean, right? So you apply the partial derivative between the mean with respect of the x of 1, and you will get 1 divided by 2 multiplied by 1. Okay, and since this 2 is the n amount, so you can also write it as 1 divided by n. Okay, so finally where is it? Okay, we found all of this value. So the derivative of the loss with respect of the x of hat of I multiplied by 1 divided by, which is here, we found it. Okay, 1 divided by the root of the alpha squared plus the epsilon plus the derivative of the loss with respect of the alpha squared, and the derivative of the loss with respect of the alpha squared is this one, right, multiply by where is it, by the derivative of the alpha squared divided by the x of 1, and that is going to be here, right? So we found the answer here, which is 2 multiplied by the x of I minus the mu divided by the amount of n amount of data plus the derivative of the mu. So the derivative of the mu is basically this really long formula here, multiply by the derivative by this, right, which is this one that we already found, multiplied by 1 divided by the n amount of data. Okay, so that is the derivative of the batch normalization. So we found all of this formula, which is all of this formula, right? And if you compare all of this formula with the formula in the paper, they are basically the same. So you can find all of this formula throughout. You can find all of this formula by doing all of this, right? By doing all of this, which is that's why we get the same formula. Okay, you just derive the formula for the batch normalizations. And yes, that is the backpropagations for the batch normalization. Now, if you don't understand everything, it is completely fine. If you don't understand anything, don't worry about it, because all of this is happening behind the scene. Okay, all of this is happening behind the scene, so you don't need to worry about it. Okay, in order to apply the batch normalizations in neural networks, we need something called exponentially moving average. So exponentially moving average is something that they call in statistics, but in a machine learning they sometimes call it weighted moving average. So what is this exponentially moving average is? So for example, I have this kind of data, and let's say I have day and the temperature of theta. Okay, so this is the temperature and this is the day. So I have this kind of data distributions. Okay, so in the first theta, I'm going to have 4 degrees Celsius. So it basically, in the first day, I would have 4 degrees Celsius. In the second day, I would have 9 degrees Celsius. In the third day, or in the theta 3, I would have 5 degrees Celsius. And then I would have, in the theta 180, I would have 15 degrees Celsius until the n amount of data. So this has n amount of data. Okay, now for the formula of the exponentially moving average itself is going to be Vt equal to beta times Vt minus 1 plus 1 minus beta times q theta, not the times theta t. Okay, so okay, this beta value is like a parameters. Okay, so we can change this value, right? So for example, let's try to calculate. Now let's try to calculate the v of 0. And so since we only have the data from the first day, which means we don't have the data in the 0th day, so it's going to be 0 anyway. Now in the v1, we are going to have, so take the example of the beta value for and it's going to be 0.9 multiplied by the Vt minus 1. So what is the current Vt? So the current Vt that we have is V1. So 1 minus 1 is going to be 0. So we are going to have V0 plus 1 minus the beta value. The beta value that we have is 0.9. So it's going to be 0.1 times theta t. So what is the current t? The current t is 1. And then we move into the V2. So the V2 is going to be, again, using the beta value of 0.9 multiplied by the Vt minus 1. So the current Vt is 2, and 2 minus 1 is going to be 1. So we are going to have V1 plus 1 minus beta is going to be 1 minus 0.9, and we get 0.1 multiplied by the theta t. So the theta t is going to be 2. So the t value is 2, so we have theta t, theta 2. Okay, and then we move on into V3 is equal to, again, 0.9 Vt minus 1 is going to be, so the current Vt is V3, so minus 1 is going to be V2 plus 1 minus beta, and the current beta is 0.9, so we have 0.1 multiplied by the theta of 3 for the current t. Okay, and you can do this into all of your data until your n amount of data. So the formula, if we have the beta value of 0.9, is going to be Vt equal to 0.9 multiplied by the Vt minus 1 plus 0.1 multiplied by the Qt, not but theta t. Okay, now if I have my beta t as 0.9 and this is my data distributions, I would have something of a function that look like this. Okay, and also it turns out when you are compute the Vt equal to beta times Vt minus 1 plus 1 minus beta times Qt, you will also get some kind of a Vt, and it's approximately 1 minus, not 1, but 1 over 1 minus beta value. Okay, so in our example, when we have 0.9 as a beta value and then apply this formula, we get 10 value, and 10 value is going to be like a representative of, so we are going to take the average between each 10 days across all of our data. So we have n amount of data. Okay, we have n amount of data, and on each 10 data we are going to take the average, and this is why the oscillation, if we have the beta value of 0.9, it's going to look like this. Okay, now if we have the beta value like close to 1, so I would have the beta value of 0.98, and then apply this formula here, I would have 1 divided by 1 minus 0.19, and it turns out we get 50. So we are going to have this kind of oscillations or this kind of functions, because we are taking the average for each 50 days of each 50 data across the n amount of data that we have. Now if I have the beta value of 0.5 and then apply this formula, I would have around 2 data or 2 days, and this is why the oscillations getting more noisy, because I'm taking the average of each 2 data across all of my data, n amount of data. Okay, now remember when I said we need the exponentially moving average to perform the batch normalizations? So here's how we do that. Here's how we apply the exponentially moving average in batch normalizations. So in batch normalizations, we need to calculate the mean and the variance, right? So in order to do that, first we need to run the entire training dataset once. Okay, we train the dataset once and then calculate the mean and the variance at each neuron and save them. So remember, each of the neuron, they have the W value, the weight and the bias value. So we are going to calculate the mean and the variance of all of those W values on each neurons and save those values. And then we calculate the average moving, we calculate the exponentially moving average of mean and the variance across all of the neurons that we have during the training, and then save the last value after the training. Okay, so in order to do these steps, here's how you do it. We are going to make a parameter, not a parameter, but a variable, something called moving mean and moving variance, and this I'm calling it moving mean and moving var. So in moving mean, we are going to apply the formula for the exponentially moving average. So it's going to be moving mean multiplied by the momentum plus the batch mean times 1 minus the momentum. Okay, and then in the moving variance, we are going to have, okay, so this should supposed to be not moving batch but moving mean, so I made a mistake here. So it's going to be moving variance. Okay, so it's supposed to be moving variance. It's going to be moving variance times the momentum plus the batch variance multiplied by 1 minus the momentum. So we are just applying the exponentially moving average formula into the batch normalizations. Okay, so that is the exponentially moving average in batch normalization. So let's apply this in program. Okay, we are in the Google Colab, and let's call this batch normalizations. Why not? Okay, so let's just start it. Let's import some dependencies. Import some dependencies. Okay, and it's going to be import.torch.nn.functional sf. We are going to need that. We are going to import torch.nn as nn. We are going to import torch.optim as optim. We are going to not import, but from torch.distributions import uniform. Okay, now let's import seaborn as SNS, and let's import matplotlib to visualize the data.pyplot as plt. Okay, let's run this. So okay, first of all, I want to create, okay, why is it so long? So let's define, so let's create a functions of custom batch what is it, torch functional. Okay, so let's create a function called custom batch norm, and we are going to have nn.module, and it's going to be define init of self in, and we're going to need in size, we are going to need the momentum, and let's give this momentum a default value of 0.9, and then we are going to need the epsilon value of 1 of e minus 5. Okay, so it's going to be super custom batch norm self, and then init. Okay, so we are okay, what is it now? Let's write self dot momentum. It's going to be the momentum, and then self dot in size, it's going to be in size. Okay, and self dot epsilon is going to be epsilon. Okay, now let's create a variable for the distributions. Let's call that u for the, that stands for uniform dot uniform. So okay, I want to create something called a uniform distribution. So okay, remember when I said something like we are going to, you know, make the distributions inside of the hidden layer to become the quotient kind of distributions, and I'm going to use the uniform as an like a example. So if you doesn't know what uniform is, okay, let me visualize. Okay, so let me visualize what uniform look like. So I'm going to import torch here. Okay, the visualization of uniform distributions. Okay, so import torch. So I'm going to create a variable called distributions, and it's going to be uniform dot uniform, which is something that we are going to use here, and we are going to give this value the low value of 0.0 and the high value of 0.1. Why not? And the samples, I'm going to have a variable called samples, and the samples is going to be the distribution that we have, and sample of, I'm going to get 1000 data. Okay, 1000 data that has 0.0 and 0.1 as the low and high value. Okay, now I want to visualize this. So it's going to be plt dot figure of the, so it's going to be the fixed size of let's say 0.6, and the SNS dot history is going to be samples dot numpy. So change this distributions into numpy array, and let's say the pins is 30, the KD is going to false, and the color is going to be blue. Okay, so let's add title and labels. So it's going to be plt dot title, and it's going to be uniform distributions. Oh my god, uniform distributions from 0 to 1, and the font size is let's say 16. Now the plt dot the x label is going to be the, oh my god, it's going to be the value, and the font size is, let's say, 14. Now we are going to need the plt dot y label of the frequency, and the font size is going to be 14. Okay, now let's show the plot, and it's going to be plt dot show, and let's run this. Module C born has no attribute of history, not history, his plot. Okay, wait, his plot. Okay, so this is what the uniform distributions look like. So we need to make these distributions into a Gaussian distributions. So to be more clear, here you can go to this website. It's called deepdatascience.wordpress.com, and it's basically to see what the normal distribution versus the uniform distributions look like. So you can see, like, this is the uniform distributions, which is similar for what we have here. Like, so this uniform distributions, and we want to make these distributions into Gaussian look-like of a distribution, which is something that look like this, right? So now that is why I'm using the uniform data distribution here. Okay, so that we really actually change something. Okay, basically that's what's going on. Now we are going to have self dot gamma value, and it's going to be nn dot parameter of the u dot sample. Wait, so for the uniform is going to be, so the low is going to be torch dot tensor, and it's going to be 0 0, not 0 but 0.0, and the torch dot tensor of 1.0. So this is basically the same as as this one. Okay, now for the u sample is going to be torch dot size of self dot in size, and and then we get the dot of view of the self dot in size. Okay. So that is for the gamma. Let's create the beta value, and the beta is going to be nn dot parameters of torch dot zeros of the self in size. Okay. Now we need to create something called register buffer. So it's going to be self dot register buffer, and it's going to be the basically the running min, and it's going to be torch dot zeros of self dot in size. And we need to also create another register buffer, and it's going to be the running variance, which is running far, and it's going to be torch dot ones of self dot in size. Okay. Now let's create self dot running min is going to be 0 like this, and it's going to be self dot running far dot fill of 1. So it's going to be look like this. Now let's create the forward propagation, and it's going to be self dot input, and the input is going to be x. Okay. So if the length of the x dot shape does not equal to 2, we are going to raise a value error, and it's going to be only for dense layers. Okay. Now if self.training is equal to the min, and it's going to be torch.min, so we calculate the min of the x of the input, and the x is going to be 0, and the variance is going to be torch.min of the x minus the min squared on the axis of 0. So this is basically the min calculation, and this is the standard deviations or the variance calculations. So now let's create self dot running min is going to be this formula. So moving min is going to be this formula, and the moving variance is going to be this formula. Okay. So the running min is self dot momentum multiplied by the self dot running min plus 1 minus the self dot momentum. So this is basically the exponentially moving average formula times the min itself. Okay. So for the self dot running variance or far, let's call it far, it's going to be self dot momentum, but not momentum, self dot momentum multiplied by the self dot running far plus 1 minus self dot momentum, and then we are going to multiply with the input dot shape in the first index divided by the input shape. Okay, it should be like this because I need this. The shape in the first index, which is the 0th index, and okay, yeah, -1, and then multiply by the variance. Okay, now that is if we are training. So else is going to be min, and it's going to be self dot min, a running min, and the variance is going to be self dot running var. Okay, now for the input of hat, x hat, so the x hat is basically the Gaussian distribution value based on the input, right? So it's going to be x minus the mean multiplied by the value of 1 divided by torch dot the square root of the variance. Oh my god, the variance plus self dot epsilon. Okay, so this is the x hat formula that we have, which is which is this formula. So this is the mean, this is the variance, and this is the x hat formula. So basically this is what we are doing, the x hat, and the output is going to be self dot gamma times the x of hat plus self dot beta. Okay, so that is basically the scale and shifting. Okay, so this is the normalized or the Gaussian distribution values, and this is going to be the scale and shifting. Okay, and we return the out, which is the distributions that we get from here, from the output. So let's run this, and we get an error, invalid syntax. Oh, okay, so this is supposed to be class. Oh my god, not function. What am I doing? Okay, now we create the class for the custom batch normalization. So this is basically the custom batch normalization. Okay, now let's create the neural network architecture and an architecture example for our custom batch normalizations. And so it's going to be, so we are going to have two architectures. So the first architecture is going to be the architecture that does not have the batch normalization, and in the second architecture we are going to apply the batch normalizations. So let's create class of networks non-batch. So we are not going to use the batch normalization in this particular architecture, just for the example, so it's going to be defined init of self, and super function is going to be net non-batch dot self, and then dot init this, and we are going to use self classifier self.classifier is going to be nn.sequential, and it's going to be nn.linear. So okay, we are going to use the MNIST dataset, so it's going to be 28 by 28, it's going to be 64, and so we are going to use the value for the non-linear activation functions. We are going to use the linear of, so it's going to be 64 and 8, and we are going to use value on, and finally we are going to use the linear of 128 and 10. So this is the amount of input, and this is the amount of a neuron in the first layer. This is the amount of input based on the first layer, and this is the amount of neuron that this second layer has, and the last layer we have 10 neurons because we are using the MNIST dataset. Okay, so for the forward propagations, define forward, it's going to be self x, and the x going to be x dot view of x dot size, oh my god, size of 0 and -1, and x is equal to self dot classifier of x, and we return x. Okay, so this is the first architecture that has non-batch normalization, and let's create the architecture that has the batch normalizations. So it's going to be class of net batch for net batch, and we are going to use the model from from Pytorch, and it's going to be define init function of self, and let's call the super function of net batch, and this is not hunter x hunter, and self and dot init like this. Okay, so for the self dot classifier is going to be nn dot sequential, and we are going to use the almost the same kind of architecture, which is the linear of 28, oh my god, 25 times 28 with 64 amount of neuron. Now here we are using our custom batch normalizations, and since we are we are going to create a Gaussian kind of distributions, across, so it's going to be on each neuron, okay, on each neuron in this hidden layer. So we are going to have the custom batch normalization for each neuron, and it's going to be nn.ReLU. So that is the first layer, and for the second layer we're going to use the linear, and it's going to be wait, how much? 64 neuron as an input and 128. It's just the same, and then apply the batch normalizations for 128 amount of neuron, and we are going to use the ReLU for the non-linear activation function, and finally we have the linear. That's going to be 128. Oh my god, 128 that has 10 output. Okay, so for the forward, it's going to be self.x, and it's going to be okay, I'm going to do this, right? X is equal to x.view, then x dot size of 0 and -1, and the x is equal to self dot classifier of x, and then we return the x. So that is for the neural network that has the batch normalizations. So now we need to create the model, and the model is going to be non-batch let's say, oh my god, model is going to be net non-batch, and for the batch model it's going to be net batch. Okay, so this is the model. Let's run this. It has no attribute of ReLU. Sorry, I made a mistake here. So it's supposed to be ReLU like this, not ReLU with little u. So it's going to be like this. Run this, and then run this, then run this. Wait, which one is it? Net non-batch. ReLU. Okay, like this. Tensor takes one position argument, but two were given, and uniform torch dot tensor. It's gonna should be like this, if I'm not mistaken. So let's run this. Torch.nn as parameter, and it's going to be self.beta. Self.beta parameter, is that correct? So let's run this again. Okay, now we need to create the loss and the optimization. So the loss and optimization is going to be loss fn is going to be nn dot cross entropy loss, basically the negative log likelihood loss, and the optimizations is going to be optimization optim dot stochastic gradient descent. So we are applying this into batch non-batch model, non-batch model that we have dot parameter, and the learning rate is going to be 0.01. okay, so with the optimizations for the batch normalization part is going to be optim dot stochastic gradient descent, and it's going to be the batch model dot dot parameters, and the learning rate is going to be 0.01. So let's run this. I hope there's no mistake. Okay, we successfully run that. So let's create something called the loader, and we call the data loader loader, and it's going to be okay, so I need to import the okay, I need to import another dependencies, and it's going to be from torch dot utils dot data. I'm going to import a data loader. Okay. Oh my god. It's going to be a data. Okay, and I'm also going to probably, just for the case, torch from, not from, but let's just import. It's going to be import torch vision dot datasets, import not import sets as datasets, and import torch vision dot transform as transform. Okay, so let's import those dependencies. And so for the loader, give me a minute. Okay, so for the loader is going to be dataset train dataset, then let's say the number of worker we're going to need is let's say 4, and then the batch size is going to be 32, and then not 32, but let's say 512, why not? And then let's shuffle the data. And the train dataset so we need the train dataset. And we need to load. So first of all, we need to load the dataset. Okay. So we are going to create a train dataset, and we are going to take datasets.mnist, MNIST, and the root is going to be dataset slash, and then the train is going to be true, and transform is going to be transforms dot transform transport dot to tensor, and let's download the dataset. Download, and it's going to be true. And then I'm going to copy this one, and doing that, and then so that's train dataset, and train loader is going to be data loader of dataset equal to train dataset, and batch size is going to let's say 64, and shuffle is true. So this one is going to be the test dataset MNIST dataset, then so this one, the train is going to be false, tensor, and then it's supposed to be the same for, and then for the test loader is going to be test dataset, and shuffle is true. And then so let's run and download the MNIST dataset. So we finished downloading the MNIST dataset. Now we can run this one. Okay, so finally let's train the data and the architecture that we've already created. So I'm going to track the loss array and the loss for the batch normalization, and let's put it into an array. So the maximum epoch that I want to have is 5. So for epoch in range of maximum epoch, so why not, so it's going to be, oh my god. So first of all, we're going to get the running loss, and it's going to be 0, and the running loss for the batch normalizations going to be the 0. So this is for the non-batch normalization, and this is for the batch normalization specifically. And for I and the data in enumerate, it's going to be lower and 0, and it's going to be inputs and the labels, and basically we get that from the data. Okay, the data. So this is for the non-batch normalizations, and it's going to be optimum.0 grad, and the output is going to be the non-batch model, and we get the inputs, and going backward, not backward, we loss, and the loss is supposed to be the f of n not f of n but c for me, f of n, f of c, then the output and labels. Then going backward, oh my god, so it's supposed to be labels, not label, and then the optimization for the non-batch normalization is going to be output of the step. Okay, I hope that's correct. So that is for the batch normalization and non-batch normalization, and then this one is for batch normalization, and it's going to be the optimization of the batch normalizations that 0 grad, and the output for the batch normalization is going to be the batch model of the inputs, and the loss for the batch normalizations is going to be the loss of FC, and it's going to be output of the batch normalizations and the labels. So that's the loss, and then the loss dot, not dot, but for batch normalization dot going backward, and the optimization for the batch normalization is going to be step. Then finally we get the loss or dot append of the loss item, like this, and the loss for the batch normalization 1 dot is going to be dot append of loss of the batch normalizations dot item. Okay, so now let's print the data. print the data, and it's going to be the running loss. It's going to be loss dot item, and the running loss for the batch normalization is going to be loss of batch normalization dot item, if that makes sense. Okay, so now if the I is going to be 40 is equal to 0, like this, let's print the loss so it's going to be like this of D and then 5D, and the loss is going to be like this of F, and then the loss of the batch normalizations is going to be dot 3F, then doing something like this, if that makes sense. Now for the epoch it's +1 and the I is also +1, and then multiplied by the amount of data that we are going to use, and the running loss is going to be divided by 40, and the running loss of the batch normalization is also going to be divided by 40, if that makes sense. So let's close this right there. So and the running loss is going to be 0, and the running loss for the batch normalization is also going to be 0. And so let's print so it's going to be is equal to multiply by 40. So we are going to print like this, and then plus the epoch value is going to be like this, dot format of the epoch +1 nope, and then plus, and it's going to be 10. And now for the input, it's going to be inputs dot view of the input dot size, and then we're going to do that. So that is okay. So that's training. Now let's get the activations from it. Activations is going to be non batch model dot eval. So let's evaluate the non-batch and the batch model dot eval. So okay, let's plot. Okay, first of all we need to create something like this. Let's see, A is equal to non-batch, my god, non-batch model dot classifier, and it's going to be the inputs like that, and then A is equal to A dot, so detach, then turn that into the numpy, then revel this value. So dot this plots like this, and we are going to A, and then KDE is equal to true, and the color let's say red, and the label is going to be normal. or no, normal, and then normal like that. Why not? And then for this, for the A, and then for the B, which is for the batch model, which is basically almost the same. So let's just, but we change it to B, and then we delete this like that. Then it's going to be B, and it's going to be B, and it's going to be, but this one is going to be 1 instead of 0. And it is also going to be like this. So we actually have 0 and the 1, but this one is not for the input, should be for B, like this, if that makes sense. So instead of red, let's use green label. Okay, so I hope that makes sense. Is that make sense? Now let's plot it. Let's plt dot use the title, and the title is going to be like this. So the loss is going to be let's use 2, and the loss with the batch normalizations is going to be 0 to F, then something like this, and then epoch plus 1, and then the loss dot item, and the loss of the batch normalization dot item. Does that make sense? And then let's plot. Let's use plt dot legend, and then plt dot save figure, and it's going to be activation distribution. Why not? So it's going to save, and the DPI is going to be 100. Then plt dot show, and then plt dot pause. We need to pause, and then let's use 0.5, and then let's print, but let's something like this. Why not? Just to separate, because there's a lot of things happening here. So plt dot plot again, and it's going to be the loss array that we've already created. Let's go to R for the red color, and then the label. So the loss R is going to be for the normal, and we also need to plot the other one. This is the loss of the batch normalization one, and it's going to be green, and the label is going to be batch norm. Now let's use plt dot save figure. Also let's save the figure, and it's going to be training loss .png. Why not? So the DPI is going to be 100, and plt dot legend like this, and then plt dot show like that. Okay, there's a lot of things that we've right here, and let's try to run this. Okay, which one? Required fire forward function, net non-batch. Define. Should be like this. Do you also make let's try to run it again. So which one? Net non-patch missing required, forward non-patch model. Okay, so let's run that again. Custom patch node has no attribute. What is bit? Bit? Where is it? So it's supposed to be beta. Okay, and then let's run this just to make sure. So let's run this again. Okay, now we are printing the loss value for the loss value that are using the, so this is the loss value that are not using the batch normalization, and this is the loss value that are using the batch normalizations. Okay, so let's weight this. Okay, so we are using how many again? 5, I guess. Okay, so 5, and we are in the 4. So let's just wait. Why not? Wait, what's going on? Function input.size. Inputs format epoch. Oh, print. So input inputs, not input. Okay, let's run this again. Okay, so I actually finished the training, but there's a mistake. So previously I put A instead of B here, so so let's train again. Okay, so I'm actually finished the training, and here I get, so this is what we get. So in the normal distributions, we get this kind of a random distributions, but when we are using the batch normalizations, we get again this some kind of a Gaussian kind of distributions, and this is why we are using the batch normalizations. As you can see, the ones that using the normal distributions is kind of a not really training, but the ones that are using the batch normalizations is training significantly a lot better than the normal distributions that are not using the batch normalizations. And so the reason this happening is because in the batch normalizations we are not having the issue of the where is it? We are not having the issue of the internal covariance shift problem. So we remove that problem, and now we get a much more a better kind of a training process. So that is the batch normalizations, and I hope you understand. But again, if you not understand all of this, it is completely fine, because all of this is happening behind the scene. You're not even going to see you're not going to see all of this. You're not going to implement all of this, because all of this is happening behind the scenes. So if you're not understand all of this, it is completely fine. But yeah, that is batch normalization for you. Okay, now we are going to implement. So it's going to be the neural networks implementation implementation using Pytorch. Okay, but now we are going to use RGB image instead of the MNIST dataset. Okay, so let's call this file I don't know, Pytorch neural networks RGB maybe. I don't know, but we are basically using the RGB image instead of a simple, a simple MNIST dataset that we always use. So again, let's import some dependencies. So import dependencies, and we are going to need import numpy just for import numpy snp, and then we are going to need import torch, and then we are going to need import torch.nn as nn, and then we are going to need import torch.nn.functional as f, and then we are going to import torch.optim as optim, and then we also going to need import torch vision, and we are going to import torch vision.transforms as transforms. Okay, so before I run this cell, I'm going to change my run type into GPU. So let's save that, and now I got connected to the GPU, and so I can run this. You have to manage session. Okay, and let's close this part. And let's wait. While we're waiting, let's create transforms is equal to transforms dot compose. So transforms, what are we doing here? So we are, oh my god, we are going to create transforms is equal to tensor forms. Okay, to tensor, and we are going to transforms dot normalize, and we are going to use 0.5, 0.5, 0.5, and then it's going to be same 0.5, 0.5, and that's going to be 0.5. Okay, so we normalize the data, and we also normalize into change the data into tensor. So let's run this part. Now after that, we need to get the data, okay. So the same thing happening as for the from the last segment. We are going to need train.data is equal to torch vision dot datasets, just the same dot, and now we are going, instead of MNIST, we are going to get the cipher of cipher 10 dataset. So if you don't know what cipher 10 dataset is, so the cipher dataset is going to be look like this. Okay, can I? So we are going to have this kind of data set, and it has a lot of category basically. So they have dog here, they have bird, they have frog, they have sheep, they have horse, they have truck, etc. So it's going to be, a color data set. It's going to be RGB data set. So this is what we want, and it turns out that Pytorch has the cipher dataset. So we can take those dataset so Pytorch has this cipher dataset that we can use, and we are going to use that. So this is how you call it, and it's going to be root is equal to dot data slash, not data slash, but dot slash data, and then we are going to get train is equal to true, and then transforms is equal to transforms, and then download is equal to true. So we are going to download the dataset from Pytorch API. Now we need to have test data, and we're going to have torch vision dot datasets dot cipher 10, and it's going to be same. The root is going to be dot slash data, but the train now is going to be false because we don't want to train. And transforms is equal to transforms, and the download is equal to true because we are going to download this dataset. Now for the train loader is equal to torch dot utils dot data loader is, and it's going to be train data, and then the batch size is going to be let's say 32. So previously we have 64, now let's use 32, and then we are going to shuffle the data, and then we are going to have the number of workers, let's say 2. So the same thing with the test loader is going to be torch dot utils dot data dot load data loader, and it's going to be test data, and the batch size is going to be 32, and then we are going to shuffle the data and using the number of workers as 2. Okay, so let's download. Okay, so what's going on? Okay, I always forgot that this is not supposed to be transforms but transform. Okay, we are downloading the data. Now while we're waiting, let's create the model. Got expected keyword transform, like that. So let's do it again. Okay, so we have already downloaded data, but we need to create the class name. So inside of this cipher dataset, the class names is going to be, or the category of the images is going to be plain. We are going to have car, and then we are going to have bird, and then cat, and then we are going to have deer, we are going to have duck, and then frog, what, duck, and then frog, and then horse, my god, and then we are going to have sheep, and finally we have truck. So this is the category that they have, which is 10 category. That's why it's called cipher 10. And let's run this cell so we get the category for our data. Now let's create the model for the neural networks. So okay, we are going to create much more proper, not proper, but much more of a deep neural networks looking kind of like, you know. So let's create the class, and it's going to be C neural net, and the C stands for module. C stands for you know, convolutional, because we are using you know, the RGB image. And as I mentioned previously in the previous segment, we are using the convolutional neural networks so that we can use the, you know, a big data set like this, like the cipher data set, because it has a lot of class, it has a lot of dimension on each data, and it has a lot of data basically. So we are going to create the convolutional neural networks basically, and then we need to have the init function, and inside of this init function we are going to have self. Now we need to call the super function, and inside of the super function we are, and then we are going to get the init function like that. Okay, so first of all, what do we need in order to create our neural networks architecture? Okay, I'm going to do this. Convolutional neural networks architecture. So first we are going to have convolutional layer, and the convolutional layer is going to be nn.conv2d, and it's going to be 3 and then 12 and then 5. Okay, and then so it's going to be I guess it's going to be 12 and 28 and 28. Okay, so and then we are going to apply batch normalizations. So it's going to be the first batch normalization, and we are going to have nn.batch norm 2d, and we are going to have 12, and going to be batch normalization for the first layer. Okay, for the first convolution layer, and then we are going to get the pooling layer. So it could be pool 1 is going to be nn done. So we are going to use the max pooling layer, and it's going to be 2 by 2 pooling layer, and then after that we are going to get 12 and then 14 data out from that, and then we are going to get to use another convolution layer. So it will be conv2, and it's going to be nn.conv2d, and we are going to have 12, and then 24, and then 5. Okay, and then we are going to have self.batch-normalizations number 2. So we are going to use the nn.batch norm 2d, and we are going to have 24, basically because this is 24. Okay, now let's create self. Okay, maybe I need to explain. Okay, I don't know if I should explain it right now or later. Okay, probably later. I'm going to explain it later. So it's going to be after the batch normalization number 2, we're going to have our fully connected layer. This could be nn.linear, and inside this linear function is going to be 24 multiplied by 5, and then multiplied by 5 by 120. So I'm going to have 120 amount of neurons. Okay, and then what else? Let's apply the batch normalization number 3, and it's going to be nn.batch norm, not 2D, but now we are using the one-dimensional because it is for the linear, and so we are going to use also 120, and then we are going to need the fully connected layer number 2. That's going to be nn.linear of 120, and let's have 84 amount of neuron, and then we are going to have self.batch normalization number 4, and it's going to be nn.batch norm 1d, and we are going to have the same amount of neuron from the fully connected number 2, and finally we are going to have self.fully connected number 3, and it's going to be nn.linear of the input, which is coming from the batch normalization number 4, and the output is going to be 10 because we have 10 categories inside of this cipher 10 dataset. So cipher 10 has 10 categories, or you can say it has 10 labels. It's just the same thing. Okay, so that is the model that we have. Now let's get out of this model. So we are going out from this function, init function, and then we are going to create our forward propagation. So it's going to be forward. It's going to be self dot, not self comma the input, and it's going to be x self dot conv1, and inside of this conv1 is going to be x. Okay, and then we are going to apply self dot batch normalization number 1 after the convolutional number 1, and then we are going to apply the value non-linearity into the batch normalization number 1. Okay, and then we are going to apply the pooling. So it's going to be self dot pooling layer number 1 after we applying the value. Okay, so this is basically you can say that this is the first layer, but sometimes I don't know, sometimes they count the pooling layer as one layer, sometimes they counting the convolutional and the pooling layer as one layer, but basically you know what this means. So you already know what that means because I explained that in great detail. Okay, I'm going to convolutional neural networks. I'm going to use an example of what happened there. So where is it? Okay, can I get a bigger data? This was big. Yeah, okay. So the convolutional layer and then the pooling layer. So this part of the layer is basically the same as this part, okay? And then we are going to have self, just the same thing, and then which is pooling layer number 2. Wait, do we have pool number 2? Wait, we don't have pooling number 2. So let's just calling this pool then. So let's doing this then, because basically the same thing. So this is going to be the same value, and it's going to be self dot batch normalization number 2, and then it's going to be self dot convolutional number 2, and it's going to be x as an input. Okay, and then we need to flatten the data. So it's going to be torch dot flatten of the x, because we are going to input this into the fully connected layer. For the fully connected layer, so it's going to be x is equal to f dot value in the self dot batch normalization number 3, and then self dot fully connected number 1, and then the input. Okay, so doing the same thing, and it's going to be a value of self dot batch normalization number 4, and it's going to be self dot fully connected number 2, like that. Okay, and then finally we are going to have self dot fully connected number 3. That's going to be the input, and finally we return the x. Okay, so we have no function because there's no no activation for final layer, because softmax will likely follow in the loss function. So that's basically what happened. Okay, so let's try to run this part, run this cell. We get an error, and it is a syntax error, and we don't need this. And let's try again. Okay, so we create our model. After creating the model, let's create a device, and it's going to be torch dot device, and it's going to be CUDA if torch dot CUDA dot is available, else we are using CPU. And let's run this cell, and then okay, let's summarize. Okay, let's visualize the CNN architecture. that we already create. So it's going to be from, so we need to have from touch summary, import summary, and we're going to create the model using the C neural networks, which is the one that we made here, C neural net. So it's going to be C neural net, and it's going to be input to tensor. Tensor, okay, not to tensor, to device. Okay, and then we can summary. Oh my god, summary the model, and 3 by 32 of 32. Okay, so why 3 by 32 and 32? 32. Well, because the data set that we have, is going to be, so let's image and label. It's going to be so let's create let's see the trained data. So the trained data is going to be, so it's going to be image, and then image dot shape. So what is the shape of the image? So this is the shape of the image. So they have 3-dimensional, which is the RGB, and then 32 by 32 pixel. So this is the data of the Cipher 10, and that's why we are going to need, you know, this dimension and this row and column. Now let's run this. Math one shape can multiply to tensor summary model to 32 32. Going to be 3 12 and then 5 and then 12 24 and then 5 and 24, then 24 5 5. ff dot linear 84 84 120 84 84 84, the fully connected. Oh, should be 1. The x, and yeah, because because we need the dimension. Okay, now this is the convolutional layer, not convolutional, but convolutional neural networks architecture that we've created. So we have the convolutional, and then batch-normalization, and then pooling layer, and then we have convolutional again, batch-norm again, and then pooling layer again, and then we apply the non-linearity, and then apply batch-normalizations, apply non-linearity, apply linearity again, and then batch-norm again, and then finally we have linear layer. So this is the you know, convolutional neural networks architecture that we've created. So now we can create the training part. So it's going to be train. So let's train the networks using the data that we have. So it's going to be 4 epoch in range of, let's say, 30 epochs or 30 iterations, and it's going to be let's print f. So let's print so that we know the epoch or the progressions that we have. It's going to be epoch. So we do that, and then we are using the running loss is equal to 0. Okay, and then it's going to be for I and data in enumerate of train loader. Oh my god, train loader, and it's going to be inputs and the labels, and it's going to be inside of this data because the data has the inputs and the label. And then we're going to get the optimizer dot 0 grad. Okay, optimizer, and yeah, I forgot to create. So okay, so let's create the model parts first. So the model is going to be C neural net, and the loss function that we're going to need is let's create the loss function, and then it's going to be n cross entropy, which is the negative log likelihood, and the optimizer is going to be optim dot we are going to use stochastic gradient descent, and then model dot parameters, and then we are going to have the learning rate of, let's say, this amount of learning rate, and then the momentum is going to be 0.9. Okay, let's run this part, and it's going. Okay, so after optimizer we are going to have the outputs. Sorry, it's going to be the model of the inputs, because in the model, in the C neural net, it will returning this X, and we need to catch that X and put it inside of this input, not this input but output, and then we get the loss of the loss from the loss function, and it's going to be the outputs and the label, which is basically the prediction and the true label. And then we're going back propagation by doing loss dot backward function like that. Okay, and then let's do the running loss is equal to loss dot item, and let's going out, and let's print the loss value that we get. So the loss is going to be the running loss the running loss divided by the amount of the train loader that we have, and it's going to be let's have just for and yep, like that. And yeah, and let's start the training, and we get an error. Of course we get an error. SGD has not attribute 0 grad. It's supposed to be 0 grad. And okay, it looked like it started to train, but while we waiting for the training to complete, because we have a lot of iterations, which is we have 30 iterations, so it's going to take a lot of times. So let's create. Okay, you know what? You can save the model by doing torch.save and model.state dig like this, and you can name the model like what do you want the model to name, like for example train .nav, and the format is going to be PTH. Okay, but since we are not done training, so we cannot save the model, but let's create. Okay, so this is how you save the model. Okay, I'm just gonna telling you saving the model, the neural networks, the NN model from Pytorch, and this is how you load the model from Pytorch. Okay, so this is how you do it. It's going to be model is equal to C neural net, and it's going to be dot to device and it's supposed to be function, and then model dot load dot state, and then dictionary, and then torch dot load, and what is the name of the model? It's going to be this one, right? So PTH like that. Now okay, again, since we still doesn't have the model to save, so we don't have the model to load because we're still waiting. Okay, it's epoch 4, we have 30 epochs, and so let's just wait for the neural networks, for AI to train. But let's create the accuracy, so check the accuracy. So we are going to create a function to check the accuracy. Accuracy check accuracy, and it's going to be loader and the model. Okay, so we are going to create a number of correct, and it's going to be 0. Oh my god, correct, and it's going to be 0. The number of samples, which is the amount of data that we have, is equal to 0. And then the model dot evaluate, so we need to evaluate the model, and then with torch dot no grad, and it's going to be x is equal to x dot to device, and then y is equal to y dot to device, and then scores is going to be from the model of the x of the the data, based on the data, and the model is going to give us the predictions, and that's why we need to score those predictions inside of the model, and we are going to get the predictions, and it's going to be score dot max, scores dot max, and then the number of the correct prediction is going to be like predictions is equal to the true label, and then sums up all of the prediction. And then for the number of samples, it's going to be prediction dot size of 0 chance, like that. Okay, and then we are, wait, I forgot, for x and the y in loader, and then this one should be like that. Okay, so then we are going out from the for loop, and let's print. So we are going to get the number of the correct predictions and the number of samples. With accuracy of the float, and it's going to be number of the correct, oh my god, it's going to be the correct one, and it's going to be divided by the float of the number of samples, and then multiply that by 100 to get the percentage value. And then let's have just 2 number behind the comma. It's going to be like that, and then we are going to have the percentage symbol, and then we're going out from there, and then model.train. So we're training the model, and then we're going out from the function, and then calling that function of check accuracy using the training loader and the model that we have, and then also we check the accuracy of the test loader that we have, and then we are using the same model. Okay, how many epoch? It has 12 epoch now. 12 epochs. Okay, so this is the accuracy check. Okay, now, okay, I want to show you something. So we can using the model that we've already trained, not just using the data set from the MNIST. So we are going to use an entire new data. So it's going to be, so what do I mean by that? We are going to predict using random images. So we are going to use random images that this model, this neural net model never seen. So it is not going to be from the Cypher dataset. We are going to use our own dataset. So that's basically what happened, what we are going to do. And okay, to visualize the data, let's use the pillow. So we need to install the pillow, and then we need to import from pill, import image, and we are going to create okay, so this is how you predict. We are going to create new transforms, and it's going to be transforms dot compose. So we are going to transforms the data that we have like that. So it's going to be transforms dot resize, because we need to resize the data, because if it's going to be a random data, we need to match the data. It's going to be 32 by 32 because that's what the input that we create for the neural nets that we have. And it's going to be transforms dot to tensor transforms, and then we are going to have transforms dot normalize. So we are going to normalize the data, and it's going to have 0.5, 0.5, 0.5, then 0.5. Then we're going to have 0.5, 0.5, then 0.5. Then that's it. Okay, so transforms epoch 18. Okay, so it still needs a long time to that. Okay, now let's create a function to load the image, and it's going to be the image path, and image is going to be image dot open using the image path, image path, and then image is going to be new transforms. So we are going to transforms the image, and then the image is going to be image dot unsqueeze. Then we going to need return the image, and let's connect the image into the device. Okay, so that is the function, and the image path that we are going to give into the load image function is it's going to be so let's see if I have an image. Okay, it's going to take a long time to load because I'm not yet mount my drive. So it's okay, epoch 22. So image.path, so I'm going to put my path image inside of this part, and it's going to be images equal to, so we're going to load the image, and it's going to be image, passing that image for image in image underscore path. Okay, paths. Okay, and then model dot evaluate, and it's going to be with torch dot no grad, and it's going to be for image in images. It's going to be output model of image. So we are going to pass the image that we have into the model that we've created, and we are going to get the prediction of it, and it's going to torch dot max of the output, and it's going to be 1, and let's print if the prediction is correct or not. So the prediction is going to be inside of the class name, so it's going to be predicted dot item, a function, and then yeah, predicted, not predicted, prediction. Okay, so we are going to get the prediction out of it. How many epochs? 25. And well, I mean, we can, you know, visualize the image, and to visualize the image we are going to need matplotlib dot matplotlib dot pyplot as plt, and we are going to need import matplotlib dot image as mpemg, and then it's going to be plt dot imshow the mpemg dot amread the images, which is the same, is going to be the same images that we are going to where is it, that we are going to put inside of this image path. Okay, so I guess that's it. So we are going to predict the random image, the image that we have. So it is not going to be from the Cypher 10 dataset, it's going to be our own image, and let's see if the networks that we've created can, you know, can predict a random image. And then so we are going to predict the random image using this cell to get the predictions, and then we visualize the image that we have. So that is basically what's going on, to see if the, so like for example, if the prediction is, you know, a cat, so okay, the neural networks that we have saying that this image is a cat. So let's try to visualize the image and to see if it's a cat or not. So that's basically what happened. Now let's find an image in my data folder. Okay, so we are finished to train. So the loss, we have 2.3. Okay, so I want to mount my drive, connect to Google Drive. So okay, after 30 epochs we get this amount of loss, and let's see if with that amount of loss we can, the neural networks that we've created can, you know, can predict our image. I don't know which one should I use. I mean, I do have images. You know what? Okay, so I'm going to save the image, not the image, but the model. And if you save the model in your Google Colab, you will have the model in here. So if you want to download the model, you can, you know, click this and then download the model to get the model, and then we can load the model by using this. And so it's going to, you know, searching for this trainnet.pth. okay okay still I'm going to find a good image derivative dataset. So let's try to use this copy.path. So let's try, and okay, we need to, let's check the accuracy. Scores iterations over, we have an error. What is that error mean? X to model that evaluate number sample, X and Y in loader, score 1 less predictions size of 0. Okay, and let's put the image, the path here to see, and this one is here. Okay. Wow, such a bad accuracy. Wait, why do I get such a bad model? Okay, there's something wrong with this model. Do I forget something? So it's going to be epoch the running loss 0 in enumerate data loader inputs label is going to be data optimizer 0 grad output model input loss function. Oh my god, what am I doing? Optimizer dot step. I forgot to update. Okay, you know what? Let's use 10 epochs for now. And then, my god. Okay, so let's start over. Using this one. Let's start over, and then let's train again. Oh my god. Okay, so we finished the training data because I'm stupid, because I forgot to but so train. So let's save the model, but now let's save the correct net, train correct net. So let's save the model, and it will appear there. And so let's load the correct one. Such a funny sentence. I can't believe I'm forget to update the parameters. Oh my god. Okay, so now let's check the accuracy. So by doing that, we get 0.6 amount of loss value, and let's see the amount of accuracy that we get. Oh my god. Okay, we get 81% of accuracy, and in the test loader we get 71 accuracy. Okay, so now let's predict using the random images. So we need to install pillow, install pillow, and then let's get the image from the below, and then let's doing this. Do you forget parentheses around around the load image? Load. No, I'm not forget, but I'm having too much. So what is it? Compose has no attribute. Compose transforms okay. What if taking this? Wait, what's going on? Then do that, but now a new, and then add the transforms dot resize of 32 and then 32. And let's try that. Has an attribute compose. Wait, what's going on? Transforms. Okay. Wait, what is going on there? So prediction is dog. So okay, so I get my image. Okay, so I should show my image. It's not in data, it's in drive. It's drive, and inside of the dataset, and this image. And you know what? Let's visualize using the matplotlib. So is it a dog? Yes, it is a dog. So the convolutional neural networks that we have is, so the model that we create using the Pytorch. So we create the convolutional neural networks model, and we have that has the loss of 0.6 during the training. And when we check the accuracy using the train loader, which is the training data, which is the data that the model has already seen, we get 81.72% accuracy. And then when we check the accuracy using the test loader, which is the data that the model has not seen during the training process, we get 31.21% accuracy. And when we are using, our own data, our own image, which is this image, we get the prediction of dog from the the neural networks that we've created. And when we visualize, it is a dog. So this model that we've created, is predicting the correct answer. So that is okay. So that is how you making the convolutional neural networks using the Pytorch frameworks or Pytorch library. Okay, so yeah. All right. So we've been using a data that is provided for us. So for example, we've been using a data like the Cipher 10 or the MNIST Dataset that is being provided by the Pytorch, or just being provided by the the many sites that we've already has visits. But you're probably wondering, what if I want to use my own dataset? So what if I use, I have a bunch of data that I want to, classify an image data that I want to classify. So how can we do that? So how can we do that? And it's not just that. Okay, how can I use my own data sets and performing neural, oh my god, networks classification using Pytorch? How can I do that? Okay, so this is what we are going to do. We are going to use our own dataset. It's not like other people's dataset. It's not the dataset that's Pytorch being being produced. So let's call this file I don't know, custom dataset, maybe sets for Pytorch. Okay, now I have my own dataset right here. Okay, in order to create your own dataset that's going to work in Pytorch, you need to do this. First, create a folder. Okay, create a folder, and this is my folder, and it's called cat.doc classifier. So inside of this folder, I would have two folders. One is train and one is together. So what is train? So train is the dog and a cat. So if you have a multiple categorical images, like for example, for the case of vehicles, so you want to classify a vehicle, like for example, you have train, you have plane, you have ships, you have car, you have a motor. So you have so you need to have 5 folders inside of your train folder. Okay, so you need to create the entire folder, and inside of this folder you need to have a train folder, and inside of this train folder you need to have 5 vehicle, which is train, car, etc., etc. In my case, I have dog and cat. So let's see. Inside of this dog data, not data, but folder, I have a bunch of dog images. Okay, so this is dog images like this, and then I also have a cat folder, and inside of this cat folder, I have a bunch of cat images. Okay, so there's a lot of cat images right here, and so that is the train folder. What about the together folder? So inside of this together folder, I would have the cat and the dog being together. So this is the mix, the mix image folder. So I have dog and I also have cats inside of this folder. So basically I have everything that is being provided inside of this folder. So I have, so again, create a folder. Okay, create a folder, and inside of this folder you need to have train folder and then together folder, and inside of this train folder you need to classify the images first. So you would have your categorical. So in my example I would have dog and cat, and inside of this folder you would have your images. Okay, and you also need to have the together folder, which is the combination of the train folder. Okay, so this is the first thing that you need to do. So now, in order to create a custom dataset, okay, I'm just gonna delete this. In order to create okay, I want to change my runtime type to GPU. Okay, so let's do that. Now let's start by making the training data. So first of all, we need to import some dependencies. Import some dependencies. I'm just gonna do that. And okay, no, it looks bad. Okay, let's import dependencies. So first we need to import OS, and we need to import CSV. So that is the first thing that we need in this case. Okay, so let's just wait, and while we're waiting, we need to create. So let's create the path to our dataset folder. So the dataset path is going to be our string, and it's going to be, well, in my case it's going to be content slash drive slash my drive slash datasets slash cat underscore dog underscore classifier slash. So we need to get into, okay, now we need to get into this folder, this train folder. So we need to get into train folder first. Okay, so let's run this. Now we need to create the CSV output. So we need to create a CSV file for our dataset, because that's how Pytorch working. So we need to have the CSV file for this. CSV file CSV output file output. Okay, and the CSV output oh my god, so the CSV is going to be let's call the, so you need to give the name of the folder, and I would name my, not folder but file, my CSV file is cat.csv. So let's do that. Okay, and then we need to open the CSV file to write. And how can we do that? Well, we can do this with open, it's going to be output CSV, and the mode is going to be W, which is write, and the new line is going to be just a string like that, as file. Then we can writer is equal to csv.write, and what we want to write csv, we want to write the file. So we want to open a file and write this file, and then we need to write the header. Okay, so the header, okay, I'm going to do this. The header is basically the first row inside of your CSV file. So it's going to be oh my god, it's going to be write row, and in the first row I want to have image title, and I want to have the label for those image title. Okay, now we need to create the loop through each folder in the dataset folder. So what do I mean by that? Well, we can do this for label, and then the folder name in enumerate. It's going to be os.list directory, and we are going to pass in the dataset path. So okay, I'm going to explain it later. And then it's going to be folder underscore path is equal to os.path dot join dataset, not dataset but dataset path and folder name. Okay, so in this part we are going to get into the dataset path. So what is the dataset path? It is inside of this train folder. So we need to get into this train folder, and inside of this train folder I want to enumerate. And then, well, so enumerate is basically giving your data a number, basically. So that's what enumerate means. And we are going to have the folder name, which is the name is either dog or cat, and we have also the label, and the label is basically, well, the dog or cat. Okay, now we need to ensure it's that it is a directory. Okay, so if I'm going to do this, so if the os.path dot is directory for the folder path, we are going to loop through each image inside of this folder, each image in the folder. Okay, so for image file in os.list directory, and it's going to be the folder path. Inside this folder path we can get, so we need to get the full image path. Okay, so image path is equal to os.path dot join for, and then folder path is equal to image underscore file. So, and then we need to ensure it's a file, and well, you need to make sure it is a file, basically. So if os.path dot is file, the image underscore path, so image path, we need to write the image file name and its label, which is, so the label is basically the folder index. So for example, remember the indexing. So if we are using the indexing, the dog is going to be 0 and the cat is going to be 1. Okay, so it's going to be writer and dot write row, and it's going to be image underscore file and the label Okay, and then we need to go outside of this. And finally, we can print to telling us if it's ready or not. So it's going to be CSV file is going to be output CSV created successfully. Okay, I believe this is correct. So what's going on here? Well, okay, when we get here, right? When we get here, we need to get the full image path. So what does that even mean? Like for example, okay, so we need to get what is my path? Okay, so this is my folder path. Okay, image. Where is it? Okay, I'm going to do this. So this is my folder path, which is the train folder path. Okay, the image path is okay, can I do this? Well, I need to get the image itself, not just the folder. So instead of this train, I'm going to go into the doc and then get the image itself. So this is what the image path means. Okay, and which is, you know, the path of the image basically. So now let's hope that it is working and let's run this. Oh, I forgot to csv.write module CSV has no attribute write because it should be writer. Okay, no such directory because I'm not yet mount my Google Drive, so we need to connect to Google and let's wait. Where is it? Okay, so I get my connection to my Google Drive, so let's run this again. And well, the CSV file created successfully. So it will appear here. Okay, and we can, you know, open this file, and this is what we get. Okay, you know what? We can actually download this and then open it. So let's try to open this file. Okay, so we have the image title, which is this, and then we also got the label. So for the doc image, the label is 0. As I mentioned, it is going to be an indexing where is it? The label and its index here. So the dog, if it's going to be indexing, the dog is going to be 0 and the cat is going to be 1, just like I mentioned before. So instead of this dog, I have 67 images for the dog, and the label for the dog is going to be 0 here, 0, and the label for the cat is going to be 1. So this is what we want. Okay, this is what we want. Oh, I have a lot of cat images. So image title and then the label itself. So we've created the CSV, and now we can finally, using the Pytorch, because for some reason Pytorch needs the CSV file for their access, and I remember that in TensorFlow they don't need the CSV file. They just or maybe I'm I'm forgetting something. But while I'm learning the TensorFlow, I don't remember I need to create the CSV file. But well, in this video we are studying using the Pytorch, so we need to create it. And well, it is a good study section, okay, now we can create the Pytorch. Pytorch, okay, what's NN for cat and for custom classifier, custom dataset. Okay, let's just call this like that. Okay, so first of all we need to import some dependencies. So we've been going through this. So it's going to be import pandas .pd because we are not .pd, pandas as pd because we are creating CSV file, so we need to import panda to read the CSV file, and then we need to import import torch, and okay, we need to import OS actually, and we need to import from torch.utils.data. Need to import dataset, and like data, and then from pill import image, with the capital pill import image, and then import torch vision dot transform as transforms, and then import torch vision. Okay, let's do that. If we need something else, we can just import it again. So let's create the model. It's going to be an model. Okay, again we need to create the class if we want to create the model inside of this Pytorch. It's going to be class, and let's call this cats and dog, and dogs dataset. Why not? Cats and dog dataset, and it could be we need dataset. So we are going to be need define the init function, and it's going to be self, and we need to have the CSV file. We need to have the root directory. We need to have transform, and the default is going to be none. Let's say we do that. Okay, so let's create the self dot annotation, and annotations is equal to pd dot read of the CSV file, and it's going to be the CSV file that we get from here. Okay, pd dot read. So we are going to read the file, and then self dot root directory is going to be the root directory, then self dot transforms is going to be transform form. Okay, so we need to define the we need to do this, define the len of the self, and it's going to be return the len of the self dot annotation. Okay, and then after that we get into the get item. Get item, and it's going to be self and an index, and then image dot path. So we need to have the path of the image, not in. I want to create a new variable. It's called the image path. That's an image file. Oh my god, image path, and it's going to be os.path.join, and it's going to be self.root directory, and also self.annotation dot ilog of the index of 0. Okay, and then the image itself is going to be image dot open using the image path. So we are going to open the image using this from the pillow library. And the y label, so we need to create the label. It's going to be torch.tensor, and it's going to be integer of the self dot annotation dot ilog of the index. Oh yeah, index is also we need to also index this part, and it's going to be 0 and 1. Now if self dot transform is equal to image is equal to self dot transform of the image. Oh my god. Okay, and then we need to return the image and the label. So we're creating basically the data preparations, and we need to have the image and the label. So let's run this, and then okay, again my file. So we need to have where's the file. So this is my file, so we need to copy this, and it's going to be like that. So this is my cat and dog classifier by using the CSV file, and the file path is, so this is basically the where is it, this one. Okay, so this file path is going to be this folder. Okay, and it's going to be slash content slash, well, in my case is my drive slash datasets slash cat and dog classifier. I believe that's correct, and then together. Okay, so we need to transforms. Okay, maybe I'm making a mistake. So this is not the NN model. It is like it's more like the data preparations. So data prep. Okay, so it's going to be my transforms, and it's going to be transforms dot compose, and we, oh my god, I want to do this. Okay, we need to transforms dot to tensor, and then transforms dot, so we need to resize the data. So let's see. Oh my god, I'm going to resize it into 256 into 256. Okay, so because your data probably is either such a big data or such a random size of a data, so you need to resize all of your data so that it's not too big and it's not random. The size is not random, so this is why we resize the data here. So the data is equal to, it's going to be cats and dataset, and it's going to be my file and the file path, and also transforms is equal to my transforms. Okay, so yeah, I know it, transform. So let's try to run this. Okay, now you know what, we need to split the data, split the data, and we are going to split it into train and test, and it's going to be torch.utils data.random split, and it's going to be our data, and we need to split it I don't know, 100 and let's say 45. So we're going to split the data, so the train will have this amount and the test is going to have this amount, if that makes sense. Let's run that, and then we need to load the data. We need to load the data for the Pytorch. So it's going to be we need to import the torch.utils. Wait, have I imported .utils datasets? No, I'm not yet. Utils and data. It's going to be import data loader. Okay, like that. Now we need to have train data, and it's going to be a data loader of, so the data loader is going to be a data set, and it's going to be train, and the batch size, let's say 30, why not? And then I want to shuffle my data, and for the test data is just the same thing. It's going to be data loader, and the data set is going to be the train instead of the train data, and the batch size is going to be the same as 30, and I want to shuffle my data. Okay, so let's run this. Okay, okay, you know what, let's visualize our data. Let's visualize our data. Yay. So to see if it's working or not. So basically that's what we're doing. Okay, to do this we need to import matplotlib.pyplot splt, and we need to have train features and the train label itself, and it's going to be next and iter, and then it's going to be train data. Okay, So we are going to print using the f string. Is going to be the feature patch shape, and it's going to be the train features dot size. Okay, and then I want to print the labels batch shape, not label but labels batch shape, and it's going to be inside of this train features, and it's also going to be the size, and like that. So the image is going to be train feature in the 0th index, and also we need to transpose and squeeze the data, squeeze the data. So for the label itself, we need to train label, and it's going to be in the 0th index. So this is basically the 0th image and the 0th label train labels, and so it's going to be plt dot time show of image, and the C map is going to be I want let's say gray, and then plt dot show. Then let's print the label, and the label is going to be label. Okay, so what am I doing here? I want to get, based on my train data, so what is the first image inside of my train data? And remember, we shuffle the data, so every time we run this and then we run this, we probably get different images because we shuffle the data. So I'm going to take the first images inside of this train data and to see what kind of image is that. So is it a dog or a cat? Okay, so let's try to run this. No such file directory, dot class first. No such files directory. Content datasets together. Let's try to run this again. No such file inside of this directory classifier. Wait a minute. Dog classifier. Maybe I'm wrong in that. Okay. Cat and dog classifier and together. Copy path. Like that, like that. And like that. So let's wait. Why is it taking so long? I just want to see the image. Okay. Now, okay, we have the image of cat. Okay, and the label is 1. The label for the cat. Now, which is basically that's what we have. So the label for the cat again is, you know, is 1. Okay, so that is the data. Now, okay, so finally let's put our data inside of the neural nets that we have. So it's going to be Pytorch. Okay, I also want to mention another thing outside of the custom dataset for Pytorch. And okay, you'll see Pytorch implementation. So it's going to be like that. It's going to be like this. So we need to import torch.nn as nn, and it's going to be import torch.optim as optim, and the device is going to be torch.device of CUDA if torch. Oh my god, torch.CUDA is available, else we are going to use CPU. Okay, so let's start with the hyperparameter, and it's going to be in channel, which is the amount of channel that we are going to have, which is it's going to be 3 because we have the RGB image. So it's channel, number of classes, it's going to be 2, which is dog and a cat, and the learning rate, let's see 0.001, why not, and the batch size, I don't know, let's say 10, and then the number of epoch, let's say also 10, and then the model. Okay, so this is what I want to show you. So we can have torch vision dot models dot Google net, and the weight is equal to default. So okay, what does that even mean? So remember in our previous segment we create a model, and we save the model. We save our model, right? The one with the .pth file. The one with the .pth file. So that is the model that we have. And inside of this model, we have the weight and the price, which is the parameter inside of a neural networks. So actually, you can use, other people's weights. And for example, I'm using the Google Net. Okay, so I'm just gonna do this. Torch.models and pre-trained weight. So all of these models is already trained. Okay, all of these models has already trained, and okay, do they have the list for the model? Okay, so this is the model for the classifications. So the following classification model are available with or without the pre-trained weights. So we can use all of these models. So in our case, we are using the Google Net, or sometimes they call it Google LearnNet. So Google Net. So let's see what's Google Net look like. So okay, so this is the architecture for the Google Net, and we are going to use this architecture inside of our Pytorch implementation. And to use this, to carrying this architecture, we can just write Google Nets, because apparently Pytorch has this architecture. So in the previous example, we are using the data sets from Pytorch. Now I want to show you how can we use the pre-trained model of a neural networks of an AI from Pytorch. So, and now we can use the default weights. So if we go to where is it, get weight, where is it? Okay, I'm just gonna. Okay, so what is this default weight means? So basically, all of this model that the Pytorch has been getting trained by a lot of a lot of data, using a lot of data, and sometimes they are using a different kind of data. And in this case, I want to use just default data from the Google Nets. So now we actually have a really good neural network model. So we have this model. So we have the input, and then the convolutional, and then the pooling, and then the convolutional again, and then convolutional again, and then finally the pooling here, and then something called inception. I'm not gonna lie, I don't think I'm going to cover this part and this part inside of this video. And then we finally get into the fully connected layer. But that's how you using the pre-trained model. Okay, now so first of all we need to define a layer, not define a layer, but we need to basically freeze all layers and change the final linear layer with the number of classes. So it's going to be okay. So what we're doing here, like for example, in Google Net, we don't know what kind of a classification that they are doing. So again, this is a classifications, but we don't know how much the the category that they are put inside of this output right here. So we need to get the correct kind of the number of output, which is based on our data. So it's going to be for param in model dot parameters, and it's going to be param dot required gets where is it, required grad, and it's going to be false like this. So you need to do this, and then for the final layers is not frozen, is going to be model dot fully connected layer, is going to be nn dot linear dot in. So in features, we are going to have 10, 24, and the output features I believe it's like that. It's going to be the number of classes that we have. Okay, like that. And so we need to model dot to device. Okay, I hope that makes sense. Now for the loss and the optimizer. So it's going to be criterion is equal to nn dot cross entropy, which is the negative log likelihood loss, and the optimizer is going to be optim dot, we are going to use Adam as an optimizer, so it's going to be model dot params matters, and learning rate is equal to learning rate, and the weight decay, so we're going to use weight, something called weight decay, and let's say it's going to be 1 then 5 like that. Learning rate, and then okay, for epoch, okay, I'm not gonna use the weight decay because I don't think I'm explaining this part, so I'm not gonna use that, so that we're not confused. So for epoch, in the range of the num epoch, so how many epoch that we have? We have 10 epochs, and it's going to be losses is equal to an empty array. So for batch dot not docs batch underscore index, and then we have data and the target or the label, data the target in enumerate of the train data. So it's, oh my god, so it's going to be, so we need to get the data to CUDA if we have CUDA. So it's going to be data is equal to data dot to device is equal to device, and the targets is also targets dot to device equal to device, and then for the forward propagation is going to be scores, and we are using the model, our model, and we are going to pass our data. So the model is this one and this one, not just that one actually. This is the model that we have, which is the GoogleNet model. Okay. Now we need to get the loss value as could be a criterion of the scores and the target. Okay, basically the loss value and the losses, I want to append the loss value inside of this array. Okay, wait, not like that, but loss dot item like this. Okay, and then we can go backward. So that's the forward, and now we go to backward, and the backward is, don't forget to update the parameters 0, we got grad and loss dot backward like that, and we need to have the gradient descent of optimizer dot step like that, and we can print the data f, so it's going to be f cost at epoch of the, of the current epoch is So I think it's sum of the loss just divided by the length of the losses. Okay, so let's try to run this model, and we are training key argument weight. Because it's supposed to be weights like that, and then linear has no attribute linear because it's supposed to be capital L. And so we are training, and let's see if it's the correct implementations. Okay, so apparently I made a mistake in this part. So it's supposed to be sum and then losses, but I'm doing this basically, so it creates an error. And let's start to train again, and then we train the data, and this is the amount of losses that we got. So we have a pretty good training losses, and we get into this point of losses. And I'm not gonna lie, since I'm making mistakes, so basically I'm training at 20 epochs instead of 10 epochs. So this is the the cost or the loss value during my 20 iterations basically. So we get into this, and okay, as you can see, if we are using the a pre-trained datasets, we basically have a really solid model. So we don't need to get into like tweaking the model first. So we can just have a little iterations, and then we already have a very good model of our classifications. So that is the custom datasets, and that is the pre-trained model. And I hope you're having fun. Okay, so we learn about image classifications. Okay, so if I'm asking you what is this image, you will answer it, oh, it is an image of a cat. And then if you put this image inside of your neural networks, and your neural network is probably guessing, oh, this is the image of a cat. But now the question is, I want to detecting the object. So this is going to be the object detection segment. So the questions become, it's not whether this is a cat image or not, but where is the cat? Like for example, so this is the cat image, but where's the cat inside of this image? And I want you to give me a bounding box, so that you can telling me the position of the cat. Okay, so this I want you to give me the position of the cat. So I would doing this. Okay, I'm not right brush, and the size is, let's say, 10 pixels, and like that. Okay, so in the object detections, I want you to give me the positions of the cat by surrounding the cat with something called a bounding box. So this is called bounding box. Okay, so it's pretty hard. So this is called the bounding box. Okay, in object detection, I want you not just classify an image, an entire image, but I want you to telling me where's the image. So if I have, you know, image classification problem, and then I want you, you know, to give me the locations of the object of the cat. I want to give me the bounding box like this. Okay, and we have I can do another example. Like here I have this image of a, you know, young student, and then, like, for example, okay, I want you to give me the locations of the bag, like, for example. So I want you to give me the bounding box surrounding their bag like this. So it's going to be like this, pretty much like this, and then like that, then like that. Okay, so I want you to give me something like this. Or another example, I want you to classify, or not to call it, but to detecting the person itself. So instead of something like that, I want you to give me something like this. So surrounding the person inside of a bounding box, something called bounding box, like this. And let's doing this, and then so this is what's called the object detection. So we are not just classifying an image, but we are classifying the object inside of an image, okay, etc., etc. So you get the point. So we need to, so how can we detecting the object inside of an image? Now I want you to introduce you to something called YOLO, which stands for you only look once, not you only live once. So what is YOLO? YOLO is basically an algorithm for object detections, and I believe they have, okay, so this is the example that they provide in the paper. So they can detecting, you know, the person. Okay, I don't know if you can see that. Okay, so it can detecting a person and a cat, and then a person and a dog. So it classify not just the image, but the object inside of an image. So you have horse, and then a person, and then you have, you know, car, and then you have aeroplane, and then you would have the birds, you would have a person. And so that's the point. So that's what object detection is. And to do the object detections, this is what they're doing. Okay, so I'm just going to explain it here. I have my YOLO explanations. Now let's say I have an image, right? I have an image, and this image is 448 pixel by 448 pixel. And then with this one single image, I'm going to split those image into a grid, into a n by n grid, which is n is the amount of grid. Okay, so this is the image, and then I split this image into 7 by 7 grid. Okay, I split this image 448 pixel by 448 pixel into a 7 by 7 grid. So now I have this 7 by 7 grid. So this is the first row, and this is the second row, the third row, and then it's first column, second column. So basically this is going to be a grid. Like if I'm doing it here, okay, I'm just gonna do this. Like for example, if I have, you know, a 3 by 3 grid. Okay, I want to split this single image into a 3 by 3 grid. So I'm going to do this. Let's pick red. I'm going to do this. Okay, I'm going to split this image basically into a 3x3 grid, and then like this. Okay, I'm splitting the image into a 3x3 grids. So this is the first grid, this is the second grid, it's third grid, and then this is the fourth, the fifth, then 6, 7, this is the 8th, and this is the 9th grid. So basically from one images I can get 9 new images based on my image. Okay, so that is the splitting grid. So okay, if I have a 448 by 448 image, and then I split into 7 by 7 grid, one grid has 64 pixel. Okay, so one grid has 64 pixel, which mean, like, again, this is for just for the example, which mean each of these grid would have 44 by 44 amount of pixel. Each of this image, each of the grid. Okay, now so now we get into the bounding box. Okay, I'm gonna remove this, and then I'm going to making this back. You know what, I'm just gonna delete this one, create a new one. It's going to be like this basically. Okay, you know what, maybe I should do this. Okay, I should okay, I'm going to do this. Okay, so bounding box. So in the bounding box you would have something called the center point. Okay, so there is the center point. Okay, so there is the center point, but instead of the center point I would have something some kind of a point, not point, but how can I say it? Okay, so basically this is what I'm talking about. I'm just gonna draw it. So the bounding box should be like this, right? Should be like this. Okay. Now the first x and y. So this is the coordinate of the x and y. So this is the first coordinates of x and y, and it is going to be in this place, which is going to be in this place, which is in the corner. Okay, and for the second x, like x2 and the y2, it is going to be the width and the height. So from these coordinates, we're going here into this direction of the x2 coordinates. So it's going to be x2 or the width. Okay, and then after we going here, we going down, and this is going to be the y2, or it's going to be the height. Okay, so that's what bounding box is, and this is what I'm drawing here. So this is basically the corner coordinates, and the corner coordinate is basically a pixel coordinates. So the pixel coordinates is, okay, you know that every image is a pixel, so that it basically based on that pixel. So for example, okay, you can say that this is the x and y coordinate based on a pixel. So it's going to be, you know, so the x is going to be the row and the y is going to be the column. So it's going to be in a 2 by 2. So it's going to be in the second row and in the second column. So that is the x and y coordinates inside of a bounding box. Okay. Now, okay, so to create a bounding box that so the center point of x and y that relative to the bounding box, you just need to divide the value of the x and y, the x. Okay, can I do this? I don't know if I can do this. It is not a good idea. Okay, I hope I can do this. So basically, to get the bounding box, not the bounding, but the center point of a bounding box, you need to have this coordinate, which is x here, and then the x2, which is here, divided by the 64, and the 64 is basically the amount of pixel that you have inside of your grid image. So it's going to be where is it? Where's my grid? Okay, so this is the grid. So each amount of the grid is going to have their own image. So basically, each grid is its own image, and inside of those grid, so in order to get the center point of your bounding box, which is in our case is going to be around here. So if you doing this, you can get the center point. So it's going to be around here. So this is the center point of your bounding box. So this is what I'm talking about. Okay, and then you just so you get the x, which is this, and then the x2, which is this one, and then the y, which is this coordinates, and then the y2 is going to be these coordinates, the height coordinates, and then you just dividing with the amount of pixel that you have on each grid, and then you get the coordinates of your bounding box. Now to get the width and the height that relative to the whole image, you can just your width is divided by the whole image width and the height, which is the pixel dimension of an image. Okay, so that is YOLO. Now when we create a bounding box, we are going to need a label to store the data that we have. And so remember that we have this grid, so this is going to be a 6 by 6 grid, and each of those grid we are going to have a label. Okay, so each grid has its own label. So what is the label? So the label is going to be C1, which is stands for the category. So for example, if I have this image, back to this image, what is the category that I want to detecting? So instead of this example, I have two categories, which is the bag and a person. Okay, so in the label you would have the category, and then you would have the probability, like so the probability is basically the classification part, and then finally you have the x, y, width, and the height. So it's going to be the bounding box kind of a coordinates, which is the x and y coordinates for the bounding box. Okay, like so for example, in this case I would have two categories, the person and the bag. So inside of this part I would have, okay, this is the person and this is for the bag, and for the probability it's going to be it's basically classification. So inside of this grid, is there an image of a person or a bag? Okay, so now if the probability is going to be 1, which is true, it's going to be, okay, which one that you're talking about? Okay, so you're saying that, okay, there is an image that we want to classify, but what image? And it's going to be this one. It's going to be whether the image of a person or the image of a bag. And then after you give me, okay, like for example, okay, so this part is going to be image of a person. Okay, so the person part is going to be true and the bag part is going to be false. And then you give me the bounding box coordinates that would give me, you know, this box, that can give me this box for the person, and that is the label that we need inside of the YOLO algorithm. And again, each of this grid has its own label. So basically what happening is we split the image. Okay, I'm gonna do this. So basically, first of all, we split the image. Okay, and each of this image has its own label. So this image has its own label. So I'm not doing that. Okay, so this image has its own label. So let's call this label 2. So let's call this label 1, and then let's call this label 3 until label 9. So in the previous classifications problem, one image has one label. Like for example, in this cat image, which means, well, the label is the cat itself. But inside of a YOLO algorithm, we need to split the image, and then each of the grid inside of this image became a new image, and those new image has its own label. So based on one image, we could have a lot of labels. Like for this example, we could have 9 labels for one images. And inside of this one images, it will contain whether it's the object and the bounding box coordinates, and the coordinate is going to be x, y, width, and height. Okay. Now we have this kind of a label. Okay, we have this kind of a label. What about the loss function? Okay, what about how can we evaluate this kind of label? So this is the YOLO loss, and I know it's so it's a little bit confusing, but I think it is not that confusing actually. So if you go to the YOLO paper, this is the loss function that they provide. So this is the loss function, and it is just the same thing with this one. Okay, so first of all, inside the YOLO loss, okay, I'm going to do this. I want to doing this. Okay, so basically the YOLO loss is divided into 3 parts of loss. So first is going to be the classes loss, and then we have the probability loss, and then we have the bounding boxes loss. Okay, so first of all, so this is the label that we have, right? So we need to calculate the loss for the C1 for the categorical, the loss for the probability, and the loss for the bounding box. So that is what happened inside of the YOLO loss. So this YOLO loss has three loss calculations. So first of all, okay, I'm just gonna do this. So first of all, they would have something like this. So this is going to calculate whether the object exists or not. Like for example, in this part, in this cat, cat part, which grid image that say, okay, I have the object and I don't have the object. Okay, so what do I mean by that? Like for example, okay, so for the first grid, for this image, does this grid has the object of cat? Well, the answer is no. Okay. So it's going to be no, it does not have the object of cat. And then we go to the second grid and asking, okay, does this image, not image of a grid, has the object of cat or not? Well, the answer is yes. Actually it has, because it has the ear. Yes. And then of course this one is no, this, and this one is definitely yes. Yes, this one has. Yes. Okay, so you get the point. So that is what this part is. So whether the object exists or not. Okay. Now, if the object exists, we can get into the loss of this part. So this is going to be the loss if the object exists, and we are going to calculate the box, the confidence, and the class. Okay, now so after we decide should the object exist or not, we need to calculate three things, which is the box, and then the confidence, and then the class. So first of all, so this is the probability or the confidence basically. So if the object exists, we can using this formula, this particular formula. If the object does not exist, we can using this formula. Okay, and now for the probability of if you having a multiple category, we can using this. So if this is if this is so this part, this confidence part is going to be either 0 or 1, because it's going to be, okay, does the object exist or not? And if this part is going to be 1, which is true, it's going to be, okay, so there is an object inside of this image. We can get into the class part, and it's going to be, okay, what kind of image? So for example, if we again using this example, okay, what kind of image? Is it the bag or is it the person? So we can calculate the loss using this part, and it's going to be this part. Okay, so this is for the object, and since in the non-object, and okay, so we are calculating this part if we have the object, but if we doesn't have the object, we don't need to calculate it. Okay, and then the last part is going to be the width and the height, and so this part, this particular part, is going to be calculating the width and the height that we have. So okay, so and remember, the loss is the difference between the prediction and the true label. Okay, so in this case, like for example, if my neural network predicted that I have, it's going to be x, y, width, and the height coordinates, and so each of those coordinates that being predicted by the neural network is going to get calculated with using this loss function. Okay, so the x of I is going to be the basically the prediction, and the x of I hat is going to be the label. So this is how you calculate the loss for the grid value, and the grid value has 4 value, which is the x, y, width, and the height. Okay, now I want to mention another thing, like, okay, for example, if I have something like this, which mean I have two category. 2C, let's say 2C stand for two category. So that means the label that I would have would be something like this. So it's going to be C1 and C2. So this is the label, and C1 stands for the bag, and C2 stands for the person. Okay, and then I would have the probability, so whether the object exists or not. And finally I would have the x1, not x1, oh yeah, x1, and then y1, and then w or x, w1, and then the height 1. So this coordinates is going to be for the C1, and then I would have x2, and then y2, and then the width of 2, and then the height of 2. Okay, so this part is going to responsible for the bounding box for the C2, and this part is going to responsible for the bounding box for the C1. So each category would have its own label. Like, so for example, if you have two category, each grid would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, wait, what? It's gonna be 8, yeah, 11. So if you have two category, you would have 11 value for each, for your label. Okay, so the label is going to be 11, and it's going to exist, and the label is going to exist on each of the grid split images. Okay, so that is what YOLO is doing. So for example, let's say okay, let's do this. Like, for example, bring back this. If this grid say, hey, grid number 5, basically grid number 5 said, hey, I have the object, I know what object it is, and I have the coordinates for my object X. So I'm going to give you what is the object that I have, which is coming from the C part, and then what is the bounding box, which is coming from this part. And finally, from those informations, we can get the coordinates, which is the X and Y coordinates, and then the width and the height coordinates, and also the name of the object, which is in this case is going to be cat. So this is what YOLO algorithm is doing. Okay, and if you're still confused, don't worry about it, because it is such a convoluted concept. I'm not gonna lie. but it is actually pretty simple. So, and we are going to implement this algorithm into programming in the next segment. Okay, so now we get into the implementation of the YOLO algorithm. So we go to, the usual Google Colab, and then let's call this file YOLO from scratch. Okay, so let's just go into it. So first of all, we need to create the model. Okay, and in order to create the model, we need to import torch, and then we need to import torch.nn as nn. Okay, so in this YOLO model implementation, we are going to have, it's going to be the implementation of YOLO model. Implementation of YOLO model. So, and we are going to add batch normalization into the model. Okay, so before we create the model, we need to have a configuration basically. So let's create a variable called architecture configuration, like that. Okay, and inside of the configuration, we are going to have so we need to get the list of, so we need the list for the structure. I'm going to make a list of so it's going to be the kernel size, and then it's going to be the filter output, and then it's going to be the stride and padding and the padding. Okay, so let's create, and we basically going to replicate this architecture, which is an architecture that you can find in the YOLO paper. Okay, so first they have the convolutional layer for, and the convolutional layer has 7 by 7, and then it has 64. So this 64 is basically the filter, the amount of filter, and then the stride, and then if you can see like this tiny number, this tiny number 3 here, or tiny number 3 here. So that is basically the padding. So we are going to add that. So basically we have 7 by 7 of a filter, and we have 64 amount of filters, and then we have the stride and then the padding. So basically this is what we do. Oh my god, really? Okay, so remember we have 7 by 7 kernel, and then 64 filter output, and then the stride is 2, and then the padding is 3. Okay, now we need to have I want to have this M, and this M is stands for stands for max pooling layer, because if you see at the architecture, they are using the max pooling layer here. Okay, and then next we are going to have 3 by 3, and then 192, and then they're going to have one stride basically, and one padding, one stride and one padding. So it's going to be 3, and then 192, and then one stride and one padding. And then we also use the max pooling layer. They perform the max pooling layer here, and then we are going to have 1 by 1. So it's going to be 1 by 1, and then I don't know if you can see it. 1 by 1, and then 128, and then it looks like they have one stride and 0 padding. Okay, and then after that they have 3 by 3, and then 256. It's going to be 3 and then 256, and then they are going to have one padding and one stride, and then they have one kernel size with 256 again. It's going to be 256, and then they have one stride and 0 padding. Okay, and then they are going to have 3 size, and then where is it? Oh, so this is 3, no, this one, and then 512, basically 512, and then with the stride of 0 and no, stride of 1, and then the padding of 1. And also, so you can actually playing with this value, because this is, this is the parameters that we are going to use, so you're not really needs to following this architecture. You can modify this architecture, and that's what we are doing. We are going to add the batch normalization at the end, and then after that what we have, we have the max pooling layer. So it's gonna be max pooling layer. Okay, and then after that we have where were we? So okay, so we have something like this, and you see this times 4. So we basically repeat this particular process 4 times. So this is what how you can do it. So we're going to create an array, and inside this array we are going to have the tuple, and the tuple is going to be 1, because this is 1, and then 5, 12, 5, 12, and then the stride of 1, and then padding of 0, and then we can have another one, which is for this one, which is 3, and then 5, 12, no, 256, 256, 1, 3, and then we have 3, and then 5, 12, basically 5, 12. Wait, no, it's 256, not 250, 56, and then we are going to have one stride and then the one padding, and then we repeat this process 4 times. So the outside value is basically how much, not how much, but how many times those tuple should be repeated. I know you cannot see that, so should be repeated basically. Okay, and then we are going to have what else, 1 and then 512. It's going to be we have comma, it's going to be 1 and then 512, and then we start of 1 and then padding of 0. Then we have where is it, 3 and then 1024. We have 3 and then 1024 with the start of 1 and the padding of 1. Okay, and then they are going to apply the max pooling layer, the M, and then so we finish made this part. Now we needs to make this part, and it's going to be 1. No, it's going to be repeated 2 times. So we are going to create an array and then the tuple, and then it's going to be 1 and then 512, and then with the start of 1 and padding of 0. Then they are going to have 3 and then 1024. It's going to be 3 and then 1024, like that, and then the start of 1 and then padding of 1, and then repeat those process twice. Okay, like that. And then they have this 3 and then, so they have 3 and then 1024 with the start of 1 and the padding of 1. Then they would have this one again, so it's basically 3 and then 1024 and then 1024, but they have the start of 2 and the padding of 1. Basically that's what happened. And then we have the last layer, the last convolutional layer is going to be 3 and then 1024 with the start of 1 and then padding of 1, and 3 1024 with the start of 1 and the padding of 1. So yes, that's the configuration architecture that we are going to have. And you know what, let's try to run this if we can see any mistake. So there's no mistake, so let's just continue with this cell. Okay, you know what, I'm going to use a new cell. So this new cell is going to be the model itself, and so we need to create the class, and then let's call this CNN block, and it's going to be, we need the end up module, and instead of another module we need to define the init function, and it's going to be self, and then in channels, and then the output channels, and then we are going to use the quarks. Okay, like that. So and then we need to create the super function. So super is going to be the name of the class that we have, and then self, like that. And then we need to have the init method or the init function, like that. And then now we can create the solve.convolutional is going to be nn.conv 2d 2d no, and convolutional 2d, and it's going to be the in channel, and then the output channel, and then we need to have the bias is equal to false, and then we are going to have the quartz. Okay, channels like that, and then we need to have the batch normalization. So batch norm, so we are going to add batch norm. So as you can see, like inside of this architecture, they are not applying the batch normalization, and we are going to apply the batch normalization in our architecture. That's basically what happened. So self.batch norm is going to be batch norm 2D, and it's going to be the output channel, and then we are going to use the leaky ReLU, and it's going to be leaky ReLU. That's going to be 0.1. So if you forgot what leaky ReLU is, wait a second. Okay, so this is what leaky ReLU is. So we are going to have the value between 0.01 and 1, and in our case we are going to have the value of 0.1 and 1. Basically, that's what happened. Okay, so that is the init function. Now we have to find the forward, and it's going to be self.input, and we are going to return the self.leaky ReLU of the self.batch-normalization, and then self.convolutional, and we are going to get the input like that. So basically we are going to have the input going into the convolutional. So basically the input like around here is going to get into the convolutional, and then we're going to add the batch normalization. So it's going to be around here. Okay, it's going to be around here, the batch normalization, and then we apply the leaky ReLU to get the nonlinear distributions or nonlinear function out of it. Okay, so that is the forward function. Okay, so that is the forward propagations basically. Now that is the CNN block. Now we need to create the YOLO class basically. So it's going to be class of the YOLO v1. Okay, and it's going to be, we are going to use the nn.module. This is the same thing, and then okay, I don't know if you can see that. Then we're doing that, and then we need to have the init function, and it's going to be self.inChannel, and the default is going to be 3, and then we have the quartz. Now we have this super function, and it's going to be the name of the class. It's YOLO v1, and then self, and then apply the init like that. Okay, so now we're looking at the architecture. So it's going to be self.architecture, and it's going to be architecture configuration. Okay, so this is the configuration that we've created here, and then we are going to use the self.inChannel. In channels is going to be in channels like that, and then self.darknet is going to be self.___ create convolutional layers, and then we are going to apply the self.architecture. Okay, self-architecture based on the architecture configurations. now we need to create a self dot this part, this, okay, I don't know if you can see that. We are going to create the not create but adding this fully connected layer. So it's going to be self dot fully connected layer, and it's going to be self dot create the VCS, and we are going to have the quarks value like that. Because okay, so we're going out from this init function, and then we're going to create define function dot forward, the forward propagations basically. So it's going to be self and then input, and inside of this part we are going to, so the input is going to be self dot darknet of the input. So darknet is going to be based on this create convolutional layer, and the convolutional layer is going to be based on the architecture configurations. Okay, and then we need to return self dot VCS, and then torch dot flatten, because remember in the fully connected layer we are going to flatten out from a lot of dimension into one dimensional data. Okay, and then what we are going to flatten? Well, we're going to flatten the input, and we are going to have the dimension of 1 basically. That's what happened here. Okay, and then we need to define the create basically this one, create convolutional layer. So let's just do this, and it's going to be self, and we are going to input the architecture like that, and inside of this architecture we have layers like this. It's going to be an empty array, and then in channel is going to be self dot in channels. So okay, so let's create the architecture. So for x in the architecture is basically okay, so if the type of the input that we have is equal to tuple, okay, not tuple but tuple, okay, we are going to have the layers plus, oh my god, plus the CNN block, and the CNN block is going to add the in channel, and then it's going to be x of the first index in the input, and then the kernel size is going to be x in the 0th index, and then the stride is going to be like that, x in channels, and then in the second index, and finally the padding is going to be x in the 0th in the 3rd index. Okay, okay, so what is going on inside of this quite complex program? So okay, so we are going to inputting this architecture basically, okay, this architecture. So when we do the the for in architecture, we are going to loop the inside of the architecture. So basically we are going to have loop this one, and then this one, and then this one, and then this one. So we are going to going through all of this, and then Like for example, in the first iteration, which is going to be this one, right? So in the first iteration we are going to meet this one. And okay, so if the input is going to be tuple, so here we have a tuple. Okay, this is a tuple. If the input is going to be a tuple, we are going to add into the layer here. So where is the layer? So we doesn't have the layer yet, because we are going to create the layer. Basically we are going to create the layer. So inside of the CNN blocks, okay, so what is the CNN blocks? This is the CNN blocks. And what is going on inside the CNN blocks? We are going to have the input channel, the output channel, and then we are going to have all of these configurations basically, because in CNN blocks this we are going to, so basically we are going to have the in channel here, okay, and then the output channel here. So in channel, so what is the in channel? So this in channel is going to be in the X is going to be this, which is basically it's not like so the input channel, okay, so the input channel, like okay, how can I explain this? So in the first iteration we are going to have, you know, a regular image. So the input channel, which is the amount of dimension that a regular image has, which is 3, which is the RGB. So in the first iteration we are going to have, you know, 3 amount of channel, and this is why we have this in channel is equal to 3, because this is based on the RGB image dimension that we have. And then we get into the this one. So what is this one? So this one is basically the output channel, which is going to be this one, not this one, okay, 64, because based which is based on the on this configurations. So we have the filter output, okay, so that is the output, filter output, which is the output channel. And then we have the kernel size in the 0th of X dimension. So this is basically the filter size, or the kernel size. Okay, so this is the kernel size, which is going to be 7 in the first iterations, remember. And then the stride is going to be this one, okay, in the second index. So this is the stride, and then finally the padding. We need to have the padding inside of this. So this is basically what happened. Okay, that is basically what happened. And again, in the first iterations we are going to check, okay, if it's a tuple or not. If it's a tuple, well, we are going to add an information into our layer array, and those information is going to be based on the input channel, the output filter, the output channel, the kernel size, the stride, and the padding based on the input. And the input is going to be the loop that going through these architecture configurations. So that is what happening. Okay, so that is what happening inside of this configuration, not configuration, but process basically. Okay. What else? CNN block. Okay. Wait. Why did I do that? Should be like that. Okay. So I can do this. Why not? Is it more readable? Okay. So, and then after we go out, and then the input channel is going to be x of 1 basically. So because we need to tracking what's the input channel. So in the first, in the first image, the input channel is obviously going to be 3-dimensional because it is going to be RGB image. Okay, so how can I write? Okay, I'm going to do this. In the first iteration, the input channel is equal to 3 because of the RGB image format. Okay, and now the input channel is going to change because we are finished with the input from the original image. Now we need to get the input from the filtering image. So it's going to be the output of the filter, because if you remember the process in the convolutional layer, where is it? Basically, the amount of layer become the amount of channels that you are going to have in the next iterations. Okay, so this is. So remember, when we have 10 filters, we are going to have 10-dimensional in the next data, and this is why the input in the next iterations, the input channel needs to be the output of the previous layer. So the output of the previous layer has 64 filter output, or they have 64 filter. So that's why we need to record the input channel for the next iterations. So this is like basically the first iteration. Okay, and then as you can guess, in the second iteration we are going to have 192 amount of filter. So the input channel in the third iteration is going to be 192. Okay. So first iteration, not this first, but the second iteration, the input channel is going to be 64 because that is the output of the first iterations. And in the third iteration, the input channel is going to be 192 because that is the amount of filters that we are applying, and so on and so on. So that's why we need to keep tracking the output filter so that we can get the correct input channel. Okay, and then we can get out of the if function and to create the elif. And so now we have the type of tuple, but if we have the type of string, okay, so what is the string? The string is this one. And what is this one? It is for the max pooling layer. Okay, so it's going to be layers, and we are going to add into those layer a max pooling layer. And so it's going to be like this: nn dot max pooling, max pool 2D. So with the kernel size, we are going to have 2 by 2, and then the stride is going to be also 2 by 2. Oh my god, 2 by 2 because based on this architecture, they have 2 by 2 with the stride of 2 for the max pooling layer. So that is basically what we are doing. So this is the M part. Why do I have a red color? I forgot to close the max pooling. Okay, so that is for if we have the string. Now we need to have the elif for the type of a list. Okay, so basically we are going to have this kind of list. Okay, so this is the list that what I'm talking about, what I mentioned, and we need to consider basically this value. So basically how many times at the tuples inside of this array or list is going to get calculated or repeated. Okay, so in every so if you can see in every in every list they have two tuples. So we can doing this is conv1 is going to be the first tuple, and then in the conv2 is going to be the second tuple, which is the first index, and the number of repeat is going to be x, which is in the in the second index. So it's 0 index, and which is the convolutional one, and then in the first index is going to be the convolutional 2, and then in the third index is going to be the how many we are going to repeat those tuple. So it's going to be second, like that. Okay, now for underscore in the range of, well, how many times it repeated, number repeats, is we are going to have the layers, and then we are going to have we basically doing the same thing with this. Okay, so this is what we're doing. We're going to call the CNN block, and inside the CNN block we are going to have the conv1, not the conv1 but in channels, and then we're going to have the conv1 in the first index, and then we're going to have the kernel size, and it's going to be conv1 in the 0th index, and then we have the stride of the conv1 in the second index, and then the padding of the conv1 in the third index. Okay, and then that is for the first convolutional. Okay, why did I get red then here? CNN block layer, CNN block, I don't know what, oh, like that. Okay, so that okay, so we finished this part. Again, we're doing the same thing with this. So the the stride index is in the second index, the padding is in the third index, the kernel size 0 index. So basically we are going to take all of this value. So this is the padding, this is the stride, it is the filter amount, you know, and this is the kernel size, etc., etc. And then after that we can create a new layers, and the plus like this. It's gonna be like oh my god, like this. Then we do the same thing. It's gonna be CNN block, and instead of the CNN block we are going to have the convolutional one, and then the convolutional 2 in the first index, and then the kernel size is equal to the conv2 is going to be 0. Okay, and then the stride is going to be the conv2 of the second index, and then the padding is going to be the conv2 in the third index. Okay, so why do I put convolutional one here? Because that is the output. Remember here. So where is it? Okay, so the input of the first part here, which is this part here. Okay, this particular part, this part. So it is going from, so the input for this part is from the calculation in this part, and we don't know. So and it's going to, so we are going to get the input from where is it? From this, the input channel, which is being recorded here. Okay, so this input channel is going to be going inside of this. Okay, but as you can see, after we going from here, we go to here, and in this part, the obvious, you know, the obvious input is going to be from the output of this part. So the output of the convolutional one is going to be the input for the convolutional 2 in this particular part. Okay, if that makes sense. So okay, so I hope that makes sense. Now, and again, we need to channels. We need to record the channels that is going out from the conv2. Okay, so we need to record the output from this convolutional 2 to become the input for the next iterations. Okay, and then what else? Okay, we can going in outside. Where is it? Okay, I'm going to do this. Oh my god. So we finish these channels, and then we can going outside of the function to and return the nn dot sequential of the layers. Okay, so we are going out, and I'm going to make sure that we are not in the for loop here, because okay, where is it? Okay, I'm going to make sure we are not inside of the for loop in the return part. Okay, so we return the sequential because it is going to be a sequential process, like this. Okay, so we are going in a sequential, you know, calculations. We come from here and then just going through here from the input, and then we going just blasting through the process into the output. Okay. Now, okay, I don't know where's the okay, so I'm assuming this position is the class, and then okay, I'm going to press tab and then making another function. So another function is going to be the last part of this architecture, which is this part, the fully connected layers, and it's going to be create the VCS here, which is based on the where is it? Something that we've created before. Wait, where is it? Create VCS. Oh yeah, here. So we're going to create this function here. Basically, that's what happened. So we are going to have a self, of course, and then we have the split size, and then the number of boxes, and then the number of classes. Okay, so it's going to be S, and then B, and then C, which is based on the split size, and then the number of boxes, and then the number of classes. Okay, number of classes. Now, in the original paper, in this paper, we should have this, 10, 24, and then we basically going to have an n-dot linear of 10, 24 multiplied by the S by S, which is the grid, and then we are going to have 40 and like this. Okay, and then we are going to have the leaky value of 0.1, and then we are going to have the n dot linear of 40, 96, and the S multiplied by SS, and then we are going to have the box number, and then 5 plus the number of classes. So this is basically what we are going to have in the original paper, but we're not going to have this because this is too much, and we only have a little resources. We only have, so we are going to use the GPU that is the Google Colab providing for us. So I think this amount of parameters is going to be too heavy, and we don't know how long it's going to take for us to train. So we are going to have a small version of the fully connected layer. So I'm going to have the flatten, but if you have again, if you have a GPU in your computer, you can use this architecture that is based on the paper. But for now, we are going to use the small version of the the fully connected layer. So we are going to have the sequential. Okay, and instead of sequential, we are going to have, of course, we need to flatten the input data, because this is going to be in the fully connected layer. And then we are going to have the nn.linear, and we are going to have 1024, then multiplied by the amount of the split size, multiplied by the amount of split size, and then we are going to have instead of 4096, okay, instead of 4096 we are going to have 496. Okay, so we are going to create a smaller linear function. So this part is basically, okay, I'm gonna make this part. So this part is basically the amount of neuron, okay, neuron, and we are going to use, you know, less than 500 neurons in our case. And then we need to have an dropout of 0.0. Okay, so I'm not explaining dropout yet. So the dropout is basically it's like we flip a coin, and then we decide whether it's whether the coin is going to be you know, a close or open. Okay, how can I explain this? Dropout is basically like, for example, you have 10 neuron. If we are applying 10 neuron, okay, if we applied dropout, so if we are applying dropout, we basically choose to whether we turn off some of the neuron. So if we apply the dropout, we probably going to have, you know, 7 active neuron from 10 neuron or 8 active neuron that we are going to use, and the other, you know, neuron is not going to use, it's not going to, you know, connected to the input. So that is what dropout is. And then we are going to apply the Ligier value, of 0.1, and then we get to the nn.linear of the input, which is for 6 like that, and then we are going to have s times s multiplied by the c, which is the amount of the classes plus the amount of the boxes times 5, like that. Okay, because we are going to, you know, split our image into the SS grid, so the amount of grid is going to be basically as this, and that's why we are applying this S in here. So S is split size, which is, you know, the grid split that we are going to have. Okay, so that is a lot, and let's try to run this if there is a mistake. Oh, there is no mistake. Good. So that is the model and the architecture. So this is the model and this is the architecture, or basically it's just the same thing at this point. And now, next, okay, what do we want to have? Okay, now let's create the loss part, the loss function, the loss calculations. It's gonna be like that. It's gonna be loss, and I'm going to do this so that we can see much better. And then okay, so for the loss, we need to import torch. Okay, we don't need to import torch because we have torch here. Okay, so let's start. Okay, so remember how many loss the YOLO have? So it had 3 loss, okay, and it has 3 loss. It has, and so the first loss is the box coordinate, and then we are going to have the object, loss, and then we are going to have the class loss. Okay, box coordinate loss. So okay, so in the object loss we are going to have 2 kind of loss. So it's going to be if there's an object, or there's no object, like that. So we are going to create all of this loss. Okay, so let's create the class called the YOLO loss. Loss like that. YOLO loss. And we are going to input the module, and so we need to create the init function, and it's going to be self, and then as we are going to use 7x7 straight or split, so we are going to have 49 images, basically 49 images based on 1 image, and then we are going to have 2 bounding box, and then the class is 20. Okay, so because in the paper they actually have 2 bounding box. Okay, let me see if I can find it. Limitation, yeah. I don't know if I can find it actually. What if I what if I do that? What if I do this? Okay, so here is the value that we are going to use. So they are using the stride of 7, not the stride, but the grid split, the split of 7, and then the amount of bounding box is going to be 2 for 1 image, basically, and then the class is going to be 12 because they are using the Pascal VOC dataset. So you don't know what Pascal VOC dataset look like. Is going to look like this. So this is the Pascal VOC dataset, which is a dataset that is okay. can I open this? So this is what the Pascal dataset look like. So you have, you have dog, you have a car, you have a person, you have train, you have plane. So they're using this dataset, and we're also going to use this Pascal dataset. And based on the Pascal dataset, they are going to have 20 amount of category. Okay. Now, so there is the init function. Now we need to have the super function, and let's call the YOLO loss, and then self, and then we are going to have init, and like that. Now we are going to use the mean square error. So it's going to be self.mse, and it's going to be nn.mse loss, and it's going to be reduction is equal to sum. Okay, let me see if I can find this for iron final prediction. So this is the training. Okay, so this one. So we optimize for sum square error, which is basically the MSE loss. Okay. If you forgot what the MSE loss is look like, is where is it? Yeah. So this is what the mean square error loss look like. Now we are going to use that. And okay, so we need to have self.s is equal to s self dot amount of bounding box is going to be bounding box. So s is going to be grid split amount, the amount of bounding box. Okay, so in the paper of YOLO, they are actually using 2 bounding box. So the output of the prediction is going to be 2 bounding box, and based on those 2 bounding box, they are going to calculate which one is better, and we are going to take the one better, the one the one that's better basically. And the way they do that to compare which one is better, they are going to use something called intersection over union. And yeah, I'm not yet explaining about the intersection over union, and I'm going to explain it in the next part. But now all you need to know is they are basically going to have 2 bounding box. Now we have the C, which stands for the amount of category for our data. Okay, and then we need to have something called self dot lambda of no object, and then we are going to need something called lambda that has the coordinates. Okay, so what we need, so what is this lambda? So if you see in the YOLO loss, if you look at the YOLO loss, you're going to have okay, so you see this lambda coordinates and the lambda no object. Let me see if my loss is where is it? So this is the YOLO loss. Okay, so I don't think I'm writing it in a better way. Okay, so basically, if you see this coordinates, So you are going to have the coordinates of the bounding box when you have the objects, right? And if you doesn't have the objects, you don't have the coordinates. So we are going to add the lambda value in the image that has the object a bigger value. So we want to emphasize that, okay, so this part, this image is important by adding the amount of lambda, by adding this amount of lambda. And for the lambda that has no object, well, it has no object, so it's like we don't care about this part, we don't care about this image. Basically, that's what I'm saying. So we need to emphasize how less important this image has this, because in this image it has no object. So basically we are making it less important since it doesn't have a object. And then in this lambda coordinates, we making it more important since it does have an object. Okay, so this is what the lambda value is. Okay, now after that, that is the init, so we need to define the forward, and the forward is going to be itself, and the prediction and the target. Of course, we are calculating the loss, so of course we need to get the prediction value and the target value, and then calculate this value to get the loss value. So the prediction, okay, so first of all, the prediction shape is going to be the batch size. Okay, it's the batch size, and then S multiplied by S times the C plus B multiplied by 5 when multiplied by 5 when being imputed. So okay, can I find that? Let me see if I can find it. It's going to be in the loss part. Inference, not that one. Oh, it's a okay. These predictions are encoded as an S times the amount of bounding box multiplied by 5 plus the amount of category. So we are using these steps in this part, the prediction. Okay, so the predictions, and this the predictions. Okay, so the predictions is going to have the predictions dot reshape of -1, and then self dot S, and then self dot S, then self dot amount of category, and then self dot amount of bounding box, then multiplied by 5. Okay, and after that we need to calculate the something called IOU, or intersection of reunion, for two bounding box for two bounding box there is coming bounding box from the prediction. So the first IOU is going to be okay, intersection over union. Okay, I'm going to create the function after I'm explaining the IOU. I don't know why I'm getting into the loss before I'm explaining the IOU, but I'm going to explain the IOU basically. So across every dimension, it's going to be 21 until 25, and then the target is going to be 21 until 25, like that. So that's the first IOU. So the second IOU is going to be the same intersection over union, and it's going to be prediction of, it's going to be 26 until 30, like that, and the target is going to be 26 until not 26 but 21 until 25, and the IOUs is going to be torch dot cat, and it's going to be the IOU of the P1 dot unsqueeze of the 0, and the IOU of the bounding box 2 is going to be dot unsqueeze like that, and then we're going to have the dimension of 0 to keep the dimension. So okay, so in the prediction and the target part, okay, how can I, okay, I'm going to do this now. The label, this label, okay, remember this label, do you remember this label? So we are going to have 20 categories. So basically we are going to have, so this is the C1, and then C2, and then C3, then C4, C5, C6, C7, C8, C9, and then C10, then C11, and then C12, and then C13, and then C14, and then C15, and then C16, C17, C18, C19, and then C20. So this is the amount of category inside of the Pascal VOC dataset. It has 2 category of an image. Okay. Now, after all of that, we are going to have this this P right here, which is stands for the probability, and it's going to be probability, and then we are going to have the bounding box. The bounding box is so it's going to be X, and then Y, and then the width and the height. So this is the bounding box, and as you can see in the, so the the target, which is the true label. Target is basically the true label. So this is the target. Okay, so this is the target, and in the in the 21 until 25 indexes, which is this part, is basically the bounding box. Okay, so this is the 21 until 25 index, and so this is the true label, like this. But in the prediction label, we are going to have two bounding box. So it's going to be x, and then we have x2, and then y2, and then w2, and then h2. And this is why IOU bounding box. So because this part is the for the first bounding box, which is this part, and this is why we are calculating the predictions between this part, which is this part, okay, and the target, which is the true label, which is this part. And then in the next bounding box, we are going to have 26 until 30. Okay, this 26 until 30 is basically, I don't know if you can see that, it's basically this part. And then we are going to compare this bounding box, this second bounding box, with the label, with the true label. And this is why we have 21 until 25 here, which is in the target, which is in the true label. Okay, so this is that is what we are doing here. Okay, now okay, so we need to take the box with the highest IOU out of the two bounding box or predictions. Okay, so it's going to be IOU maxes, and the best box is going to be torch dot maximum value, and it's going to be IOUs, and it's going to be dimension of 0. Okay, now we need to have something called exist box, and it's going to be equal the target, and it's going to be 20 in the 20th index dot unsqueeze of 3. Okay, so what is going on here? So this is basically the object exists, object of I. Okay, if we have a box, does that box has a target? So what is in the 20th index? In the 20th index is the probability. Okay, and this is why we are targeting the 20th index, because okay, if it exists or not, if in this probability they say okay, it doesn't have in an object, well, we don't need the bounding box. But if the probability said it has an object, we are going to use that bounding box. Oh my god. So I'm sorry about that. Now we need to find the box coordinates loss. Okay, so the box coordinate loss is going to be this part. Okay, this part. Now I don't know if you can see that. So okay, first of all we need to set boxes with no object in them to 0, because we only remember in the previous one we have two box. Okay, so we are going to take the one of the two. Basically that's what happened, and the prediction which is the one with the highest IOU like this. Okay, so we are going to have the box prediction is equal to exist box multiply by something like this. So the best box multiply by the predictions like that. And what is the predictions? The prediction is 26 until 30 plus 1 minus the best box multiplied by the prediction of something like this, and then something like that, 21 until 25. Okay, so what is going on here? Basically what is going on here, remember in this part we basically going into the probability part. So if the probability okay, I'm going to do this. If the probability is 1, means basically the object exists, mean there's an object, okay. I'm going to do this. If probability 1, there's an object, and if the probability is 0, means, well, there is no object. Object like that, there's no object. So in this part, so we are going to get the exist box. Okay, exist box. If we get, if we get 0 in this exist box, we are basically going to multiply the exist box, the second part, the second bounding box, with the amount of 0, and it would make this box is is gone. So it's not the box prediction anymore. But if the exist box is 1, we are going to keep this one, and we are going to ignore this one, basically, which is ignoring the first box. Okay, so that is what's going on in this part. Now let's see if I made a mistakes. Should be tuple, because it is a multiplications for the for this part. Okay. Next we need to have box targets, and it's going to be the exist box multiplied by the target. And okay, what is the target? So the target is again in the true label, and it's going to be 21 until 25 indexes, in the index of 21 until 25, like that. Now I'm going to do this. Okay, now we need to take the so based on these calculations, we need to take the square roots, this part of the of the width and the height in the bounding box coordinates. So we need to take the square root. Take the square root of the width and the height of the box. So it's going to be box predictions of the 2 until 4, and it's going to be torch dot sign of the box prediction. It's going to be like that, and then multiply by the torch dot square root, like that. Okay, I don't know if you can see that. The square root value of the torch dot the absolute value between the box prediction, that is from 2 until 4, and then plus d1e plus 6. So this is the epsilon value to prevent that we have zero in the square root calculations. So what is 2 until 4? So what is this? So remember that in the box, okay, so in the box prediction, remember in the box prediction, so the box predictions will have box prediction is going to be, well, the predictions box, which is x, and then the y, and then the and the width and the height, right? And when we want to calculate the width and the height, we just needs to take basically these two, and that's why we are using this indexing to take the width and the height, because we want to calculate the square root. We want to calculate we want to perform this part of the calculations. Okay, this part of the calculations. Now that is for the box prediction, but with the box targets, it's going to be just the same thing. It's going to be 2 until 4, because we want to take the width and the height, and that's going to be torch dot square root, the square root of the box target of the oh my god, of 2 until 4th, the width and the height. Okay, now the box loss is going to be self dot MSE, which is the mean square error, and it's going to be torch dot flatten between the box prediction, and we want to have the ndim of -2, and then we want to have torch dot flatten of the box target, and we will need to have the n dim as also -2. Okay. So that is for the box coordinates. Now we need to calculate the object loss, the loss for the objects. Okay, so this part, okay, the box coordinates part is okay, where is it? Where's the calculations? Where's the okay? Is basically this part, okay? This part is basically this part, and now we are going to for the object loss. Okay. So for the object loss, we need the prediction box, because okay, inside of the prediction box, remember that we have, so prediction box is going to be the confidence score or the probability score for the box with the highest IOU. So the prediction box is going to be something like this. It's going to be best box, which is the box that has the highest IOU multiplied by the prediction. So what is the prediction of the box? It's going to be 25 until 26 plus 1 minus the best box and then we multiply it by the predictions. 20 until 21. Okay, that is for the prediction box. So now for the object loss, we have the self.mean square error, and we are going to have torch.flatten the x-axis box multiplied by the prediction box, like that. And then we have torch.flatten of the axis box, and then multiply by the target, and it's going to be 20 till 21, which is you know, the probability one, the probability index, like that. Okay, so that is the object loss if it has an object. But what if it doesn't have the object? So it's going to be an object loss part so we are going to have no object is equal to object loss value. The loss value is going to be the self.mean square error, and it's going to be torch.flatten, and we are going to flatten with 1 minus the exist box multiplied by the prediction box, and it's going to be 20 until 21, and then the start dimension is equal to 1. Oh my god, what is this? Dimension is equal to 1, and then we go from there to should be like this, should be like that. Yep, and then like this. Okay, then torch dot flatten, it's going to be just the same thing, exist box, and then multiply by the target, exist box multiplied by the target, and the target is going to be 20 until 21, and it's going to start dimension, it's going to be 1. Should be like that, and I have too much tuple. Targets, not target, okay, what is this? Flatten, torch flatten, exist box. Oh, start dimension. Wait, what is this? Sum.mse, what is this? Red. I don't know what this is. Red. What is? Wait, let me see. Let me check. Flatten and then exist box. Then the predictions and then the targets. Like that. Do you like that? Like that. Okay. The indexing problem. Okay. So there is the object. And then so again we are going to have the object loss, and we are going to add the number of the self.mean square error. That's going to be basically the same thing with this, so we can just copy this like that. But for this part it's going to be 6, because yes, 45, 46, and 1, okay. For the object, so this is basically this part, this probability part, okay, that we are calculating. So okay, so where is it? It basically this one, the probability one. Okay, so if it has an object or not, basically. So that is what we are calculating, this one. That is for the object. Wait, let me see first. Okay, so okay, to make it clear, this okay, so this part, where is it? I'm going to make it like this. Okay. Okay, so this part, the object loss and the not object loss, is going to be this part. This part. Okay. So if the object exists or not, and we can calculate it based on this part, if the object is exists or not. Okay. And if in the paper, it's going to be it's going to be this one. So these two, as you can see, this one has the object and this one has no object. So this is what we are doing here. Okay, now what we need to do is we need to have the loss for the classes, which is the last part here. So let's create those. So it's going to be the loss for the class, class loss. Okay, so let's make this bigger and okay. Now for the class loss, we are going to have the self.mse, and inside of this MSE we are going to have torch.flatten, and it's going to be exist box multiplied by the prediction, and exist box predictions until, well, the amount of category that we have in the VOC Pascal. In the Pascal VOC dataset we have 20 categories, and this is in the first 20th index, remember. So we are going to take all of this category and then we're going to calculate the loss. Okay, all of that 20 thing, and then let's end the dimension with the -2 to keep the dimensions, and then we have torch.flatten, and it's going to be exist. Oh my god, exist. Oh my god, exist box, and then we have to multiply by the target. So what is the target? Well, just the same, it's going to be 20 until 20. Like this, like that, until 20, and we are going to have n dimensions of -2. Okay, now for the loss we are going to have self dot. Okay, so wait, what is this red thing like that? For some reason I have red again. So predictions, class loss flatten. Where's the wrong part? Make it more clear. The n dimension of 2. Is it the target? Not the target. No, it's not the target. Exists self.mse. Wait, what is where's the wrong part? That's flatten exists box. Let's close that. Wait. Okay. So for the loss, finally, we need to have self dot lambda. Okay, so this loss, class loss, is basically this one, which is where is it? The class loss. The object, which is basically this one, right? So this last part here. Now, for the entire object, for the entire loss, this is the, where is it? Okay, remember the lambda part? We need to insert all of those lambda. So it's going to be lambda multiplied by the sum of all of this plus lambda of the coordinate multiplied by the sum of all of this, and then plus this, and then plus this, and which is basically, you know, the bounding box coordinates plus the object loss and then the class loss. So it's going to be like this. So it's going to be lambda coordinate, which is this one, lambda coordinate, okay, what do I call it again? The previous one, where's the lambda? Yeah, lambda coordinate multiplied by the box loss. The box loss, which is the loss that we have here, the box coordinates, okay, which is all of this, which is the first row in the paper, okay, the box loss plus, okay, the box loss plus the object loss which is, okay, I'm just gonna finish this one first. So it's going to be self dot lambda no object multiplied by the no object loss plus the class loss, okay. So this is what we got. So it will be self lambda coordinate multiplied by the box losses, which is all of this, okay, the first two row, plus the object loss, okay, so plus the object loss here, plus the object loss, and then plus self dot lambda with no object, so plus lambda with no object, okay, multiplied by the no object loss, this one, lambda with no object with the no object loss, and then finally plus the loss class loss, and we get all of this box loss and then object loss and then class loss from all of this calculation. So for the object loss we have this no object loss, from the class loss we have this, from the object loss that has the object we get from this, and from the box coordinates we get the box loss we get from this, and that is the loss function of a YOLO. And of course let's try to run this. It's going to take a while. Invalid syntax. What do you mean invalid syntax? Flatten. Oh, so this is the part where exists box target. Oh, there's too many dot. Is that what you mean? Okay, so that is the YOLO loss. And of course we need to to finish this IOU problem. So maybe in the next segment I'm going to explain the concept of IOU, and I'm going to need to explain a couple of concepts, not just the IOU. So in the YOLO they are using something called the non-max suppression, and I'm also going to explain that in the next segment. So yeah, I hope you're waiting for me in the next segment. Okay, now let's create the data. So this is basically the data loader for the YOLO algorithm. So remember, in the YOLO algorithm we need to split the image into SNS grid, which is something like, so in the paper, so it's going to be something like this, SS grid, and okay, in this case it's going to be 7 by 7 grid. So let's create something like that. So first of all we are going to import OS, and then import pandas as PD, because we are going to use the Pytorch, and the Pytorch wants the CSV file for the custom dataset, for their dataset, and then we need to have pill and then import images, not images but image. And okay, so let's create the class for the VOC dataset. So we are going to use the VOC dataset, and let's start with torch.utils data.dataset. okay, the data.dataset, and then we need to have the init function, define init, and inside of this init function we have self, and then the CSV file that we are going to use, and then we need the image directory, the label directory, and then we need to define the amount of grid, and then the amount of bounding box, and also the amount of class or the category that we have, which is 20. And let's say transforms is equal to none. Okay, like that. So okay, now we need to create the self dot annotation, and it's going to be panda.read CSV, and it's going to be the CSV file, like that. And then we are going to have self dot image directory, which is the image directory, and then we are going to have the label directory, and it's going to be label directory, oh my god, directory, like that. And then we have self dot transform, and it's equal to transform, which is none, and then self dot s is equal to s, and then transform, like that, and self dot p is equal to p, then self dot, oh my god, self dot c is equal to c. Okay, now we need to create a function of the len of self, and it's going to be return the len of the self dot annotation. Okay, like that. And then we need to have the function for get item, like that, and then it's going to be self, and then it's going to be the index. So it's going to be label path, oh my god, path is equal to os dot path dot join of the self dot label directory, and then self dot annotation dot log of the index and 1, like that. And then we need boxes is equal to an empty array, and with open of the label path, like that, sf. So for label in f.readLines, we are going to have the class label, and then the x, and then the y, and then the width and the height. So this is the label. Like for example, if we have, we want to detecting the image of cat, so it is going to be cat, and then the coordinates of the bounding box, which is the x, y, width and the height. And it's going to be an array, and inside of this array we are going to have the float of the input of the x, not the input, but for the x coordinate, if the float of x, oh my god, the float of x is not equal to the integer value of the x, else we are going to get the integer value. So for x in label dot replace of the basic the new line. So okay, so this slash and n is stands for new line, and we have like this, and then we split the data like that. Okay, and then we're going down and have boxes dot append and inside of this box is going to be class label, and then the coordinates of the bounding box, which is the width and the height, like that. Now we going out from the width, and we going to have the image path variable, and it's going to be os.path join self dot image directory, and we're going to have self dot annotation dot ilog of the index and 0, and the image itself is going to be image dot open image image path, and then the boxes is going to be torch dot tensor. So we change the into the tensor array, basically boxes. Okay, now if self dot transform oh my god, if like that, so it's going to be image, and then boxes is equal to self dot transforms image and the boxes. Oh my god, boxes like that. Now let's get out from that. If now we need to convert to cell, so we got doing label of the label matrix is equal to torch dot zeros of self dot s. Oh my god, self dot s, and then oh my god, self dot s, and then self dot s, and then self dot c, and then self not self dot c, multiply by 5, not multiply but plus 5, and then multiply by 5 with the self dot b, like that. Now for box, in the boxes is going to be the class label and the bounding box coordinates, which is the x, y, width, and the height, and we get those value from box dot toList. Box, okay, and then we need to have the class label is equal to the integer value of the class label. So we want to have the integer value and prevent the float value or the float data type. Now we need to have I, so I would have I and the j, and it will represent the row and the column. Okay, so I is for row and the j is for the column, and it's going to be like for each row and for each column it's going to be the integer of self dot s multiplied by the y, and then the integer of self dot s is going to be multiplied by the x. Okay, and for the x cell and the y cell, it's going to be self dot s multiplied by the x minus for each column, and then self.s multiplied by the y minus for each row, like that. Okay. So we still inside of this for loop, and we need to have the width cell and the height cell, because so we found the x and y cell. Now we need to have the width and the height of the cell, and it's going to be the width multiplied by the self dot s, the amount of grid, and then for the height multiplied by the self dot s, like that. Okay. Okay, what else? Okay, so if there's no object found in the for a specific cell found in the specific cell of I and j. Okay, so cell is basically the grid, and cell is basically the grid. So so this is the row of the grid, and this is the column of the grid. Okay, so if there's no object found in the specific cell of I and j, so this is basically a coordinates, right? A coordinates of the row and the column. So for example, I want to, detecting, like for example, a dog in this particular case. So this dog, like for example, if I doesn't have the dog object, like for example, in the sixth row, in the first row and the second column, which is this box, which is this specific coordinates, which in the the first row and the sixth column, I don't have the object of dogs. So we need to restrict to one object. We need to restrict to one object per cell. So we can do this if the label matrix for a specific coordinates, which is the row and the column, then 20 like that is equal to 0. 20 because we have 20 classes. So first of all, we need to set that there is an object. There is an object. So it's going to be label matrix of those specific coordinates is equal to 1. Not equal to 1, but equal to 1. Okay? Now for the box coordinates, is going to be box coordinates coordinates is equal to torch dot tensor, so change those value into a tensor value, and we need to get the cell, the Y cell, the width cell, and the height cell, like that. Width. So we still inside of this if function, and then the label matrix is going to be I and then J and then 20, not 20 but 21 until 25, which is for the bounding box is going to be equal to the box coordinates, like that. And then we need to set the one hot encoding for class label. Okay, and so the label matrix is going to be Y and then J and then the class label. Class label is equal to 1. Okay. And I guess so now I guess we can get the image. So return the image and the label matrix. So what we are getting from this part? Let me see if my return is correct. So I hope it's outside of this for loop. Let's see. Okay. And okay, so what do we get from this? So we are going to get image that has been split up and get an image that has been split up into S by S grid, and each of those grid will have its own label. Okay, so this is what we are doing in this part. And you know what, let's try to run this. I get an error. So what's the error? It has no data sets. Utils.data has no data sets because it should be data set like that. And yeah, it's correct. So that is the data preparations for the YOLO algorithm. Okay, so in this part I'm going to explain to you about something called the IOU, or intersection of reunion. So what is intersection of reunion? Well, it is quite of a simple concept actually. So here I have an example of intersection of reunion. So let's say you have an image and then you have the object inside of your image. So for this example I have a car, and so this is the first bounding box that is acting as a label. So this is the ground truth bounding box. Okay, so this is the ground truth bounding box. So this is like the true bounding box, and this is the prediction bounding box. Okay, so to evaluate how good this prediction is, all we need to do is we compare the intersections, the size of the intersections over the union. So the union is going to be all of this part. Okay, so I'm going to draw it for you. So for example, I have this cat, and let's say okay, I'm going to do this. So let's say this blue okay, so let's say this blue box is the true label. So this is the true the correct, the label bounding box. Now I have another bounding box. Let's say I have this red bounding box, and this is the predictions. So let's say I have the prediction like this. Okay, so this is the prediction box. Now the intersection of reunion is calculating. So this okay, I'm going to do this. Okay, so intersection is going to be this area. Okay, this is the area of intersection. Oh my god, I'm going to do this. So this okay, so this is the area of intersection. Okay, this is the area of intersection. Like that. Okay, so this is the area of intersections, and this is the area of union. I'm going to do this, and this is the area of union. Let me show you my artistic skill. So this is the area of the union. Okay, let me do this. Okay, so all of this is the area called the union, and this is the area of the intersections here, based on the bounding, the prediction and the label bounding box. So the intersection of a union is basically, we need to calculate the size of the intersection divided by or over by the size of the union. So that is what the intersection of a union is. So in this way we can calculate how much how good our prediction for the bounding box is, and in a computer vision, the correct bounding box is always have the IOU bigger than 0.5. So if you have the IOU of, or the intersection of a union bigger than 0.5, it is the correct predictions basically. Okay, so that is the intersection of a union. Okay, so next I want to show you something called non-max suppression. So what is non-max suppression? So non-max suppression is, okay, I'm going to use this imagination example, and I'm going to do this. Okay, so let's say I have a bounding box. Okay, let's say I have the bounding box, and all of this box is going to be a prediction box. So this is the first prediction of a bounding box. So this is the first prediction, and then I would have another bounding box as a prediction. So this is the first prediction, this is the second prediction, and then maybe this is the third prediction, and maybe this is the fourth prediction. So all of these bounding box, okay, and what the non-max suppression do is I'm going to have a value for each of these bounding box. So for example, okay, wait a minute. Wait, why is it so small? Okay, so I put the value for each of the bounding box. So in the yellow bounding box, I would have 80%, and in the green bounding box, I would have 60%, and in the red bounding box, I would have 40%, and in the blue bounding box, I would have 30%. So what the non-max suppression does is it is suppressing, well, just like its name, all of the bounding box that has lower value than the maximum one. So in this case, the maximum value is 80, which is this yellow bounding box, and so the other bounding box would be suppressed. Okay, would be suppressed based on the maximum value. Okay, so that is what the maximum non-max suppression is. So basically, we get the maximum value and then compare this value into the other value, and all of the other value would be get suppressed based on the higher value that we have. Okay, so that is what non-max suppression is. Okay, so in this part, I would like to explain to you something called about something called mean average precision, or MAP. So what is mean average precision is? So in the mean average precisions, we basically getting like the prediction value. So this is basically for the, so remember in the image classification case, classification case, the accuracy level, we can just compare the label that the neural network has produced, which is the prediction, compare it to the the true label. So we compare the prediction and the true label, and we just comparing in the classification part, we just comparing whether this image has this subject or not. Like, so for example, using this image in a classification problem, I would just say, okay, this image is a cat image, and then the predictions is just telling me whether it is this image has a cat or not. That's it. But in the object detection, it's a little bit different, because in the object detection, we actually have something called the bounding box. We have the bounding box value, and not just the classification value. So the label is not just it's not just it is a cat. Now we also have the bounding box coordinates, which is the x, and then the y, and then the width, and then the height. Okay, so in order to calculate the accuracy, we need something called mean average precisions, because we're not just going to calculate the accuracy for the classifications, but we also calculate the accuracy between the true label of the bounding box and the predictions. Okay, so how can we do that? First of all, we are going to use something called confusion matrix, and in this confusion matrix, we are going to have 4 value, which is true positive, and the true positive is going to be the prediction label is equal to the class and the ground truth label is equal to the class. So that is true positive value. The true negative value is going to be the prediction label is the class while the ground truth is not the class. Okay, and we have the false positive, and the false positive is going to be the prediction label is the class and the ground truth is not the class. Okay, and then finally we have the false negative, and the false negative is going to be the prediction label is not the class and the ground truth label is the class. Okay, so that is the confusion matrix. Now we also need something called a precision and recall. So in the precision and recall, we basically, so in the precision we are going to have something like this. So the true positive, so which is the prediction label is equal to the class and the ground truth label is equal to the class. So the true positive divided by true positive plus false positive, which is the prediction label is the class and the ground truth is not the class. Okay, and we also have something called recall, and recall is the true positive divided by the true positive plus the false negative, while the false negative is the prediction label is not the class and the ground truth label is the class. So this is what the mean average precision is, and all of this value, we are getting all of this value based on the IOU concept. Where is it? So we are getting all of this value based on the intersection of the union concept that we've already talked about. So I'm not gonna lie, I'm not good at explaining this concept because I'm not gonna lie, me myself is not quite get it yet. So but the concept the concept itself is not that complicated, but the thing is I don't know, it's just not quite fun to study, I don't know, but you know, the concept of, so as you can see, the concept for the IOU is quite simple. You just, you know, divide the, so you just have the intersection over the union and then you get the value, and then you get the value, and that is basically comparing the ground truth, not the label and the prediction bounding box. And for the non-max suppressions, you have all of this value, and then you get the highest value, and then you suppress all of the value of all of the bounding box that has less value than the maximum value that you get. That is the non-max suppressions. And for the mean average precisions, this is to calculate the entire predictions, the accuracy for our predictions, not just the classifications, but also we are calculating the accuracy for the prediction label and the and the what's it called, and the bounding box value. So that is what the three concepts that we are going to apply in a YOLO algorithm: intersection over union, non-max suppressions, and the mean average precision. Now let's get into the programming part. Okay, so before we writing the utility, you can call it the utils part, the utility, which is the IOU, the non-max suppression, and the mean average precisions. I would like to fix something inside of this data part. So inside of this data part, I made a mistake, and this is my mistake. It should be annotation like that, and it should be annotation like this, and this one is also should be annotation like that. and yes, I think that's my mistake. Okay, so as you can see, I'm doing this in the next day. So all of my all of my cell is not running yet, so I'm going to run all of the cell. I'm going to run that cell, and then running this cell, and then running this one, and then running this one. Why not? Okay, so I would like to place my utils. Okay, where should I place my utils? Okay, I'm gonna doing it after data and before the loss. So it's going to be utils like this, and the utils is going to be so first of all I'm going to import torch, and then I'm going to import numpy as np. Okay, so what is that import? So I already imported torch. Well, I don't think I need to import torch again. Then I'm going to import matplotlib .pyplot as plt, and then I would have matplotlib .patches as patches, and then from collection I would like to import something called counter. Okay, so let's create the intersection over union like that. Intersection over union, and inside of the intersection over union we would have something box prediction, and then the box label, and then the box format, and let's say the format is going to be the midpoint as the default. Okay, now so to calculate the IOU, you need to have some parameters. The parameters that we are going to have is going to be the box prediction, and it's going to be in tensor, which is the prediction of bounding boxes, and it would have a format something like this. So it's going to be patch patch size and 4, which is for the 4 coordinates, and then you have boxes labels, and it is also going to be tensor, and it's going to be the correct labels of bounding box, and it would have the same format as the predictions. And then finally we have okay, I'm going to do this. So parameters for the IOU, and finally we have the box format. Now this one is going to be a string format, which is basically the midpoint or the corners if boxes, which is the x and y, and then like this, or x1 and then y1 and then x2 and then y2. Okay, so let's do this. So if the box format is equal to midpoint, okay, so for the midpoint for the bounding box is going to be box 1 x1, okay, and it's going to be boxes underscore prediction underscore predictions, and you know what, instead of prediction I'm going to have and labels, because you know, it's going to be a lot. Oh my god. And then I would have something for like this, which is the x coordinates minus the boxes predictions, and then we doing something like this divided by 2. Okay, so and I'm going to copy this part. So that is for the box 1 x1. So for the box 1, and for the y1 is going to be instead of, so it's going to be the y value, and then for this one it's going to be this index. Okay, and for the box 1 and underscore x2 is going to be like this, but we are not doing that, but we are not minus but plus sign. And then after that we have box 1 for the y2, and it's going to be like this, but this one is going to be in the 2, and it is also not minus but plus sign, and this one is going to be 3, and this one is going to be 4. Okay, so that is for the midpoint x1 x2. So that is for the box 1. So for the box 2 we basically almost doing the same like this, but of course this is for the box 2, and then this box 2 like that, and it's going to be box 2 x1 for the prediction, then box label, but so for the box 2 instead of predictions it's going to be the labels, and it is also the labels, so it's going to be like that. Okay, so it's going to be labels, it's going to be labels, and it's also going to be labels, so it is also going to be a label, doing this and doing that. Okay, and I guess that is correct. Now for the, if the box format is equal to corner, we would have something like this. So the box 1 of the x1 is going to be the boxes predictions in the, well, of course in the first index, in the 0 until the first index, which is the first index basically. So and then for the box 1 and then y1 it's going to be boxes predictions of 1 until 2. So I'm going to copy this actually, and then for the box 1 x2 it's going to be this index. Then for the box 2 box 1 for the y2 is going to be 4, and this one is going to be 3. Okay, now for the box 2, so there's the box 1. Now the box 2 is basically the same. Okay, so the box 2 is basically the same, but of course we'll change this to, and then this one is going to be instead of prediction, it's going to be labels. Like this. Okay, and then we going out from the if statement. Okay, now we are going to create x1 is equal to torch dot max, and we are going to have box 1 and x1, and then box 2 and x2, and for the y1 it's going to be the same torch dot max, and of course it's going to be box 1 and then y1 and then box 2 and then the y2. Wait, not it's going to be box 2 and then x1 and y1, like that, supposed to be like that. And then for the x2 it's going to be torch dot max of the box 1 and then x2, and then we have box 2 underscore x2, and then we have the y2 is going to be torch dot max of the box 1 of y2, and then the box 2 of the, and then we have the y2, like that. So okay, let me see, I guess this is correct. I feel like this is correct. So okay, so we need to dot clamp like that if the box is not intersect. So basically we are going to do this intersection is going to be x2 minus x1 dot clamp to 0 multiplied by the not x but y2 minus the y1, and then we clamp the value. Okay, so we would have, and then we would have something like box 1 area is going to be the absolute value of the box 1 and then x2 minus the box 1 and then x1, then multiply by the box 1 and then of y2 minus the box 2, not box but box 1 with the y1. So it's going to be box, so let's see, box 1 x2, box 1 x1, and then box 1 y2, and then box 1 y1. And then for the box 2 area, it's going to be the absolute value of the box 2 x2 minus the box 2 x1 multiplied by the value of the box 2 box 2 minus the y2, and then box not minus y2 but underscore y2, and then minus the box 2 underscore the y1. Okay, so that is the box area, and then we can return the intersection divided by the union. So the union is going to be box okay, you know what, I'm going to do this. Union is going to be the box area, box 1 area plus box 2 area minus the intersection plus 1 of E minus 6 for the just to keep, we're not dividing this intersection with the 0 value. Okay, so over the union like that. Okay, so let's try to run this. So this is the intersection over union. Now we need to have so we finished the intersection over union. Now we need to make the non-max suppression. So the non-max suppression is going to be the bounding box, the IOU threshold, is that the correct way to write threshold? And then the box format, and for default we are going to choose corners. Okay, so for the non-max suppressions, we are okay. So the goal is the list of bounding boxes after performing the NMS given the a specific OU threshold. Okay, so the goal is of a list of bounding box after performing the non-max suppression given a specific IOU threshold. So here's what we are going to do. First of all, I'm going to assert a type of bounding boxes, and it's going to be a list because we want a list boxes, B boxes. Okay, and so the bounding boxes is going to be like this. So box for box in B boxes if box is bigger than the threshold, like that. And the P boxes, we are going to sort all those P boxes with P boxes. Okay, so I'm not gonna lie, I'm not doing quite well right now, so it's a little bit I have a little bit of flu right now, so I'm sorry if my explanation is not quite you know, quite clear. As you can hear, my sinus is quite bad, but you know, let's just keep going. So the key is going to be lambda, and we have x until the x of in the second you know, in the first indexes, and then we're going to reverse those boxes. Okay, and then the P boxes after the the normal suppressions, because this is what we want. We want a list, so we want a list of box given a specific threshold. So this is what we want. Okay, so we want to add the this array. So while boxes is going to be like this, so the chosen box is going to be P boxes under dot pop of 0, like that, and then P boxes is going to be an array, and inside of the array we are going to have box if the box in P boxes, not if but for P boxes, for box in P boxes, if the box in the first index, in the 0 index, is not the same with the chosen box, like that, or intersection over union, and we are going to using the function of intersection over union, and we are going to give the tensor of the chosen box. Box like this with this index, and then after that we are going to have a torch.tensor of the box, and then 2 until 1, and then we are going to have the box format is equal to box format. Okay, and we're doing that with the IOU threshold. Okay, so if we put a threshold here, and then we get the value from the intersection over union, so the intersection over union will give us the value of, well, the intersection over union, and we are going to have the IOU threshold. So remember when I said we have a correct IOU if the IOU is bigger than 0.5. So this is what we are doing. What we are doing here. Okay, and then we going out from this array. So big boxes after the NMS is going to be a pen of the chosen box, like that, and then we can going out oh my god, and press return. Okay, like here, return the B boxes. After the NMS, like that. And I have something wrong here, and okay, what is it? If box is equal to chosen box, b boxes dot pop after s oh, it's supposed to be or not off. So okay, so let's run this, and then well, we get the correct cell running. Now let's create the function for the mean, average, precision, and we are going to need a lot of things. We are going to need the prediction boxes, we are going to need the true boxes, we are going to need the IOU threshold, and the IOU threshold is, well, we are using the standard, which is 0.5 and 0.5, and then the box format, we are going to use the default of a midpoint, like that, and then the number of classes is going to be 20 because we are using the VOC data format that has 20 classes, or has 20 categories. So the goal is okay, I'm gonna do this. Okay, so the goal is the MAP, or the mean average precision value across all classes given a specific IOU threshold, and we want to a float value of this MAP basically. So first, okay, so first of all, we are going to list all of the MAP for each of the classes, MAP for respective class. So the average precision is going to be like this, and then we use for numerical stability, which is the epsilon value, and it's going to be the classic 1 of e minus 6. Now for C, in the range of the number of classes, is going to be detection, and we have the ground truth. Oh my god, and it's going to be like this. So okay, we need to go all the predictions and the targets, and only add the ones that belongs to the current class. So basically we are doing this. So for detection, in the prediction box, if detection of 1 is equal to the class, is equal to the C, to the specific class, detection, oh my god, the detection like this dot append the detection like that, and then going out, and then for the true box we are doing the same thing in the true boxes. So if the true box of 1 is the same as the specific class, the ground truth dot append the true box. Like that, and then we're going out from the for loop. Okay. Okay, so the next thing we do is going out from this loop, and then find the amount, find the amount of the bounding boxes for each training sample. Like that. So we're doing the amount of bounding boxes is going to be, we're going to use the counter, and then we are going to get the GT, and then 0 for GT in the ground truth. The ground truths like that. And what else do we need? Let's create the key. So again we got to create a key. So for key, in and file in amount of bounding boxes, that, like that, and then in the items we are going to list all the amount of the bounding boxes, and that's the key. So we basically creating a dictionary here, and it's going to be equal to the torch dot zeros of the file. like that. And then so we show get the, so basically get not get but sorted out the prediction values, which is in the second. So the prediction value is going to be in the second index, if I'm not mistaken. So it's going to be detections like that dot sort with the key of using the lambda and x until x2, and then we reverse so like that. And then so the true positive is going to be torch dot zeros with the length of the detections like this, and the false positive is going to be torch dot zeros of the length and detection, just the same detection like that. And so for the total of the true bounding boxes is going to be the length of the ground truth, like this. Okay, now okay, so let's see. So if the total is not, it's true. If the total true bounding boxes is equal to 0, we are going to continue, just continue like that. And then for detection IDX with a detection in enumerate, so we are going to enumerate all the detections, and it's going to be the ground truth, image, and it's going to be, oh my god, wait, the ground truth image is going to be the bounding boxes for the, oh my god, bounding boxes, not bounding box but p box, for the p box in the ground truth, if the p box in the first index, which is the index 0, is going to be the same as the detections of 0, like that. And then the number of the ground truth is going to be the length of the ground truth image, like that. So the best IOU, so we start the counting with the 0 value, and now for the index and the ground truth in enumerate of the ground truth image, and it's going to be the IOU in, so we get the value of the IOU by using this IOU function. It's going to be torch.tensor, then detection in this index, index, and then torch.tensor of not detection, but oh my god, what is this nonsense, of the ground truth in this index, which is the opposite. Now for the box format is going to be box format. Okay. Now, if the IOU is less than the best, not less, but is greater than the best IOU, then, well, we need to make those IOU become the best IOU. So the IOU become the IOU, and the best, the ground truth IDX is going to be the IDX itself. In this. Okay, so now we're going out from this for loop, and now if the best IOU is greater than the IOU threshold, we are doing this. So if the amount of the bounding boxes detection in this index and in this index, no, it's something like this, which is the best GT index is equal to 0. So the true positive, so that's wrong. So the true positive is going to be detection IDX. Oh my god, IDX is going to be 1. Okay. Else the false positive 1. The false positive 1 in the detection in that particular index is going to be 1. Oh my god, my sinus. Now we're going from this if statement, and then else the false positive is going to be detection index is equal to 1. Okay, so this is in the case if the IOU is lower than the detection itself. Okay, now so we need to going out from this for loop basically. So let's going out from this for loop, and it's going to be here, not that for loop, but for the from the so this for loop. So we need to going out from that for loop. Is it correct? I don't know. Wait. It's going to be here, I guess. Maybe. Yes. Why not? So in this part, okay, so in this part, the true positive sum is going to be the torch dot sum of the TP, and the dimension is going to be 0. And for the false positive is going to be torch dot sum of the false positive, and it's good to dimension is going to be 0. Okay, so for the recalls, we are going to have the TP, which is the true positive, divided by the total of the true boxes plus the epsilon value, sum, and for the precision is going to be torch dot divide the true positive and the true positive of like this plus the false positive plus the epsilon, like that. And then the precision, oh my god, what is that? And then in the precision again, we are going to have torch dot cat of the torch dot tensor in the first index, and we would have the precision. So that is for the precisions. And wait, cat concaten cat like this, like that. Okay, so again for the recalls, we need to recalls else, and then it's going to be torch dot of the torch dot tensor, and we're going to give 0 and recalls. Like that. Now for the average precision dot append is going to be torch dot traps the precision and the recalls. And then finally we can return, going out from this function, return the sum of the average precision divided by the ln of the average precision, and that is the mean average precision function. Okay, so of course we want to visualize the image, so let's create a function that can visualize the image, which is plotting the image. And of course we are going to need the image and the bounding box. The bounding box. Oh my god, I'm really sorry, I'm not quite I'm a little bit sick right now. I'm really sorry if I'm not explaining things, but hey, the show must go on. So we're going to have im as a variable, and it's going to be the np array, the numpy array for the image, and we need to get the height and the width. Then we are getting this shape, which is the im shape. So we're getting the width and the height. So first of all, we need to create the figure and access, and it's going to be fig and access. Oh my god, it's going to be fig and then access is going to be plt dot subplots, and it's going to be 1 like that, and then we can display the image using x.imshow like this, and we are going to show the image. So for in a bounding box, so the first the 0th index is the x midpoint, and then for in the second index is the width, okay, while in the box in the first index is the y midpoint, and in the 4th index is the height. So it's going to be like not 4, but what is it, 3rd, so the 3rd one. So we need to create a rectangle patch. So okay, I'm going to go here. So for box in boxes, we are going to get the box, and we are going to get the box until box of like this, to get the width until the width value. So we need to assert the length of the box. Oh my god, the length of the box if it's equal to 4. Now the upper left of x is going to be box 0, and then minus box 2, and then divided by 2. And for the upper left of the y coordinates, left for the y coordinates is going to be the box in the first index minus the box 3 divided by 2. Okay, like that. So the rectangle is going to be equal to patches dot rectangle rectangle. Okay, so for the rectangle, we are going to create the upper left of x multiplied by the width, and then the upper left of the y we are going to multiply by the height, and we are doing that with the width like that. And let's see, so the box in this, so this one is going to be by the width. Oh my god, what is this nonsense? And then the box of 3 multiplied by the height, like that. And then for the line weight, it's let's say we choose let's say 1, you know, let's just say 1 is going to be a thin one, and the edge color is going to be red, and then the face color is going to be none. So we have the line weight, the edge color, the face color, and then we need to add the patch. So the patch is going to be x dot add patch into the rectangle, and we are going out and then plot the image, plt.show, like that. So that is the visualization. Oh my god, visualization of the image. Okay, so now we need to have a function to get the boxes. So we define the function and get the bounding boxes. And inside of this function, we are going to have something called loader, and then we are going to have something called oh my god, loader model the IOU threshold, and then we need the prediction format, and let's say the default format is going to be cells, and then the box format is going to be midpoint, and of course the device is going to be q dot. Okay, now okay, so all the prediction boxes is going to be an empty array, and we need all the prediction, not prediction but true, oh my god, boxes is going to be an empty array, and we need to fill all of this empty array. And how can we do that? Well, first we need to evaluate the model. Okay, and then the train IDX, make sure it's 0 for the first iterations. So it's going to be for batch index IDX, comma, the x and the labels in, and enumerate the loader. So it's going to be x is equal to x dot to device, and the labels is going to be, oh my god, labels dot to device, and with torch dot nograd we are going to have the predictions is equal to the model of the x. Now the true boxes, true bounding boxes is equal to the cell boxes. Okay, so I have not created that function yet, apparently. Cell boxes to boxes. So we are going to create this function in a minute and we are going to have the labels, and for the p boxes we are going to have the cells, but the cell box boxes, 2 boxes, and we are going to have the prediction. Okay, now for the IDX, wait, let me evaluate this part with torture or grad and then the predictions and the label. No, it's not supposed to be like that. So I forgot the batch size. It's going to be x dot shape of 0, and this one should be like this. So for the ITX is in range of the patch size. Okay, so for this part we are going to get the non-match suppression boxes, and we are going to call the non-match suppression function to get those boxes, and we are going to have B boxes ITX, and then the IOU threshold is going to be our IOU threshold value. Now the threshold is going to be threshold like that. Yes, and then for the box format, oh my god, format, we are going to have the box format like that. Format. What else? Okay, now for the non-match suppression box. Okay, non-match suppression box in the inside of this part, inside of this variable, we are going to have something like this. So all the prediction, not prediction, the pred boxes dot append the train IDX plus the NMS box. And then for box in the true bounding boxes in that index, we're going to so if the box in the first index is bigger than the threshold, if bigger than the threshold value, we are going to append all of these boxes into the true boxes. Dot append with the train IDX now plus the box. Okay, now we going out from that for loop, and the train IDX is going to be 1 plus 1. And yes, now we can going out and have the model dot train and return all the prediction boxes and also all the true boxes. Okay, now we need to create another function, and it's going to be convert the cell box, and we are going to have the prediction and the grid value. So first of all, we are going to get the prediction, and the prediction dot to CPU, and the batch size is going to be prediction dot shape in the 0th index, and the predictions is equal to the predictions dot reshape, and it's going to be batch size. It's going to be the grid 7 by 7 and 30, like this. Okay. So this is like basically our label, right? Now for the P boxes of 1, the predictions is going to be in the 21 until 25 predictions, like that. So that's for the bounding box 1. So for the bounding boxes 2, the predictions is going to be, oh my god, there's too much dot, in the 26 until 30. Now the scores, we can get the scores by doing torch.cat, and then inside of this cat we are going to have the prediction of in the index, like this, and then we do dot unsqueeze to 0, and the prediction of in this index, instead of this index, dot unsqueeze and into 0, and then the dimension is going to be also 0. So that is what the scores going to be, and the best box is going to be scores dot argmass of 0, and then unsqueeze it, unsqueeze into -1. For the best boxes, it's going to be P boxes of 1 multiplied by the 1 minus the best boxes, the best box, like that. So plus the best box multiplied by the P boxes of 2. Now for cell indices, we are going to have torch dot arrange into 7 by 7, and repeat the batch size with 7, and this was 1 for the dimensions. And we are going to unsqueeze with the value of -1. Now for the x is going to be 1 divided by the amount of grid that we want, and then the best boxes is going to be till 1 plus the cell indices. And then for the y coordinate, we are going to have 1 divided by the s amount of grid, and we are going to have the best boxes in the 1 until 2 plus cell indices, and we are going to permute into 0 to 1 and 3. Now for the W and the Y, is going to be the amount of grid, and for the best boxes, it's going to be 2 until 4 in this index. Now the converted box is going to be a torch.cat of the X, Y, W, and then the not, oh my god, and then the Y with the dimension of -1 to keep that, and we won't have dimension, and then predict that class is going to be predictions of until 20, because the first 20 index is the is the category again, and then we do the argmax of -1, and we unsqueeze those into the -1. Okay, now we need to have the best confidence. And it's going to be torch the maximum output of the predictions, and it's going to be in until the all of the category and the prediction until 25, not until, but in the index 25, and then we unsqueeze the -1. That is the best confidence. Now for the converted prediction, we are going to have, so this is the converted bounding box, and now we need to have the converted predictions, and we are to have torch.cat, and it's going to be predicted class and best confidence and then we're converted P boxes, and I want to have the dimension of equal 1 like this, and finally we can return the converted predictions, and let's see if we did something wrong, at least right now. Okay, so now let's create the functions that we need here, which is this function. Okay, solve to boxes, and it's going to be out and the amount of grid that we have, and so the default is going to be 7. So the converted prediction is going to be convert cell boxes out like this, and then we need to reshape the dimension into the out dot shape, and then something like this, s by s, and then in this dimension, then converted the prediction in this particular index is going to be converted prediction inside of this index dot long. Oh my god. And we have got to have all p boxes. It's going to be an empty array. Now for the ex of idx in the range oh my god, in the range of out dot shape of this amount, and it's going to be p boxes. We have an empty array for that, and we can get all of the p boxes index in the range of the well, s by s. So in our case it's going to be 49 because we are using the index, not the index, but the amount of grid of 7 by 7. So we are going to have 49 probability box. So for the p boxes dot append, and we are going to have x dot item for x in converted prediction is going to be x dot idx, and it's going to be p box underscore idx, and throughout all and just everything after that p boxes, not the like that, and we can get all the p boxes that append, and it's going to be p boxes, and then we can return all of the p boxes. Oh my god. Return all the p boxes. And so let's try to run this now. Well, since we are going to create a model using the Pytorch, so let's save the model, a function that can save the model. And okay, so in this particular training we are to get some specific value of error. So if we get into those specific value of error, we're just going to stop the training and then just save the model in that particular checkpoint, in that particular loss value basically. So basically what we're doing here is we set a value, and that value is going to be the loss value or maybe the accuracy value. And if we get into that value, so for example, if we have 1000 iterations and we get into that value, into that specific value in the, I don't know, in the iteration 200, so we're just going to stop the training and save the model in that particular value. So we can say it's going to be the save checkpoint because we are going to save the model in that particular value. So it's going to be checkpoint, it's going to be state, and the file name that we are going to use is let's say for the default is going to be myolo.pth.tr, and it's going to be the format model. We can print that it's something like this, saving checkpoint like this, why not? And then we can, you know, save the model, torch.save, and it's going to be state and the file name. Now after we save, of course we want to load the model, so load, you can create the load checkpoint, and the load checkpoint, it's going to have checkpoint and the model and also the optimizer. So let's print something like this, loading checkpoint, and we are going to have model dot load state dictionary of checkpoint, and it's going to be a state dictionary. And for the optimizer, we can optimizer like that, get the load state, then dictionary, load state dictionary, and then the checkpoint. Checkpoint is going to be the optimizer. And yes, I guess that's it. We can try to run this model, this part, and yes, that is the utils. It is a lot. But we need all of this. So we've already created basically the model, we create the utils, and we create the loss function, and also we create the data preparations. Now for the last part, we are going, well, not the last part, the next part, we are going to create the training part. So yeah, let's just start to create the training. Okay, so before we get into the training part, I want to show you what the dataset look like. So you can download the Pascal VOC dataset for the YOLO in this using this link, or basically just go to Academic Persons. So this is where I learned the YOLO implementation from scratch basically, and everything that I've already code is basically based from this person implementations. And so this is the Pascal VOC with YOLO, and you can download this dataset. This dataset is quite big, so it has 4.63 gigabyte, and inside of this dataset, so after you download this dataset, you can upload those dataset into your Google Drive, and this is what the dataset look like. So you will have the labels. So let me open this label. Okay, you know what? Let me open it this way. Open with the text editor, and let me open the image for that dataset. Okay, so what is this? I just want to see my text, bro. Okay, so as you can see, like, this is the image that, and this is its label. So okay, so what is this what this number means? So in this part, this one is going to be the label for the category. So remember that in the VOC dataset they have 20 categories, so which mean this dog is going to be in the 11th category. And for this value is going to be the bounding box coordinates. So this is going to be the x, this is going to be the y, this is going to be the width, and this is going to be the height. And as you can see, like this bounding box coordinates is basically around something like this. Okay, so it really close with the corner, so every one of this value. And this is what we want, because based on this image, like the bounding box should be like really close to the corner of these images itself. So that is the image, and that is the label. And if you download from this link, the download Pascal VOC, you will get this CSV file which has 100 example. So let me open this. Can I open this with can I open this with this? So this is what this 100 example CSV look like. So it has the image and it has the label, which is the text label, and it has around 100 images, okay, or 100 example, as you can say. Now that is the data, that is the VOC Pascal dataset. So let's create the training. First of all, okay, let's just import everything. So we are going to import torch, and then we are going to import torch vision dot transform as transforms torch vision, and then import, okay, what transforms, and then torch.optim as optim, and then import torch vision dot transforms dot functional, oh my god, as ft, and from, okay, tqdm, import tqdm. So this is basically a visualization of a visualization progression bar. So that is what this library is. It is a simple library, but it's showing us the progression basically. And then we need to have from torch .utils .data import data loader. Now okay, so let's put a seed of 123, so we can get the same the same initialization value or the same random value. So it's going to be in torch, and then we going to have torch manual seed and it's going to be the seed. Okay, now for the hyperparameter, so we're going to have the learning rate, and it's going to be 2e minus 5. And for the device, of course, we are going to use CUDA if torch dot CUDA dot is available, else we are going to use the CPU. Now the batch size is going to be we are going to be using 16. Now in the paper, in the YOLO paper, they are using 64 batch size, but I don't think the Google Colab, I mean I don't think we can have that many dataset using the Google Colab GPU, but you can, experiment doing it yourself. But for now we are going to use 16 amount of batch size, and the weight decay is going to be 0, and the epoch is going to be 50. We're doing 50 epochs, and then the number of worker is going to be 2. The pin memory is going to be true, and the load model is going to be false, because we are going to train the model, not loading the model. Okay, so let's just create the load model file, and it's going to be, let's say, overfit .pth.tar, and then for the image directory, it's going to be the directory inside of our Google Drive, and for the label directory is going to be inside of our Google Drive. But let's just do that for the moment, and let's focus on the class of the compose, and we're going to have the object, and let's use, and then we can use this init function. Is init, and it's going to be self, and then transforms, to basically self dot transforms is going to be transforms. Okay, after that we can create a function of call, and it's going to be self, and then image, and then the bounding boxes that we have, boxes like this, and it's going to be 40 in the self dot transforms, and it's going to be image, and also the bounding boxes, and it's going to be t image, and then p boxes. So we're going to use the transforms inside of a Pytorch to transform all of the image into, a standard, training image, basically. I'm sorry, my sickness ruined my day, ruined my explanation, and just return the image with its bounding boxes. Oh my god. And okay, so after we create that class, let's just use that class to compose our data. So basically it's going to be transforms dot resize, and it's going to be 448 by 448 of a pixel, and then transforms into tensor like that. I feel like I'm forgetting something. It's should be like that. Should be like that. This also should be inside of an array like that. Okay, now let's create the training function. Train fn. It's going to be the train loader, the model, and the optimizer, and the loss fn. and the loop is going to be the tqdm, so we are going to use the tqdm, and the train loader, then leave is equal to true. Okay, so now we need to create the min loss is equal to an empty array. Now for batch idx and the x and y coordinates in enumerate of the loop, we are going to doing this x and y is equal to x dot to device, and y is also to device, like that. And then the output is going to be the model, so we're going to calling the model and get the output from the model. And the loss the loss is going to be okay. So I'm sorry, this is not coordinate, but this is the the image and the label. Okay, so the loss is going to be loss underscore fn, and it's going to be the output and the label. And then we can create a min loss dot append, like that. Loss dot append is going to be loss dot item. Oh my god. And the optimizer is going to be 0 grad and then loss dot backward, basically doing back propagations, backward, and then the optimizer dot step, like that. And then let's update the progress bar. So the loop dot set postfix fix like this, and then loss is equal to the loss dot item. And then we can going out from this for loop and then print the min. And so the min loss was, and it's going to be the sum of the min loss divided by the ln, the amount of the, not the amount, but the amount of the min loss, just the amount, how much the min loss value it has. Okay, now we can create the main function, and it's going to be the model is going to be the YOLO model that we create here. Where is it? The first part. So this one, the YOLO v1 model. So YOLO v1 and it's going to be split size is equal to 7. Let me go to YOLO v1. Okay, so the split size is going to be 7, which is the amount of grid that we are going to have, and then the number of boxes is going to be 2, the number of classes is going to be 20, and then make it into device, connect into device. Now for the optimizer, it's going to be optim. We are going to use Adam as our optimizer, and inside this Adam we're going to have the model dot parameters, and the learning rate is going to be the amount of learning rate that we've stated before, and the weight decay is going to be the weight decay, like that. Learning rate. Okay, now get the loss, and it's going to be is equal to the YOLO loss. Okay, YOLO loss, like that. It's capital YOLO loss. Now if load model, so if we are loading the model, it's going to be load, we are going to call which one, this part. Okay, so we are going to call this function, which is the load checkpoint, and we are going to have torch dot load, and it's going to be load underscore model underscore file, then the model and also the optimizer. Okay, now for the train. Okay, now for the train dataset. Oh my god, dataset. We are going to have the VOC data set, and it's going to be transforms is equal to transforms, and then the image directory is going to be image directory, and then the label directory is going to be the label directory. Yeah, so let's get all of the path basically. Okay, so in this train dataset we are going to get this example, 100 example CSV, and then copy that path like this, and then for the image directory we are going to copy path and then put it here, and then for the label copy path, then put it there. Okay, and then so let's just copy this test, copy like that, and that is for the train dataset. Now for the test loader, not loader but dataset, it's going to be the same VOC dataset, and we are paste the test part and then transforms basically the same with this. So let's just copy this and do that. Okay, so that is the test dataset. Now for the train loader, is going to be the data loader, and we're going to have the dataset is equal to train dataset. Oh my god, train data set. For the batch size, is equal to batch size, which is in our case we are going to use 16 instead of 64 based on the paper, and the number of worker is equal to num worker. The pin memory is equal to the pin memory, which is 0. For the okay, so let's shuffle the data. So shuffle is equal to true, and then drop last is also equal to true. Okay, so that is for the train loader. Now for the test loader, we are going to have oh my god, data loader, and basically doing the same thing with the training loader. So dataset is equal to test dataset. For the batch size is equal to batch size, and for the num of worker is equal to num worker, and then what else? Pin memory is going to be pin memory, and then the shuffle is equal to true, and drop last is equal to true. Okay, it's something like that. After that, we can create the for loop for the training part. So for epoch in the range of epoch, and we are having 50 epochs, so it's going to be 50 iterations. So for the first part, for the prediction boxes and the target boxes, okay, we are going to get those value from get b boxes, and we are going to throwing the train loader, the model, and then the IOU threshold, and it's going to be 0.5, and the threshold is, oh my god, it's going to be 0.4, let's say. Now for the mean average precision, oh my god, AV precision, we are to call the mean average precision function that we create before, and we are going to throw the prediction boxes, the target boxes, and the IOU threshold, like that, and it's going to be 0.5, and the box format is going to be a midpoint. So now let's print the train MAP is equal to mean average precision, and then we also print the epoch. Okay, now if the mean average precision is less than 0.9, okay, so this is the what I'm talking about, in this where is it, in this part. So we create a checkpoint based on the mean average precisions. If the mean average precision is greater than this value, we are going to get into the checkpoint and we are going to have a dictionary. So the state dictionary is going to equal to the model dot state underscore dictionary, and the optimizer is going to equal to the optimizer dot state underscore dictionary. Okay, now we can save underscore checkpoint and then call the model and then use the checkpoint, and then the file name is equal to the load model file. Okay, now import I'm gonna use time to time.sleep, and it's going to 10. Now let's get out from this if, and the train fn is going to be the train loader in the model and the optimizer and the loss underscore fn. Now we can get out from the main function fn should be fn, then where else? Load checkpoint. Guess that's it. Load fn. So this one is also load fn. Okay. Then we go out and then create the name is going to equal to the main function, and it's going to be running the main function. So yeah, this is the training part. Okay, so this is the training part of our YOLO implementations. Okay, so let's start the training and let's hope it is oh my god, I'm so sorry. Let's hope it is working. It takes a long time to train because there's a lot of dataset. Not just there's a lot of dataset, but there's a lot of kind of calculations, because we also have a lot of, you know, label, not just the input, but the label itself is a lot. So let's just waiting for the training section. And also I'm going to upload all of my, you know, Google Colab file on my video description. So if you want to see my you know, Google Colab file, you can go there. Okay, so with training. So this is the 0 iteration, this is the first iteration, this is the third iteration, and remember we have where is it? We have 50 iterations. Training. Okay, so let's just wait until the training section is finished. Okay, so we finished the training, and this is what we got. So okay, so for this example, I'm assuming it is detecting the bottle, and this one is detecting the cow basically. This one is detecting the person and the cat, and this one's detecting the horse, and I don't know what it is. It's probably going to detect the person, but the bounding box miss a little bit, and I guess this one is detecting the train, and this one is just detecting the house. I don't know, it's not quite and this one is detecting the plane, and let's see if we have another one. This one is detecting the computer, and this one is, well, detecting the car and a person. So this is the YOLO algorithm that we create, and where is it? And again, in the training part, in the training section, I'm actually stopped at this checkpoint, which is the 43 iterations, and I get in the 43 iterations, I get the mean loss is this value, and the loss is this value. Okay, so yes, that is the YOLO implementation from scratch, and I'm not gonna lie, this is like the hardest part in this video. Like, this is the hardest part in this video. So in the next part, I'm going to show you like how can you use the pre-trained YOLO. So it is more simple. It is probably like, you know, I guess we're not even use 15 line of codes. So yeah, in the next video, in the next segment, we are going to use the YOLO pre-trained model, and we are also going to use the pre-trained datasets. So yeah. Okay, so in this part, in this segment, it's going to be the easiest segment. I'm not gonna lie. So we've already studied how to create our own model. How to create our own model. We already studied how the mathematical aspect behind all of this model. We've already studied about image classifications. We already studied about object detections, and we study a lot about, you know, AI optimizations. And now I want to show you, so in the previous segment we've created a YOLO V1 from scratch, and YOLO V1 is basically an old model, and you can go into the Ultralytics website. You can go to docs.ultralytics.com. So this is so Ultralytics is basically okay, I don't know what Ultralytics is, but basically they are who, not responsible, but they are who, you know, basically getting in touch with the YOLO algorithm. So you can explore every YOLO. So okay, not the first, but the newest YOLO that me currently making this video is YOLO 11, which is YOLO V11. But you know, we already study about the YOLO V1, and the reason we study about YOLO V1 is basically because the YOLO V1 is the foundation of all of the YOLO version that is, you know, that is getting uploaded, being open source. So okay, in this part we are going to use the YOLO model. Okay, we are going to use the YOLO model. So previously, remember when we are using the pre-trained model, when we are training, I forgot in which segment, but we are already learned how to use model, pre-trained model for classifications. And now we are going to use the YOLO model, the YOLO pre-trained model, and we are going to use the YOLO V8 model. So you can go into the where is it? Into the models here, and then so I'm going to use, okay, so you can use any version of YOLO, or maybe you can, you know, doing your own experiment and see which one YOLO is, which YOLO version is better. Okay, so in this part I'm going to use YOLO V8. Okay, but again, you can use any of the YOLO. So the reason why I'm using YOLO V8 is because, well, it's quite in the middle. So I hope you are comfortable, you know, getting into the old version of YOLO or the newest version of YOLO. So I'm going to choose the YOLO in the middle. Okay, so here's the overview for the YOLO V model. You can read all of those, of course, and then I want you to scroll down into this part. So so here you have the model. So this is for the YOLO basic model, basically, and then as you can see, this is for the detection, and then you have YOLO V8 for the image segmentation. You have the YOLO for the pose or key points, and then you have oriented detection, and then you have for the classifications, a simple classifications using the YOLO V8. Now I want to show you, okay, I want to download the model of YOLO V8 in a detection task, for detection task. Okay, so here's the YOLO V8 for the detection, and here is the model. So here's the model. So you have 5 YOLO V8 model for image, for object detection, basically, and so okay, you can download all of this model. Okay, you can download all of this model, and as you can see, each of this model has a different size, not different, where is it, parameters. So all of this YOLO model has a different parameters, and I guess N is stands for nano, S is stands for small, M it stands for medium, L is stands for large, and X, I don't know what X stands for, extended version probably. So you can choose your own model, and remember, when you are using a bigger model, the calculations that's going through all of this AI model is going to consume your computer power. So basically you need to choose between you know, how fast your okay, I forgot the English name. Okay, so did you want the speed or did you want the accuracy? So that's basically, so do you want the speed or did you want the accuracy? So if you want the speed, of course you can download the small version of YOLO because it has less parameters compared to the other YOLO. But if you want the accuracy, you can download the larger YOLO model because it has a lot of parameters inside it. So it can, you know, giving you a quite accurate model. Okay, so I already download all of that model. So here's my model. So as you can see, so the N YOLO model, can I do this? I want to show you. Okay, so I already download all of this model, and as you can see, the N YOLO model is a small one. It's only 6 megabyte, and then I have the medium, which is 50 megabyte. I have the small one, which is 22 megabyte. I have the large, which is 85 megabyte, and then YOLO, the YOLO X for 133 megabytes. So all of this model, so now we can use all of this model in our own computer, our own machine. So okay, this is the first time we are using IDE after a long time. So I want you to go into your terminal, okay, and okay, if you're wondering what Python version that I'm using the Python version of 3.11, and okay, I want to quit. Okay, so I want you to install a couple of things. To install the YOLO, so to use the YOLO model, you need to install the YOLO library. And to install the YOLO library, you can just type where is it? You can just type pip install ultralytics. So you can just doing this and then click install. And since I have my own, since I already download, I'm not going to doing that. So I'm just gonna kill this terminal. So now, after you install the ultralytics module for you to execute the YOLO model, I want you to also, okay, I'm going to do this new terminal again. I want you to also install something called CV2, OpenCV. So I want you to install, I want you to doing this to install the OpenCV module. So what is OpenCV? So OpenCV is a library for you to interact between the Python and your camera, basically. So this camera here. So you can play with this playing with this data from OpenCV. So this is the image processing library. So okay, in my machine I installed the OpenCV, this version of OpenCV, which is 4.5.3.56. So if you are the first time installing OpenCV, you're probably going to get the newer model of OpenCV. And I'm not gonna lie, it's been a long time I have OpenCV on my machine, and I never uninstall it, I never updating it. So this is the version that I'm using. This is the OpenCV version that I'm using. So if you want to getting the same kind of so if you want to following me step by step, I'm encouraging you to install this version of OpenCV, because they probably update the library and then change something, and you probably going to get an error if we are using a different OpenCV model, OpenCV version. Okay, so let's start the coding. So it's going to be a real simple. I'm going to have import CV2, and this is going to import the OpenCV library, and then from ultralytics import YOLO. Okay, so that's how you import the YOLO model, not the YOLO model but the YOLO framework. And then you can create a variable called model or whatever, and then we can call the YOLO function, and then we can we can use our YOLO model that we've already download. We can already, so you download this, and then we can use that into our programming. So I'm going to use the YOLO medium just for the for the example, and then I'm going to copy as path and going back to my IDE, paste that, and then I have my model. Okay, so this is the model that I'm using, and I'm using it inside of this YOLO framework. Now I want to doing an object detection in the image. And okay, so remember we are doing an object detection because we are download the model for the object detection. If you want to image classification or segmentation key point, you can download all of this other model. But in this part of the segment, I'm going to use the object detections because that's what YOLO is famous for, which is the object detection. And then we can go into the image, and then we basically giving our image. So here's I have a couple of images. Now I'm going to copy these images, which is copy as path. So I'm going to copy the path to that images, and then R, and then like that. So R string is going to this working as a root. You can say as a root, so that the Python can find the file that you want inside of your machine. Okay, and then we can create a result, and then we can call the model. So the model is using this model, and then we can go into the image and put our image into the model, and then we are going to show is equal to true to show the status or the prediction. And then we can do cv2 dot weight key, and then we can pass 0, and then we can run this program, and let's see. Okay, it's quite long. Okay, I don't know if my OBS, so I'm also making a video, so I don't know if the OBS is also making my machine slower. Okay, now we get a result. From the image that we passing through into the YOLO, and then we get the information about the image. So apparently it has 5%, it has 1 bus, it has 5 backpacks, it has 2 handbags, 2 books, and this is the time where they the prediction works, where they predict. So let's see what the YOLO predicted. Okay, so we are using we are using the medium YOLO model. Okay, so we are using the medium YOLO model, and we get a really good image detections. So it detect the person, it detect the backpacks, it detect the books, it detect the entire bus, even though it's not really a bus. At this point, I'm not gonna lie, but it is a really good detections. Okay, so let's close this, and let's use a different model. So I want to use the nano model, which is the smallest model. So here it only has a 6 megabyte, and then so let's run this, and then let's compare the model. And let's wait just a little bit. Okay, now as you can see, by using the smaller model, you get less accurate of a model. So now we only got the person and then 1 handbag, and then wait, there's a yellow box, 1 handbag and 1 backpack. And well, compared to the previous model, which is the medium model, which is the more the bigger model, this looks like a a really, I'm not gonna say it's a bad model, but it is quite a simple model. I would say that. I'm not gonna say it's a bad model, but it's just a much more simple model. And again, if you want to looking for the accuracy, I'm suggesting you to use the bigger model. But if you want the speed, I'm suggesting you to use the smaller model. Okay, so that is how you can use a YOLO in your computer. Okay, now let's play with this model. So I'm going to use the medium model again, and then I want to detect my image number 4. So image number 4 is going to be like this, and let's run this model. Okay, so this is my another image. So it detecting, well, a lot of person. It detect a bottle. Well, it even detect a tie. So let's see what this model get. So it get 13%. It get one tie. It get 2 bottles. And okay, so yeah, that is the YOLO algorithm, the YOLO pre-trained model. And in the next part, I'm going to show you how can you create your own. So we are going to use the pre-trained YOLO model, but we are going to use our own with our own dataset. Oh my god, we are going to use the YOLO pre-trained model to train our own dataset, and I'm going to show you in the next segment. Okay, so in order to train our own dataset, we can well, there's 2 type of dataset. I would say the first dataset is the dataset that you get from the internet. So if you want to get a dataset from the internet just for you to to having fun study, you can go into the universe.roboflow.com, and then you can get a lot of kind of dataset. So here's they have a lot of dataset. Well, they provide you with the dataset for object detection, for the classification, instance segmentation, key point, and semantic segmentations, and they are having a lot of model for it. So okay, I'm going to find a dataset. So for example, I want to use construction safety, and okay, so here is the I can so here's one of the example of the dataset that we can use, and you can get okay, so you can see the classes. So they have 11 classes, and it is for object detections. And for the classes, they have the boots, the okay, I don't know if you can see that. So the hard hat, the hook, machinery, mask, no hard hat, no mask, no safety vest, person and safety vest, and sky. Why is it sky? Like why the sky is there? I don't know. So okay, in order to download this this model, you can go into this, not the model but dataset. You can go to dataset, or you can I see the images before I download? Okay, so here's the example that they are they can show us. Of course, there's a lot of it's basically a construction safety dataset. So to download this dataset, you can go into the dataset part here, and then, well, because I'm using the YOLO V8 as an example, we can choose to you can click this part, and then you can either download it using the zip to computer or show the code. And I always download the zip to computer, and then you can click continue to download. Now I have the dataset with me already. So here's the construction site safety. So after you download the dataset, you are going to get this folder, and they are going to have 3 folders. So the first folder is going to be the test folder, and inside of this test folder, they are going to have the label, and of course the label is just the class and then the coordinates for the bounding boxes. So they have the label and then they have the images. So that is for the test, and it is similar with the train. They also has the images and the labels, and as you can see, they have the images, they have the labels like this, and then in the validation they also have the labels and the images. Okay, now I'm going to train these images, this dataset, using the YOLO V8 pre-trained model. And to do that, I'm going to go into my Google Colab, because I can use a free GPU. Why not? So we can change the run time into the GPU to get the GPU, and then okay, let's wait. Then I'm going to connect to my Google Drive. So I already uploaded. Okay, so I already upload this construction dataset, custom dataset, into my Google Drive. So okay, so this is basically the same dataset that I'll show you. So this is the construction safety, and this is the validation. It has the train and it has the test folder. Okay, where's my Google Drive? Okay, so to train the model, first of all, we need to install the Ultralytics. We need to install the Ultralytics to get the YOLO frameworks, and then you can just click enter, and then it will download all of the necessary dependencies. And then while we waiting for the download to finish, I'm going to just doing from Ultralytics import YOLO, just like before we did in the detection. Okay, so it already finished. So import YOLO from Ultralytics, and let's run. Okay, so we get a correct execution. Now to train the dataset, okay, I'm going to custom training. Okay, let's use, okay, here's how you can train your own dataset using the YOLO pre-trained model. You can go in something like this, YOLO, and then the test. So you can doing task, and it's going to be let's say detect for object detection, and then you can mode is equal to train model. The mode is going to be train. Okay, so the task is going to be object detection. The mode is going to be train, because we are training our own using our own dataset, and then the model is going to be YOLO V8. I'm going to use the YOLO V8 because in the middle version, and you can choose which model you want to use. So in the detection, as I already mentioned, you can have nano, small, medium, large, or X. So I'm going to use the S1, because this is just for the example, and then .pt, because that is the format data. And then we can have the data is equal to, so it's going to be, well, it's going to be your data basically. So okay, this construction safety is going to be in the content, and it's going to be in the drive, and then my drive datasets, and then it's going to be inside the construction safety, I believe so. So okay, so you know what, I'm just gonna inside of this dataset. Okay, so I'm just gonna copy path like this and like that. So it's going to be construction safety, and then we are using this data.eaml. okay, construction safety slash data dot wait, what is it again? EAML. okay, and then okay, I don't know if you can see that, and then we can how many epochs that we want. Let's say I want just 100 epochs, and then the image size EMGSZ is going to be 640, and then let's try to run this, and let's see. Okay, so okay, data, oh yeah, ML does not exist because it should be data dot YAML, not slash YAML. Okay, let's see what else again. Data dot YAML. Okay, I'm just gonna copy this. Where's my construction safety? Data YAML, copy path. Let's just doing that, and then just let's run this again. Content drive above exceptions direct. Oh, there's too many dots. Oh my god. Okay, so okay, I hope we're running. Okay, so here's the model summary. You can see the model. They have convolutional, and then convolutional, and then all of this, you know, the model architecture, and then it trying to let's wait for the YOLO model to train. Okay, so as you can see, okay, so we are training our model. So this is the first epoch out of 100 epoch, and of course this is the training part. You have to wait until the training process is complete. Okay, so basically after you finish the training, okay, so basically after you finish the training, all of this training process, you can download your YOLO model, and it will appear in here. So it will appear in here as your YOLO model, and then you can download that model, and then just use that model, just the same, which is using the same kind of example that we are using before, because it's going to be the same format. It's basically the same format, but it has a different kind of a data set that it is having, because we are already training with a different data set. And so yeah, that's how you can train the YOLO using the custom data set. Okay, so probably you doesn't want to have getting data from the internet. You want to literally have your own image, and then you want to train a a YOLO model using your literally your own image. I'm recommending you to install this image, label image, and you can do the installation by doing this. So pip install lxml, and then pip install pyqt5, and then you go to the directory that you want to save, and then you can do this command, and then you can run this command, and then after you get this, you can go into the label image master, and then you can run this Python model, not Python model, but Python file, and then you get into this kind of environment. You can click open here, and then you can go into your data. So it's going to be okay, so I have an example. So for example, I want to have my cat, and if you're using YOLO, you can choose this into YOLO. So it's going to be YOLO, and then we can create the rectangle box. So this environment letting you to create a label for your data. So let's say so this is a cat image. You can say it's cat as a label, and then you can click OK, and then you can click save. You can click save, and then you can click save. Okay, after you click save, you can go into your folder, and now you have your imagery, and it will telling you the class. So in this case, the class is apparently number 2, and it will telling you, it will giving you the coordinates for the bounding boxes. So this is how you can create your own literally your own data set, not just downloading the data set from the internet. And then after that, of course, you need to create a folder, and inside of this folder you need to have 3 kind of folders. It will be the test, the train, and the validations. And each of those folder you need to have the image and the labels, and then you can train your data set using this custom model, this custom training YOLO. And then of course you can use your model in using this command. Basically that's what happened. So yeah, I think that's it. I think I'll show you the training. I'm showing you how you can create your own image dataset. I'm showing you how can you using the pre-trained model, showing you how can you download your custom model, and yeah, I think that's it. Okay, so we study a lot, we learn a lot, and this is the end of the video. And if I'm not gonna lie, I'm not expecting so when the first time I'm thinking about creating this video, I'm not expecting this video to be this long. I'm not gonna lie, but you know what, it's quite fun of a project, of a video project. So I'm seeing this video as my own project, and I hope you get a lot of things from it. I hope you get a lot of knowledge from it, and I hope you study a lot. So yeah, bye.